Good morning, everyone. Yeah, Alhamdulillah. Good morning, everyone. Welcome to day 4 of the AMALathon. Thank you to those that have taken the time to join us live. What we're going to be covering today in this additional session is separate science chemistry. Topic 3, quantitative chemistry. So we're going to go through all the numeracy elements that could potentially come into your exam. Later in our chemistry session, we'll be going through the same topic, but we'll be going through the content which is general and is for all different, for the combined and for the triple and for separate science. So, percentage yield. As always, if you have any questions, please ask in the live chat. So why is it not always possible to get all of the product that you should? So this is one of the things that commonly comes up in exams. So when you start looking through past paper questions, you're going to see that this is a question that comes up again and again. And it's not the most complicated question, but it does need a little bit of practice. So the reaction might not finish because you can sometimes have reversible reactions. So you don't always get 100% product. Because number one, because reactions sometimes go backwards, they're reversible. Some of the product can be lost when it's removed from the reaction. So for example, if you're doing a reaction within a test tube or a beaker, not all of it is transferred, and some reactants might react in unexpected ways. You also sometimes lose some of the reactants because they're gases and they diffuse away. Now, definition of yield is the amount of product made in a reaction is called the yield. So this is the actual calculation now. Percentage yield equals mass of product actually made divided by the maximum theoretical mass of product made. So we can calculate mass using mass equals, I love this. This is something which one of my students showed me recently, Mr. Mole. In other words, mass equals MR times the number of moles. So that's how you can work out your theoretical mass. And your actual mass is whatever you found out. Now, the scientist obtains 12.5 grams of zinc iodide. The percentage yield in this reaction is 92%. So what's the maximum theoretical mass of zinc iodide produced in this reaction? Now, if we look at our formula, it is mass, the yield equals mass of what's actually made divided by theoretical. So we're going to think, what bits do we have? So we've got our percentage yield, which is 92%. We've got the actual, which is 12.5 grams, and we don't have the theoretical. Now we're timesing it by 100 because that's how you get a percentage. So in actual fact, what we can do from the beginning is divide that by 92% by 100. So we've got 0.92. And then we can say that 0.92 equals 12.5 divided by the theoretical. Then it's just a matter of rearranging. The theoretical moves this way, the 0.92 moves this way, and so the theoretical equals 12.5 divided by 0.92. So in theory, they should have got 13.586956517 grams. So we round that to one decimal place, which is all you need to do. 1 or 2 decimal places is enough. 13.6 grams, and that grams is missing there. Okay, atom economy. Now I just want to point out, in this kind of question, it's possible you might be given the 12.5 grams, then you know that you've got zinc iodide, so you'd have to work out the MR of zinc iodide. And you'd have to work out the number of moles. or you're given the number of moles, and then from that you can work out the mass, and then you can divide them, and you can then automatically work out what the theoretical yield is. So in some questions you'll have to work out what the theoretical yield is. Now the theoretical yield, how you calculate it, is something that's covered in combined as well, as it is what I've just explained. Mass equals Mr. Mole. Atom economy. Atom economy is the measure of how efficient a chemical reaction is in using all the atoms from the reactants to make the desired product. So atom economy equals the relative formula mass of the desired product divided by the sum of the relative formula mass of all reactants times by 100. So let's do a practice question. So here we've got silver nitrate, AgNO3, plus sodium iodide makes silver iodide plus sodium nitrate. So give your answer to three significant figures. So first, what we've got to do is work out the relative formula mass of each one. Now, at the moment, the question not said what we need to find out the percentage atom economy for, but we can do it for anything. So if we said we want so at the moment we know that silver nitrate has a relative formula mass of 170, sodium iodide is 150, silver iodide is 235, and sodium nitrate is 85. So what we do next is, for example, if I want to know, actually let's look at the question in more detail. So in this particular question, because it's missed out as part of the question, we're trying to find out the atom economy for silver iodide compared to everything. So if we now look back at the actual formula, it's the relative formula mass of the desired product divided by the sum of all the reactants, or it can be the sum of all the products as well. So we want to know the atom economy of silver iodide. So for silver iodide, it was, our MR is 235. Now what we've got to do is divide it by the total of either the reactants or the products. So in this case, if we look at silver nitrate, AgNO3, that's 170. So the MR of that is 170 plus sodium iodide, which is 150. So that equals 320. So we want to do 235 divided by 320. And that equals 73.4%. So we multiply that by 100, so it becomes a percentage, and we get 73.4%. Now let's try the same thing, but this time let's work out the atom economy for sodium nitrate. So let's remove. We can still keep the 320. We're going to keep the 320 because that is the relative formula mass of all the reactants. But this time we're looking at nano3. We're looking at sodium nitrate. And sodium nitrate has a relative formula mass of 85. And then we're going to multiply that by 100. So this time we're working out 85 divided by 320. So it's 26 point. So we times it by 100 as well. So it's 26.6%. And that's how we do atom economy. So a lot of the maths that comes into the higher content, into the triple award content, is actually not too complicated. From a basic perspective, a lot what you do need to do, and I would advise doing it straight away, is going through past paper practice. And then if there's any questions that you're unsure of, just let me know in the live chat, or you can send a message through any of our animations or videos on the YouTube channel through our you can send it through the message that we're sending. If you're in contact with us through WhatsApp, you can just contact us there as well. So how can concentration be measured? Many chemical reactions happen in solutions. Concentration tells us how much solute is dissolved in a solution. So how much solute, that's a solid, is dissolved in a solution. So just a quick recap. This is the liquid that something dissolves into is the solvent. The thing that you dissolve into it is called a solute. And when they mix together, we get a solution. So the solvent is measured in decimeters cubed. It's a liquid, so you measure the volume. Whereas the solute is a solid that you're dissolving in. That's where either you have moles or you have grams, because you're looking at how much you've actually added. Concentration tells us how much solute is dissolved in a solution. It is measured in grams or moles per cubic decimeter. So it could be moles per decimeter cubed, but it could also be grams per decimeter cubed. So I'm just going to write that underneath so you can see both. That means when we're working out concentration, it can either be moles divided by volume, but concentration can also equal the mass divided by the volume. Okay, a potassium nitrate solution contained 0.2 moles. So it's got 0.2 moles of potassium nitrate dissolved in 0.4 decimeters cubed of water. Calculate the mass of potassium nitrate in 25 centimeters cubed of this solution. Now there's two ways we can go about this. This is just a ratio question. But initially when a lot of students look at questions like this, their first reaction is, it looks really complicated. There's lots of numbers, they're thinking how does it fit into a formula? But actually it's just ratio. So one thing we've got to do now is we've got 0.4 decimeters cubed of water gives us 0.2 moles of potassium nitrate, and we've got 25 centimeters cubed of this same solution. So we've got a solution that's made up of 0.4 decimeters cubed and it's got 0.2 moles inside there, and now we're trying to work out from there, if you took 25 centimeters cubed out, how much potassium nitrate would be in there. And we've got the relative formula mass as well. So the first thing we're going to find out is the number of moles in 25 centimeters cubed. Now, we're going to convert the 0.4 decimeters cubed into centimeters cubed, or we can convert the 25 centimeters cubed into decimeters. Now, for myself, I think the easiest way is to convert the decimeters cubed. So that means we're going to multiply it by 1,000. So we've got 400 centimeters cubed. So what that means is in 400 centimeters cubed of solution, we've got 0.2 moles of potassium nitrate. So now how many do we have in 25? So what we've got to do is 25 divided by 400, because remember it's a ratio, it's a proportion. So we want to know what proportion 25 is of 400, and whatever that proportion is, we're going to multiply it by 0.2. Which is what's shown there. So as you can see here, the number of moles is 25 divided by 400. So that becomes a proportion times by 0.2. So the number of moles equals 0.0125. So remember what we said before, mass equals Mr. Mole. The MR times the number of moles. So we know the MR is already given it to us, 101.1. And we've just worked out the number of moles, which are here. So we just multiply them together and we have the mass in grams. And that's a nice 4-mark question. So if there's anyone that didn't fully understand that, you're more than welcome to say, if there's anything at the moment that doesn't make sense, you've just got to mention it in the live chat and I will go through it again. So really good question here, where it says, what is atom economy for and what is it about? Now, with atom economy, it's more something that a business would look at. So it's not something you need to know the answer to. It won't come necessarily. It won't come in a question. It's just more to see. It's more looking at profits. So if you put a certain amount of reactants into something, how much of it actually became the product? So it's more of a profit thing. It's more looking at it from an economical perspective. Now I hope that makes sense, because these are the kind of questions that come up quite often. So if it doesn't, please ask and we will go through it. Okay, now my intention hopefully is to finish this by past. If I can get this completed by past, then we are going to move on to physics 2.5.1. In fact, we should be able to finish this before then. So there was a topic right at the end yesterday that we weren't able to complete, and it is separate science. And after that, we'll do a little bit more physics, linked to physics topic 3. The last part of the physics topic 3 that we're covering today at 12 o'clock, the last part is also separate science. So if we can finish that in this time, that'd be brilliant. Okay, so here's another exam style question. So let's quickly, what I would advise is while I'm talking about it, have a go yourself. And if you want to tell me in the live chat if you got it right or wrong, that would be fantastic. It means that we can, for me, it just shows me what you've understood and not understood. And moving forward, what we will do is we'll do live polls. So students can so students can have a go at the answer and give me, in the poll, it'll have a multiple choice options, and that'll kind of give me an understanding of where students are up to, what they've understood, not understood. Just add a little bit more interaction. So here now we've got 12 centimeters cubed of 0.06 moles per decimeter cubed of phosphoric acid, and that was needed to neutralize 36 centimeters cubed of potassium hydroxide solution. So there we've got 3 KOH, potassium hydroxide. Now for triple award, you should be able to look at this and say that's potassium hydroxide. You should be able to look at H3PO4 and know that P is phosphorus and the H3 represents that and shows that it's an acid, so it's H3PO4, phosphoric acid. And then you've got potassium phosphate and water. Now what we've got here is a ratio of 3:1. So 3 KOH's, potassium hydroxides, react with 1 H3PO4, phosphoric acid. What that means is we've got 3 moles of KOH reacting with 1 mole of H3PO4. So here it says calculate the solution, the concentration of potassium hydroxide. So right now we know centimeters cubed, we know the volume. So what we're going to do here is number of moles. So number of moles equals concentration times the volume divided by, now if the volume is in 12, we've got to convert this to decimeters. So all this is, before we said concentration equals the number of moles divided by volume. We've just rearranged this. So we've rearranged it so that the number of moles equals concentration times volume. And volume needs to be in decimeters, so we divide by 1,000. So that's going to be 0.012. So now if we work out number of moles, it's going to be 0.012 multiplied by the concentration, which is 0.06. And that equals this, 0.00072. Okay, now as I mentioned before, 0.00072. Now, like I said to you guys before, this is one phosphoric acid reacts with 3 potassium hydroxides. So it's a 1:3 ratio. So if our number of moles for H3PO4 is 0.00072, then the number of moles for KOH, potassium hydroxide, is going to be 3 times as much. So for that reason, we multiply it by 3. So moles of KOH is 3 times more than that. Now what does that give us? We now know the number of moles of KOH. So look what we've done at the moment. We've used this formula that we've already covered. Concentration equals number of moles divided by volume. We rearranged that formula so we can work out the number of moles. Number of moles equals concentration times volume, and we had to divide the volume by 1,000 because it was in centimeters cubed. Now we've got the number of moles of phosphoric acid. This shows it's a 3:1 ratio. So whatever the number of moles of phosphoric acid was, we've multiplied it by 3. So we've got the number of moles of potassium hydroxide. So this is where we're up to now. We have 0.00216 moles of potassium hydroxide. Now we know what the moles are. N equals 0.0216. From the information, we know the volume. So volume equals 36, but we're going to divide that by 1,000. So now how do we work out concentration? We just divide them. So we're going to divide those two numbers. So concentration equals 0.0216 divided by 0.0360 or 36, and we get our answer 0.06 moles per decimeter cubed. So units were missed out there, but it's important to add the units. I hope that makes sense. And this is why I'm saying when you finish this, you can rewatch the video, rewatch what I've just gone through, look at how the process works, and try some past paper practice questions. This is as difficult as separate science chemistry is going to become from a numeracy perspective. Okay, amounts and volumes of gases. So when gases are the same temperature and pressure, so when you have the same temperature and the same pressure, you end up with the same number of moles. The same number of moles will be used will take up the same volume. So you'll find that you have the same number of moles within that space, within that volume. So at room temperature, at 20 degrees, and normal atmospheric pressure, 1 mole of any gas occupies 24 decimeters cubed. So whenever you get a question and it says you've got 1 mole of gas, automatically you can do this. V equals 24 decimeters cubed. Because at that point in the question, you might not know what the question's asking for. But at this point, you know 1 mole is going to give you 24 decimeters cubed of volume. So you can work out the volume of gases involved in a reaction by using a balanced chemical equation. So the carbon dioxide was collected at room temperature and pressure. So automatically, if it's collected at room temperature and pressure, we know it's got a volume of 24 decimeters. How many moles of gas, how many moles of oxygen gas is there in 120 centimeters cubed? Now, if 1 mole is 24 decimeters cubed, then how much is going to be in 120 centimeters cubed? So the first thing we're going to do with centimeters cubed is divide it by 1,000. So we can convert it to decimeters. So it's going to be 0.12. I'll add the 0 anyway. Decimeters cubed. Now, if one So now that we know we've got 0.12 decimeters cubed of gas, we just want to find out how many moles are in there. All we're going to do is divide that by 24 because it's a proportion question. So 0.12 divided by 24 and multiplied by 1. But you don't need to multiply it by 1, and that equals 0.005 mole. You don't need these extra zeros. I think someone got excited when they were making the PowerPoint. Excellent, and that is the end of the triple content for AQA Topic 3 Quantitative Chemistry. I am going to go through the rest of this today at 11 AM, but I didn't think we'd end up with enough time. I think there would have been enough time, but because some of the students are doing only combined, it helps to get through some of these topics in the morning. Now I'm just going to bring up Physics Topic 2. And then we're going to start working through Physics Topic 2. So we're going through Physics 2.5.1. So while it's loading up, if anyone has any questions, please keep asking. It has been nice to see how many questions students have actually asked over the last few days. Thank you for your engagement. You can probably tell from the way I'm presenting, I'm not a YouTuber. I don't have that extra special engagement in my voice. I'm just, and even as a teacher, I'm not, maybe as in a class, it's a little bit different because you have people in front of you, but teaching on YouTube is not the same as teaching in a classroom. But it's still been fun, and the more I do it, I'm sure I'll get better and better. So I hope it's still been engaging for you guys, although engagement wasn't at the top of my priority list, but I still hope I've kept you guys engaged. Okay, so 2.5.1. Okay, static electricity. So, how can insulating materials acquire an electrical charge? So insulating materials can gain an electrical charge through friction. So when rubbed against each other, when rubbed against another material, a process known as charging by friction. So this is a really good, that image shows exactly what happens. So electron transfer occurs when two insulating materials are rubbed together, causing one material to lose electrons, becoming positively charged, and the other to gain electrons, becoming negatively charged. So what essentially happens is, you can see here, just where I'm putting this arrow, you've got within every clot, within every atom, you've got the nucleus is always going to be positive, and then you'll have electrons in the outer shells. So in one sense, what's happening here is you're providing enough energy to allow some of those electrons to come off and transfer across to the other material. Now it's a temporary thing because there isn't a necessarily space for those electrons. Because when those electrons move across to the plastic there, the atoms already have full electron shells. There's already covalent bonding. So the electrons stay on the surface, or they're around for a certain amount of time. So temporarily you end up with a difference in charge. So one temporarily becomes positively charged in that it's become more positive temporarily, and one has become more negative temporarily. So what happens when the two electrically charged objects are brought closer together? So when two objects with electric charges are brought near each other, they exert a force on one another. So two objects that carry different types of charges attract. So here you can see in the balloon, if the charges are the same, they'll push away. So if anyone's ever taken a ruler, in fact you can try this at home, you can try it anywhere. If you get a ruler and the kind of plasticky type of ruler, and you rub it against your coats work better. By coat I mean, actually I'm saying coat, I mean more like a suit jacket, that kind of material. Or even if you have a dishcloth at home, that will work. Now, if you go to your tap and just have a small thin stream of water flowing through it, the second you take your ruler towards the water, what happens is the water bends away. That's because water has an area of negativity. That's linked to covalent bonds. I'm just going to very quickly explain this to you. So when we did covalent bonding, let's say this is water. I've made the hydrogen molecules quite big, but then in reality they're not going to be the same size as oxygen. So hydrogen shares one electron, and so does the oxygen. The hydrogen shares one electron, and so does the oxygen. But oxygen's in group 6. That means it's got 1, 2, 3, 4 more electrons in the outer shell. That space there is highly negative. So if you bring across a ruler, like we showed on this slide here, that piece of plastic, and that plastic is also negative, what's it going to do to the water? It's going to repel it. So that's what I mean by point 1. You get repulsion. Anyone that's doing A-level physics, that will help, A-level chemistry, that's something that you'll cover in a bit more detail. Now, two objects that carry different types of charges attract. So you can see here, if you do the same thing, but you do it with, and you put a little piece of tissue on the table, you'll see that that ruler will pick up those pieces of tissue. And that's because the ruler is negative and the tissue has a slightly positive charge. And that happens just from tearing it. You cause some of the electrons to be lost. And two objects with the same type of charge, it's just what it's at being, they repel each other. And attraction and repulsion between the two charged objects serve as examples of non-contact forces. So this shows how this is a non-contact force. So what occurs when two electrically charged objects are placed in close proximity of each other? Now, I am going to go, actually no, this is still static electricity. So what's happening with this balloon is, I'm assuming everyone's at some point, some adult, especially when someone's a child, there's always one adult that comes along with a balloon and shows how someone's hair attaches to the balloon. Now actually what happens is, once you rub that balloon against your clothing, you are increasing the number of electrons in the balloon. Now when you put it up against the wall, because it's negatively charged, what's it going to do to all the electrons in the wall? It's going to push them away. And because it pushes those electrons away, it makes the surface of the wall temporarily positive. So now we've got the negativity that's in the balloon, and we've got the positivity in the wall, and we have an attraction. And that's why the balloon sticks to the wall. And that's why sometimes things stick to us. Similar things can happen in our body as well. Now, objects with the same, all they're trying to show here is that objects with the same charge repel. Objects with opposite charges attract, but that's why the balloon attracts to the wall. Okay, electric fields. Now I'm going to go through what's written here, but I'm going to explain this in my own words, because it's the way some electric fields is sometimes taught or explained is really complicated, when in reality what you're trying to understand is can be quite straightforward. So it says here, an electric field is the area around the charged object where it can exert a force on another charge. Even if the objects aren't touching, a charged object can still push or pull another because of its electric field. So an electric field is the area around a charged object where it can exert a force on another object. So it can exert a force on another charge. So even if the objects aren't touching, so what we've just said, so an example is, if you have a positive charge, it creates a field around it. If you place a negative charge nearby, it gets attracted. So essentially what we're saying is this: what we've caused to form here, due to the way this machine works, you end up with a positive charge. Now when they say electric field, it says an electric field is the area around a charged object. So now all the area around this, because you've got a charge in that piece of metal at the top, in the hollow metal sphere. So you've got a hollow metal sphere at the top, it has a charge, and the area around that charged object can exert a force on another charge. So if something comes in within this field, it can exert a force on it. So depending on what the charge of it is, it's either going to pull it towards itself, or it's going to push it away. Same way magnets work, even if they're not touching. So what you end up with is an electric field around that charged hollow sphere. Now, even if they're not touching. So a positive charge creates a field around it. So now we've got a positive charge and we have a field around it. If you place a nearby, and this is what I mean by where it doesn't have to be that complicated. Now, we've got the hollow metal sphere, it's got a charge. If we now bring into that vicinity there a negative charge, what's going to happen? It's going to be attracted. If we bring into that field a positive charge, it's going to be repelled. So fields, electric fields, cause forces. So the strength of an electric field depends on the charge producing it and the distance from the charge. A stronger charge creates a stronger field. So when you're charging it up, the more charge put into it, the stronger the electric field is going to be. Now, when you're drawing the electric field lines, what you've got to remember is this: the arrows are going to point outwards if it's a positive charge. So here you've got positive charge, which way the arrow's pointing? Outwards. If it's a negative charge, the arrows point inwards. So it would be the same thing, but the arrows would point inwards. So if there's a negative charge, the arrows point inwards. Now, between the two opposite charges, arrows always go. So if you've got two charges, I've gone to the next point. So when we draw electric fields using field lines, there's a few rules. One is lines always go from positive towards negative, and that shows the direction a positive test charge would make. And the closer the line, the stronger the field. Also, the lines have to be drawn uniform. So when you draw positive lines, it's always outwards. You can see from the lines that you've got equal distance between all of them, so they're uniform. And the closer the lines are, so if you had more lines and they were close to each other, it shows that the field is stronger. The lines never cross. Now, when it's a positive charge, the arrows point outwards. When it's a negative charge, the arrows point inwards. And when you've got two opposite charges, then the arrows go from positive to negative. which you can see. The arrows for negative go inwards, the arrows for positive go outwards. So it would always go from positive to negative. So arrows, if they were between these two, would go that way. So what do electric fields actually do? So let's quickly just finish this bit. Radial field lines, so outward for positive, inward for negative charges. Even distribution, so the lines are evenly spaced and point straight out. Strength variation, so you have the strongest near the surface and weaker when you get, I should say, further away. So it's inversely proportional to distance squared. What this means is, closer to the surface, if you look at the lines are closer to each other. As you get further and further apart, the lines become more and more distant, so the strength of the electric field reduces. And the other thing to keep a note of, to keep in mind, is that, like I mentioned, there's no field inside the sphere. So inside the sphere where the charge is being generated, or the electric field is being created, there's no charge. So you never put the electric fields within the sphere. So the field inside is zero due to surface charge redistribution, meaning all the electric field is then being generated from the surface, not from within. It's a hollow sphere. So how does sparking occur? Sparking occurs when there's a build-up of electrical charge. When a build-up of electrical charge is suddenly discharged through the air. This occurs due to the breakdown of air as an insulator. So, first thing, when the charge builds up, the static charge builds up on an object. For example, when you're rubbing a balloon. So what you're starting to do, so in this case, when you have, for example, a cloud, on quite days when it's quite hot and cold, the hotter the clouds are, they start moving upwards because they've got more energy. As they start cooling, the water starts to condense and they move lower. Now, as different clouds rub past each other, we have the exchange of electrons. So we end up with difference in charge. Some become more negative, some become more positive. So that means there's a buildup of charge. The field becomes strong enough to affect nearby air. So eventually, you get such a big difference that you end up with a high electrical field strength. The field becomes strong enough to affect nearby air, and at that point, as the energy transfers through the particles, it ionizes the air. So the electrons are removed from the air molecules, making the air conductive. Now, this is something that I've not covered with you at the moment, but we're going to cover in topic 4 physics, is that if you have an electron, for example, you have an electron in this shell, if it gains energy, it can become excited and go to a higher energy state. Now, when that electron drops back down to its original position, it emits that energy as electromagnetic radiation. But we can also have this scenario where the electron goes to a higher state, but then it gains even more energy, and even the electron in the outer shell, they can gain enough energy to separate themselves, free themselves from the atom. This is what happens in the middle of the sun. So if you think of fusion, for those that have covered it in school, I'm assuming everyone has by now, in the topic of space, if you think about fusion, hydrogen and helium, when they're produced, they don't have electrons. Why do they not have electrons? Because they've dissipated. There's so much energy there that they've dissipated. So when this electrical charge now goes through the air, the electrons in a sense dissipate, so they become ionized. That means the air becomes conductive. So if the electric field is strong enough, it can ionize the air and cause sparks to jump through it. At which point it then looks for a grounding. So that sudden discharge, the charge then flows through the air, creating a visible spark. In other words, lightning. It can happen. You probably felt it sometimes when you shake someone's hand or you touch. You touch someone and you get like an electric shock. That's exactly what's happening there. Okay, excellent. So that topic is finished as well. Okay, I'm going to now go to physics topic 3. And we're just going to go to the last bit. Now at 5 to 10, I will give everyone a 5-minute break and then we'll restart at 10. Okay, pressure in gases. So again, this is triple award content only. And again, if you have questions, please ask. So how can gas be compressed or expanded? So we're now looking at pressure in gases. Now this does tie in with the content that we're going to finish later on today. So it would have been better if I taught it to you afterwards. But this is the time that we have at the moment. Karuba, apologies, I might not get time to... I have got a note of your question, but if it's okay, I'm going to answer it tomorrow between 9:45 and 10 a.m. So I'm really sorry, it is in my mind, and I did prepare for that, but I will answer it properly tomorrow, if that's okay. So how can gas be compressed or expanded? So a gas can be compressed by reducing the volume of its container, because that way particles are forced closer together. So if you're all your particles in a large container and it's a closed system, if you reduce the size of it, as long as no particles can enter, you still have the same number of particles, but now they're closer together. That means pressure increases. Because what we've got to understand here is, what is pressure? Pressure is when a force is exerted, because pressure equals force divided by area. It is the force exerted over a certain area. And the smaller the area the force is exerted on, the bigger the pressure. So in this sense, it is every time a particle collides with the side, with the wall, that then a pressure is exerted. But if you decrease the volume, then more particles are going to hit the side of the container. So if more particles are hitting the side of the container, we have an increase in pressure. Now a gas can be expanded by increasing the volume of its container. So if you increase the volume of the container, that means particles won't hit the side as often, so the pressure decreases. Pressure can be, now this is specific to triple content. Pressure times volume equals a constant. So we've got pascals, meters cubed for volume, and what is work? So doing work on gas increases its internal energy. So let me just explain here. If we were to rearrange this, then pressure equals K over V. So what we're essentially saying is that pressure is inversely proportional to the volume. So if you increase the volume, what happens? You decrease the pressure. If you decrease the volume, you increase the pressure. So that formula is just explaining this. So if you increase the volume, you decrease the pressure. So pressure equals a constant divided by volume. So they're inversely proportional to each other. So what is work? Doing work on a gas increases its internal energy. So remember, work done equals force times distance. So doing work on a gas increases its internal energy, which may result in a rise in temperature. So every time these gas particles collide with each other or into anything else, they move a certain distance, they exert a force, so in a sense work is done. So now if you decrease the volume, you have more particles colliding with each other, so you have which causes an increase in internal energy. And if you increase the internal energy, that usually is represented as a rise in temperature. So why does pressure of gas increase when its temperature is increased? When temperature increases, gas particles gain kinetic energy. So remember that kinetic energy, always go back to formulas, is half times the mass times the velocity squared. Now, if we're increasing the energy, we can't change the mass. What's the only thing that's going to change? The speed at which it moves, the velocity. So if you increase energy, you automatically increase its speed. They move faster. Now, if they're moving faster, they're going to collide more often with the walls of the container, which means greater pressure. Now, each collision also happens with more force because they've got more energy, and that results in higher pressure inside the container. So why does pressure increase when a gas is compressed? So when a gas is compressed, its volume decreases. The particles are now closer together, and because they're closer together, they're more likely to collide, and they're more likely to collide with the walls of the container. That means each collision also happens with more force. We end up with more frequent collisions, which means there's more force on the walls, which increases the pressure. Okay, thank you everyone. We're gonna take a break till 10 o'clock, and then we're going to restart with biology, the end part of topic 2 and the starting of topic 3. So thank you everyone for joining a little bit earlier. We'll be back in a few minutes. Good morning and welcome to day 4 of AQA AMALathon. So we're going to continue with topic 2 biology today. We're going to finish this off and then we're going to start topic 3 biology. So if you have any questions, they can go straight into the live chat. If I'm able to answer them, I'll answer them straight away. The ones I can't answer, I'll answer during our specific time. Now, there was one question that was asked yesterday, amazing question, in fact. Why does proportionality change between voltage and current in V equals IR formula and power equals IV formula? I've not been able to answer that today because I was doing some triple award content, but I will answer that question tomorrow morning at 9:45. It's not something that you necessarily need to know for GCSE. However, the understanding that comes from it does help to understand electricity a bit better. So I will go through it. It will take a few minutes to go through. It is quite a big question. In fact, it's an impressive question. Really good question. Okay, so coronary heart disease. The definition of CHD or coronary heart disease is as a condition where the coronary heart arteries, now the coronary arteries are the ones that supply oxygen-rich blood to the heart, they become narrow or blocked due to a buildup of fatty deposits or plaques. This reduces blood flow to the heart, increasing the risk of chest pain, which is angina, heart attacks, and other complications. The main thing that we're saying here is that the coronary artery. So even though this is where some people get confused. They think, why does the heart need its own supply? Now, when the heart has blood inside it, it's got so many cells that the oxygen from that blood can't reach. So the blood, once it's pumped out to the rest of the body, it has its own supply going through the coronary artery. Now the coronary artery, then eventually the blood from the coronary artery goes to capillaries that feed the whole of the heart. That supply, by feed I mean they supply the heart with its own supply of oxygen. And that way the heart can keep contracting. Now if the oxygen does not reach the coronary artery, if the coronary artery is blocked, that means the blood's not going to reach the heart. If it doesn't reach the heart, then we've got an issue. And what's that issue? That the cells aren't getting oxygen, which means they can't do respiration. So this goes back to topic 1. It goes right back to basics. Mitochondria. What happens in the mitochondria? Respiration. Respiration is glucose plus oxygen, makes carbon dioxide plus water. So you have to be able to make these small connections, especially if we're aiming for grade 9. And how do we understand these small connections better? Lots and lots of past paper practice. So the causes is atherosclerosis is the most common cause. This is when fatty deposits build up on the arteries. What actually happens within arteries, and we're not just talking about the coronary artery here, is that sometimes the lining can get damaged. When it does become damaged, it makes it easier for fatty deposits or cholesterol to build in that area. So it's a little bit like if that's the surface, you get some damage, the body repairs the damage, but now the area is just slightly rougher than the other areas, so it's easier for just little bits of fat to start attaching. And it just starts as a thin layer, then another layer comes across, another layer, and before we know it, it's a blockage. But not before we know it. It does take time. But a healthy diet can reverse all of these things. So the symptoms of coronary artery disease, or coronary heart disease, include chest pains, chest tightness, which is angina, shortness of breath, neck pain, and numbness of legs or arms. So what are stents? So if someone does have this, so essentially what we're saying is that's the artery and we had a damage there, then over time the layers are built up till there's a bit of a blockage. Now The blockage does not have to be the whole way through. It can just be a partial blockage, but even that partial blockage is going to slow down the red blood cells that are trying to get through. And that means you have a slowing down there, and that's why you can get some of these pains. So if you look at these, shortness of breath, that's because you have a reduced, because now if less red blood cells are getting through, so you can see here, you've got less red blood cells going through, that means you've got less oxygen getting to your mains, getting to certain cells, so you start to feel pain in those areas. You start to get a bit of numbness in those areas because the cells aren't getting enough oxygen. So stents are small mesh tubes. So stents are small mesh tubes used to keep arteries open and ensure blood flows properly to the heart. So what this stent actually does is, and I'll show this with this pen, the stent is, actually let me see if the picture's here. So initially you've got, if you can see that little mesh and it's got a balloon inside. So this is actually stage 1. So this is slightly in the wrong order, but that doesn't make too much of a difference. It's got the mesh with the balloon inside. Once it reaches the area where the blockage is, or where there's a buildup of fatty deposits or cholesterol, the balloon is blows up, and then the balloon part is removed. So what you're left with is so this is step 2, then you're left with step 3. So the mesh is now open, it's keeping the artery open, it's keeping the fatty deposits pushed to one side, and now our red blood cells can continue moving through. So what it essentially does is it restores blood flow to the heart, it reduces the risk of heart attacks, and it also reduces the risk of blood clots. Because if you've got this situation scenario here, you can get a buildup of blood caused by this fatty deposit, and that can start to form a clot and a further blockage. So these are different ways of treating coronary heart disease. We've got statins. Now what statins do, the type of medication, and they attach themselves to some of the excess fat. So it lowers blood cholesterol, it reduces fatty deposits, but the disadvantages are that it causes muscle pain and weakness. Artificial heart, this is not really used too much, but it's a temporary heart support. So this is where people have, if anyone has ever had a heart transplant, for example, they would put the artificial temporary heart in place so the blood keeps flowing around the body. So it helps with transplants, but there's a major risk of clots and infection. But at that point, if someone's heart is at the point where they're having to have if anyone's at the point where their heart needs to be replaced, then the risk of blood clots or infection wouldn't be high up on the list. Now, if we're looking at with stents, the positive with stents are that they restore blood flow to the heart, they reduce the risk of heart attacks, but a negative is the risk of blood clots. And partially, and that risk of blood clots, apologies, I explained something completely different when that came up. So thank you, Nadia, for pointing that out. You're absolutely right. With the actual metal mesh there, you can start to get a build-up of fatty deposits again. You can start to get bits of blood that start to clot as well. So there are side effects, there are negatives to the stent as well. Yeah, so thank you, Nadia, for pointing out. I linked it to something completely different. Now, heart transplant replaces the faulty heart, but that's very uncommon. And if anyone's had a heart transplant, it requires lifelong medication, because essentially the body treats that new heart as an invader, the same way it would treat bacteria and viruses. And mechanical valve. This is something that's commonly used. This is where the valves in the heart, due to high blood pressure, they become damaged. So when we've showed the valves previously, we've shown them looking like this, But imagine constantly the blood goes through really fast. The blood's going through really, really fast. It's a bit like every time you walk out the door, if you slam the door, you slam it open and you slam it shut, eventually the door's going to break. So what can happen is, instead of the valves looking like this, they start to look more like that. And they never fully close, which means you constantly have a little bit of blood going back from the ventricles back to the atrium. So mechanical valves, these valves can be replaced. So cardiovascular disease treatment includes medication, surgery, and lifestyle changes. Each has benefits and limitations, with the best approach depending on the individual. Treating both symptoms and causes improves quality of life and reduces complications. Okay, so there's a few health issues. So here's a few key terms. Health means health is a state of complete physical, mental, and social well-being. It's not just the absence of disease or illness. So that's the definition from WHO, the World Health Organization. Pathogen is a microorganism such as virus, bacteria, fungus, or parasite that causes disease in a host organism. So this will all help in the next part of this. Cancer is a disease caused by uncontrolled cell division. So whenever the word cancer comes up into an exam, the word that we need to keep in mind, the word that we need to use is uncontrolled cell division, which leads to the formation of tumours and potential spread to other parts of the body. So you've got two different types of tumours, one that stays in one place and one where parts of the cells start breaking off, and then the uncontrolled cell division happens wherever they land, wherever they stop. Then you've got non-communicable diseases. These are diseases that are either genetic or due to lifestyle and environment. So for example, diabetes type 2 is partially genetic but also partially because of a person's diet. Cardiovascular heart disease is partially genetic, partially because of diet. But the whole point here is, if you stand next to someone who's got cancer, diabetes, heart disease, it doesn't spread to you. So non-communicable diseases are the ones that don't spread from person to person, whereas a communicable disease is a disease that passes from person to person by a pathogen. So the pathogen causes it to move from person to person, and it can go through direct contact, the air, water, or vectors. So bacterial and viral infections can act as triggers for other serious health conditions. For example, certain bacterial infections may lead to long-term inflammation, increasing the risk of heart disease. So what we're trying to say here is that some communicable illnesses or diseases can lead to non-communicable. So the example here is that bacterial and viral infections can act as triggers for other serious health complications. So the bacterial infection might lead to something that's more long-term, like heart problems. Poor diet and lack of exercise contribute to non-communicable diseases. So things like obesity, due to a poor diet and lack of exercise, that can lead to type 2 diabetes, high blood pressure, and cardiovascular diseases. Exposure to carcinogens increases the risk of cancer. So substances like tobacco smoke, UV radiation, harmful chemicals can cause mutations in cells, leading to uncontrolled growth and tumor formation. So things like cigarettes, etc., do have a lot of carcinogens. Carcinogen just means a substance that can lead to cancer. Excessive alcohol consumption damages organs. So things like excessive alcohol consumption will lead to liver disease. It can lead to brain damage. It can also cause issues to the fetus. Mental health issues can be linked to physical health conditions. Things like chronic stress, anxiety can weaken the immune system. There is a connection between the two. It can weaken the immune system, which contributes to heart disease, high blood pressure, and digestive issues. Malnutrition affects overall health and development. So a lack of essential nutrients can lead to weakened immunity. It can lead to stunted growth, and increase susceptibility to infections. Lifestyle. So lifestyle refers to the way a person lives, including daily habits, behaviors, choices, and activities. It encompasses aspects such as diet, exercise, work, social interactions, and overall health practices, which collectively influence physical and mental well-being. So what we've already covered, diet and exercise lead to a lot of non-communicable illnesses. Alcohol can lead to non-communicable illnesses, and so can smoking. And things like smoking can lead to low birth weight of a child. Now, a lot of these issues when it comes to smoking is because when a person smokes, they are taking in lots of chemicals, they're taking carbon monoxide, and some of these things pass to the child through the placenta, through the umbilical cord and the placenta. Also, they have a knock-on effect to the amount of oxygen that's in the pregnant lady's blood, which means sometimes you have a reduction in oxygen going to the child, so that can lead to low birth weight. It can lead to premature birth, miscarriage and stillbirth, and it can lead to birth defects as well. And sudden infant death syndrome. Then, and that's all linked to this, because the effects of pregnancy, of smoking on the actual pregnancy, it can weaken the immune system. It causes developmental issues in the child as well. It causes issues with the placenta. So smoking can cause placental abruption. In other words, it can destroy parts of. Yes, this is still combined. It can destroy some of the placenta. And it reduces, one of the big things, it reduces oxygen supply. All I'm doing here is I'm just going into this with a bit more detail. You don't necessarily need to know this level of detail, but it is still combined. So, cancer. Now, we've already kind of covered this. What I said before is essentially what's going to come up now is uncontrolled growth and division due to a mutation. So, when we cover protein synthesis, one thing you're going to understand is that, in fact, I have partially explained this. When you've got a stem cell, why does a stem cell differentiate or specialize? That's because within the genes that are there, that within the DNA inside, it has the genes for every single protein inside the body. Actually, I've just gone into a bit more detail. You don't necessarily need to know that level of detail. It's just to kind of expand on how something like smoking has an impact. So don't worry, it's not because you do get questions on smoking. It just helps to have that little bit of extra info. You don't need to memorize it. So if you've got a gene, for it to become, for example, a red blood cell, then certain parts of the gene have to be turned on, certain parts of the gene have to be turned off. Now, within the gene, now I know this is triple, but it's just to explain the science behind it. Within the bases within the gene, you have some parts of the base, some that code for the gene, and you've also got non-coding. So you've got coding parts of the gene and you've got non-coding parts of the gene. So with a non-coding part, I'm just going to do it in a different color. So let's say this part's non-coding. So some genes are called coding genes and some are called non-coding gene. So this part here, the coding gene, that part there will give the information to the ribosome to make the actual protein. But this part here, the non-coding part, gives the information to the gene on how much of that protein should be made and when it should be made. Now, if you get a mutation in the non-coding part of the gene, it could be that the information changes, so now not enough protein is made or too much protein is made. And it's a similar kind of thing that happens in cancer. It's when a certain gene is turned on or turned off, and so the cells start to multiply rapidly, uncontrolled. So here you can see one cell becomes 2, 2 become 4, and so on. But here we've gone from 1 to 2 to 6 to many. So it's multiplying rapidly, it's uncontrolled. And then we've got two different types, benign and malignant. So benign are the ones that we don't consider to be life-threatening. They can still cause health issues because they press on vital organs or tissues, but they are localized in one area. That means that one area can be treated and the person can be cancer-free. Malignant, however, is when, for example, part of this breaks off. So the cancer cell breaks off, it flows through the bloodstream, and then wherever it stops, it starts multiplying again. So you end up with another cancerous, a person can end up with another cancerous tumor in another area, another region. So here's an exam style question. Actually, just to answer your question, can we go through exam questions so we get focus, exam content and practice? Generally speaking, the main aim of the AMALathon was to go through content. So I have, I suppose, been skipping through some of the questions, but since you've asked, I will pause at the questions and go through the questions in a bit more detail. It's just I want to make sure all the content has been covered by Thursday, because I won't be able to give any time beyond that, and I don't want to leave when I've only covered 75% or 80% of the content. Like I said to you guys, as you're outside of the AMALathon, if you ever come across a question that doesn't make sense, if you just let me know, because if you go to one of our posts and just send a message through one of our posts that just says, I was doing, for example, paper 2018 question 3 in combined science or triple award, did it make sense, could you explain it? What I'll do is I can make a quick video and upload it with the answer, or I can also or I can just answer it on give you a direct answer. It'll either be myself or someone from the team that I'll reply, but we're happy to do that. That's the kind of company we want to be. So you're more than welcome to communicate with us. So what you can do is contact us outside of the sessions, but I will be going through lots of past paper questions in the pre-exam workshop. So the pre-exam workshop will be on the weekend prior to every single exam. The whole session will just be past paper practice, and it'll be past paper practice linked to the topics that I think are more likely to come up. So it'll be a chance to revise as well. So I'll be going through the paper 2 content in the May half-term holidays. It'll be exactly like this. I'll be covering all the content. So just to recap, we're going through all paper 1 content now. Then you've got your 3 paper 1 exams during May, and the weekend before each one, I'll be going through lots of paper 1 practice. Then we'll have paper 2 content. I'll be covering it just like this in 18 hours. It'll be another AMALathon. So a marathon with myself explaining everything. And then in June, you'll have 3 paper 2 exams. And before each exam, I'll be doing past paper practice. We'll just link to the topics that I know or I feel are more likely to come up. Now, I'm usually around 80% accurate. But like I said, if you have any questions outside of this, please ask. I'll make a short clip or a short video just quickly going through it. So, exam style questions. Describe how tumours form. So tumours form due to abnormal and uncontrolled cell division. So all we're talking about here is describe. When it says describe, it's one of those kind of questions that you just memorize and you just give the answer to it. So how to describe how tumours form is due to, and the main part of the answer is this: uncontrolled cell division. Benign tumours do not spread to other parts of the body. Malignant tumours can spread and invade nearby tissues. How is it that some tumours might spread to other parts of the body? So now when you say we need to describe how it gets from one place to the other. Cancer cells can travel in the blood or the lymphatic system to form secondary tumours. So it's this part here. They travel through the bloodstream to form secondary tumours. So we've covered this part in the blood to form secondary tumours. So if you look at just these 2 slides, these are the main questions that can come up on this. So these are the main 3 questions. How do tumours form? Or what's cancer? Uncontrolled cell division. What's the difference between a malignant and a benign tumour? It's this. One doesn't spread and one does spread. And how does it spread? It spreads in the blood. So that set of exam questions, if anything, just summarizes everything. Describe the trends in the number of people with malignant melanoma from 1985 to 2008. So I'm going to zoom into this so you can see it. So if you look at the question, it says we can still see the question if I zoom in this much. Describe the trends in the number of people with malignant melanoma 1985 to 2008. Now let's look at all the information first. So we've got the line that doesn't have any dashes. That's for all people. Then we've got the dashed line for rich people, and the dash with the dotted line. So the dotted line for poor people. So describe the trends in the number of people with malignant melanoma. So first thing, because it says describe, we are literally describing what we can see. So what's the first thing we can see here? We can see from 1985, and we're looking at total number of trips abroad, number of cheap holidays in the sun. So the first thing we can see from 1985 to 2008, it's increasing. So that's the first part of the answer. The incidence of melanoma is increasing over time. So we're initially just saying this is what we can see in the graph. It's increasing. Then now let's have a look at this part here. The number of people with malignant melanoma in the UK per 100,000 people. We can see the number of people with malignant melanoma is increasing. Now if you look at that line, what's happening to its gradient as time increases? The gradient's getting steeper. So that means the number of cases rising more rapidly in recent years. Now it doesn't need to be written in those words. It can just be that looking at the gradient, the line's getting steeper and steeper, which means more and more people are getting malignant melanoma. And if you look at the gap between the rich and the poor. And the gap between the rich and the poor is quite big initially. Now, malignant melanoma is skin cancer. Now that would have been, if we read the whole question, that would be part of the information. So I'll give that to you now. And what it shows is in 1985, richer people getting more malignant melanoma, and now, so the gap here is bigger and the gap here is smaller. Now that's the description. If it said, can you explain why that might have happened? Then if you're trying to now explain why, if you look at the difference in the holidays, that would be part of the explanation why. Because it says total number of trips abroad. So the total number of trips abroad is greater in both of them. There's more trips abroad, and number of cheap holidays in the sun has increased from 1985 to 2005. So if we compare the cheap holidays in the sun, that means now the cheap holidays in the sun are more affordable. More people from poorer areas are going on these cheap holidays in the sun, so therefore there's an increase in the melanoma. So now we explain the why, but this question is just description. Okay, 2.3.1, plant tissues. So plants have different types of tissues that perform specific functions for growth, support, and transport. Okay, so if you just excuse me for 1 second. There's something I just want to quickly check. The main types of plant tissues include epidermal tissue, palisade, mesophyll, spongy mesophyll, the xylem and phloem. So that's important for us to know about. The guard cell and the stomata. So the epidermal, that forms the outer layer of the plant. It helps protect against water loss and pathogens. Then the palisade layer is where you've got lots and lots of chloroplasts for photosynthesis. The spongy mesophyll layer is where you've got air spaces. The air spaces facilitate gas exchange. Xylem, this is one of our key terms. It transports water and minerals from the roots to the leaves. The phloem transports sugars produced during photosynthesis at different parts of the plant. And meristem tissue, found in growing regions like the tips of the shoots and the roots, responsible for cell division and plant growth. So, plant organ system. Cells are uniquely adapted to carry out specific functions efficiently within an organism. So, if you look at these root hair cells, the function of this root hair cell is to efficiently absorb water and nutrients from the soil. So this is something we've already covered, but I'm just going to quickly recap. It's got a large surface area to maximize water and mineral absorption. So we explained this before, that all this surface here is used for osmosis and for active transport. Now, if it was just a cube shape, if it was just a rectangular shape or cuboid shape, then it wouldn't have as much of a shape. So it's this additional part here that increases the surface area. It contains, for active transport, lots and lots of mitochondria, and it's got a thin wall so that there's a short diffusion pathway. So cells are uniquely adapted to carry out specific functions. So this is now really important, xylem. There are multiple questions that come up. It is quite a common question where xylem gets compared to phloem, or just 2 or 3 mark questions on xylem. So it forms a hollow tube to facilitate the easy movement of water. So this is again something we covered, but we'll cover again really quickly. It's got this spirals of lignin, and that helps provide support and withstand water pressure. And it has no cytoplasm or organelles to ensure an uninterrupted flow of water. So it's important to understand xylem in the context of transpiration. Then phloem has a reduced internal structure to create more space for transporting sugars. It contains sieve plates that allow water carrying dissolved sugars to flow smoothly, and it's supported by companion cells which provide energy and essential nutrients to keep them functioning. Okay, now I'm just going to explain transpiration before we move on to the last slide. Now, in transpiration, if that is the stem and these are the roots, and we've got our leaves at the top, then what will happen? Yes, we can say the sucrose moves from the source to sink. Yes, that's in phloem cells. Yeah, that's absolutely right. So now we've got lots of water here. Now, initially, and we can understand this from 2 different perspectives. So let's look at it from both perspectives. Now, the water will evaporate from the top. So the water evaporates out. So now what we've got, and I'm just going to show it with the highlighter, is this region has reduced in water. So which means that's because the water is evaporated. So that means now we've got more water here. So what's that water going to do? It's going to move from where there's lots of water to where there's less water. And now the water that's below that is also going to move into the space where there's less water. The water below that is going to move upwards. The water below that's going to move upwards. The water below that's going to move upwards. So now we're going to have less water in the roots, so the water is going to enter the roots. So there's a constant flow of water through the stem. But it all starts from the fact that the water evaporates here. Now another way of understanding it is also from a pressure perspective. Now, if I put a straw in a glass of water, and that's a really big straw. Now, when a person tries to drink from the straw, initially what they do is they suck all the air out. And by sucking all the air out, what have they done? They've created almost like a vacuum. They've created an empty space. And by creating an empty space, which way is the water now going to go? By an empty space, another way of saying empty space is low pressure. So now we've got a space that's low pressure, or you could say low water concentration as well. But I'm going to explain it from a pressure perspective. So it's a low pressure. That means the water goes from where there's lots of water or higher pressure and enters that empty space. And that's what's happening in the stem. That's transpiration. That's the movement of water. Now, between each water molecule as well, you have a weak intermolecular bond. And so when one water molecule gets pulled up, in a sense, it helps pull the rest of the water molecules up as well. So that's why if you have a glass of water and you put water right to the top, you see this kind of skin of the water where it's above the line. That's because of the weak intermolecular bonds between the water molecules holding it together. So if you think of medieval chainmail, cohesion tension, If you think of medieval chainmail, where you've got all these links between the metal chains, when it's all on the floor and you grab hold of part of it and you start pulling it up, the bits, because they're all connected to each other, it pulls up all the links underneath as well. And that's partly what's happening. So when the water starts moving, it's essentially pulling up the water below. So you need to understand this, that in one respect it's osmosis, it's water going from a region of high concentration to a region of low. But another way of looking at it is from a pressure perspective, going from high pressure to low pressure. But all of it starts because these leaves, the water's evaporating out. Now, if the water evaporates out at a faster speed, then the movement of water, the transpiration will be faster. And that's what we're going to look at on the final slide of this topic. So at a higher temperature, as the rate of temperature increases, the rate of transpiration also increases because water evaporates more quickly. So exactly what I was saying before, if the water evaporates out more quickly, that means the water underneath is going to move into that empty space. The water below that's going to move into empty space. And that transpiration stream is going to start occurring at a faster speed. So that means transpiration will also happen quicker. Now, increased wind intensity. What that means is, if we've got water particles in here, and we've got less water particle on the outside, then the gas will diffuse out. So because at that point it's a gas, it diffuses out. And that means we have an increase in water particles. At a certain point, diffusion is going to slow down because of how much water is outside. But now if a gust of wind comes and blows away most of those water particles, what have we done? We've created a diffusion gradient. So even more particles will diffuse out. So stronger winds speed up transpiration. So that means by removing water vapor from around the leaf, that means even more evaporation is going to occur. High humidity. Humidity means the amount of water in the air. Yep, thank you, Akshat, that's correct. So high humidity, when humidity is high, transpiration slows down since the air already has high moisture content, and that reduces evaporation. So we've now because it's humid, you've got more water particles on the outside, which means there's a higher concentration on the outside than inside, so less water molecules are going to evaporate out. You get less diffusion. And finally, greater light intensity. More light increases the rate of transpiration because it causes stomata to open. So on bright days, the stomata are more likely to be open. Okay, excellent. I'm just going to very quickly change the presentations. So I'm going to move to topic 3 now. Now, if I can just get an understanding from the group, because there is around 15-20 students that have been on every single day. So I'm going to consider you guys my core group. And then I know there's a lot of students that are watching their own time. So at the moment, yesterday's video, I think we've had nearly 500 views. And again, I really appreciate those people who've been spreading the message. And those people that are taking benefit, liking our videos and sharing them. Because we have really been surprised. When we initially did this, we thought if 10, 15 people watch, 20 people watch, at least it's a start. So we really weren't expecting 500 to 1,000 people to watch the full AMALathon. So we really appreciate those people that have been sharing. Now, because you're the core group, I'm going to go with whatever you guys want me to work with. So I don't think I'm going to finish this topic 3 in time. And there's a triple element that comes towards the end on monoclonal antibodies. So if we don't finish topic 3 in the next 20 minutes, which we're not going to, is everyone happy to log in at 9 a.m. tomorrow? If you are able to, brilliant. Okay. Those that can't, it's not a problem. It'll be recorded. It just means we'll be able to, I'll get up to whatever I get up to, and then we'll finish. And yes, so wherever I can go through exam questions, I'll go through exam questions. I'll spend a bit more time on it. And we'll start using some of that morning time. Okay, 3.1.1. Communicable disease. So, as we've already said, communicable diseases are the ones that spread from one person to another, and they're caused by pathogens. Now, whenever this comes up as a question, both elements are important. Both aspects of this are important because you have to be able to say that communicable disease is one that passes from person to person. Also, you have to mention the fact that it's caused by a pathogen. And sometimes you might get a question on what is a pathogen, and that it's a microorganism that causes an infectious disease or a disease-causing pathogen. So what are communicable diseases? So examples are the flu, caused by a virus, tuberculosis, caused by bacteria, athlete's foot, caused by fungus, malaria, which is caused by a protist, but it's spread by a vector, by mosquitoes. Now, these can be treated and managed through vaccinations, good hygiene practices, or the use of antibiotics and antivirals. Antivirals not being as good, but antibiotics being specific for bacteria. Again, that's a very common 1-mark question. Why can we not use antibiotics to destroy a flu or to treat? If someone's got a flu, why can they not take antibiotics? Because antibiotics only kill bacteria. So, communicable diseases spread through various transmission methods. They can spread through droplet transmission, which is when a person coughs or sneezes or while they're talking, etc. Airborne transmission, which is the same as droplet transmission. It's when someone coughs or sneezes. Waterborne transmission, so there are certain illnesses like cholera that are spread through the water, and that usually occurs more in countries where there's an issue in the sewage system. So if there's an issue in the sewage system, what happens when there's an issue in the sewage? So we've got our water pipes and our sewage pipes. Whenever there's an issue where the two things combine, then you can end up with some of the kind of fecal matter or pathogens that are in the sewage, and that can enter the normal drinking water. So then things like cholera, etc., spread. So when cholera was a really big problem in the UK, we're talking the 1800s, it's because what they found was that the sewage system and the drinking water were mixing. Then there's direct contact, which is things like athlete's foot and HIV. So that can be the sharing of bodily fluids. Now, that's a separate transmission as well. So things like HIV is through, which is direct contact, but that is a sexually transmitted infection. Then we've got vector transmission, where something's passed on by an animal. So, for example, malaria is passed on by mosquitoes. Lyme disease is passed on by ticks, and then foodborne. So you've got things like salmonella and E. coli infections. That's in undercooked food or contaminated food. So how can we prevent that? Good hygiene practices. So that's hand washing. So again, if you go back just 100, 200 years, one of the issues that was occurring was that doctors weren't washing their hands when they went from patient to patient because there wasn't an understanding of microorganisms. So a doctor would have a bloody overall, would go to one person, they'd do the operation, do whatever they need to do, then they pass on to the next person, and whatever was on their hands, etc., it wasn't really washed off till the end of the day. So they were just passing germs from person to person to person. Even if you go back 20 years, 30 years ago, in hospitals around the world, what they found was there was a version of Staphylococcus aureus, which is a bacterial infection. Was spreading in hospitals that was resistant to a really strong antibiotic called methicillin, so MRSA. So that was spreading in the hospitals quite fast. And what they realized in the end was that it was spreading through people's shirts and people's ties. Because people wash their shirts, they wash their clothes, but doctors weren't washing their ties on a regular basis. Even if you think of yourself, if you wear a tie to school, how often do you wash your tie compared to how often the amount of times, how often you wash other things. Even your blazer, how often do you wash your blazer compared to other things? So if you imagine if you're a doctor who wears the same blazer every single day, the same tie, and it gets dry cleaned once a month, or it's not washed very often, then the germs are just gathering on there and they were passing it from patient to patient. Now, vaccination is vaccines stimulate the immune system to develop immunity against specific diseases. That's going to come up and we'll go through in a bit more detail. Safe food and water practices. So in countries where there is issue with water, it's just boiling it first and it's cooking meat and chicken properly, particularly chicken. Then vector control. So areas where there's issues with mosquitoes and malaria, it's using insect repellents, mosquito nets. So sleeping with a mosquito net stops mosquitoes from coming in. Mosquitoes reproduce they give birth to their offspring, which is a tiny little egg, in stagnant water. So removing stagnant water means you're reducing breeding grounds for mosquitoes. So if you control malaria and dengue by reducing mosquito breeding sites. Dengue you don't need to know about, it's malaria that you need to know about. Isolation and quarantine. So anyone that has got an illness, so this goes back to COVID-19, is people who are ill just isolating themselves for a bit or quarantining so it doesn't pass on. And the use of antimicrobial agents. So disinfectants, antiseptics, antibiotics. Yes, coronary disease is in combined. So using disinfectants, antiseptics, and antibiotics help kill or inhibit the growth of pathogens. So how bacteria and viruses actually make us feel ill. So bacteria releases toxins, poisons, that damage the tissues and cells, causing symptoms like fever, pain, and swelling. So what these toxins actually do is they attach themselves to our cells. So you know how we have specificity in proteins? This toxin has a specificity towards our cells. So it attaches to our cells and it stops our cells working properly. For example, salmonella bacteria produce toxins that cause food poisoning, symptoms like vomiting and diarrhea. Now what viruses do is slightly different. They invade the host cells. They take over the machinery and multiply inside them. And that leads to cell damage or destruction, causing illness. So when we do protein synthesis in a bit more detail, this will make a bit more sense. But essentially, our ribosome, when we have DNA, so I'm aware some of you are not doing triple award, but still this helps add context. So we have our DNA within the nucleus. Now that DNA is too big to fit through the nuclear membrane and go to the ribosome. So let's say I'm going to put the ribosome over here. That DNA is not going to be able to leave the nucleus. It's too big. So what happens instead? So let me start again. So we've got our nucleus. The whole page is a cell, but that's just a nucleus. We've got the DNA. The DNA is not going to fit through the gaps, the nuclear membrane. So what happens is the mRNA, a copy is made, which is a single strand. That single strand then goes to the ribosome. And then the ribosome, there's something called a tRNA, which takes, for every 3 bases, it codes it as an amino acid. So for every 3 bases, the tRNA releases an amino acid, and then the amino acids join to each other to make a protein. Now that single strand of mRNA, which I just mentioned, viruses inject our cells with that single strand of mRNA. But it's a viral mRNA. And what that mRNA does is it attaches itself to our ribosome, and our ribosome and the tRNA start to make a protein. And when that protein is made, what is that protein? It's a virus. So our cells start to make the virus for the virus. So it hijacks our machinery. So for example, the influenza virus infects respiratory cells, leading to flu symptoms such as cough, fever, and fatigue. So, exam style question. So Akshat, just for you, I'm not going to skip any more questions. So, explain how bacteria and viruses cause illness in the human body. So essentially, what we do is, so it's a format question. It says explain how. So what we're going to do is we're describing and we're saying why. So bacteria causes illness by releasing toxins. That's what it does. So that's a description. And what does that lead to? Why does it do that? So that the cells are damaged and the tissues are damaged. These toxins then lead to symptoms like fever, pain, and diarrhea. So why is that? Why does why is that? Why is that? Why does the bacteria release toxins? So it damages the cells and tissues, and then that can lead to pain, fever, and diarrhea. Now, reality is that that first bit there would get you 2 marks, but it's always good to add that little bit extra info, as long as it's linked. Viruses cause illnesses by invading and multiplying inside host cells. Now, eventually, when our body starts to make lots and lots of viruses, so our own cells start to make lots of viruses inside there. Eventually, our ribosomes make so many viruses that the cell bursts, and then those viruses then each one goes to an individual cell. So that destroys the cell, leading to symptoms such as fever, cough, and fatigue. So, viral disease, mention a definition of measles. So measles is a highly contagious viral infection caused by the measles virus. It mainly affects children but can occur at any age. The virus spreads rapidly and can lead to severe complications if not managed properly. Now, the next few slides, it's going to give you the symptoms, how it's spread, and how it can be controlled. And what I would advise is go through past paper practice with these slides open, and what you'll start to see is what parts of these slides come up over and over again. Or even with your revision guide open, or whatever you're using for revision. So, high fever is due to, and how are measles spread? Because of direct contact. So here's the symptoms of measles: high fever, red skin, rash, usually starts on the face and spreads. Now, how is it spread? Through direct contact, and it's highly infectious. So the virus can remain in the air and on surfaces for hours. And controlling either isolation, so infected individuals should be isolated to prevent spreading of the virus, and also public awareness, educating people about the symptoms and importance of vaccination. Because there was a time where no one was vaccinated, so hundreds of thousands of people were dying all the time. Then vaccinations were made, and then we went down to hundreds and just tens of people dying. But then what people started to think is that the people are actually dying because of vaccinations. In fact, the 10 or 20 people a year that die from measles at that point, a lot of them were because of the vaccination. Now, we'd gone from hundreds of thousands of people dying to just tens of people dying, but the tens of people dying from vaccination was blown out of proportion, so then people stopped vaccinating the children. And now there's been another increase in things like measles, mumps and rubella because less people have had the vaccination. So public awareness is very important. Okay, HIV is a sexually transmitted infection. So the symptoms are, in fact, there's no symptoms for years in some cases because the HIV can initially lay dormant. But what HIV does, and this will come in a bit, is that it weakens, or it says it here, it weakens the immune system, so it attacks the white blood cells. And because it's attacking the white blood cells, it's weakening our immune system, so we lose our ability to defend ourselves. And once it gets to an advanced stage, it's called AIDS. That's the point where the immune system has been compromised, it's been destroyed pretty much. At that point, a person can die from just a cold, a flu, pneumonia, whatever they catch. The body doesn't have the ability to defend itself against it anymore. How is it spread? The main ones are unprotected sex. However, particularly in the 80s, what was happening was when someone needed a blood transfusion, there was a big drive. I think this happened more in America than it did in the UK, but it did happen in the UK also. There was a big drive to get people to donate blood. So as they donated blood, what they weren't doing was checking it. So they didn't screen the blood to see if it had infections. So when someone suddenly needed a blood transfusion, they gave the blood transfusion, but then they passed on AIDS. So there's lots of people, I would say thousands, it's a rare thing that occurred. And after they found out what they were doing wrong, it didn't happen again. But infected blood transfusion, so they had a blood transfusion that was infected and they got AIDS because of it. And prevention and control, HIV testing for early detection, antiretroviral therapy. So this is a specific therapy that attacks viruses. Now this antiretroviral therapy is really good, and it slows down the spread of HIV. So where someone may have passed away from HIV really quickly, now they can live a relatively long life. So it takes 20-30 years longer for the HIV to spread. And it's important for education and awareness to prevent spread. Okay, we're going to stop there and we're going to take a 5-minute break, and then we'll come back to chemistry. Now, our next chemistry topic is a little bit, well, I don't think it will take the full hour. So if we do have additional time, it might mean that we'll be moving on to chemistry topic 4. That's fine. So we'll have a quick break. We'll restart at 5 minutes past 11. Right, thank you everyone. See you in 4 or 5 minutes. Welcome back, everyone. So now we're going to move on to the second part of our session, which is our AQA AMALathon Day 4. Session 2 is chemistry. So what we're going to be going through now is chemistry topic 3. So if we look through this, we have completed atomic structure, we've completed periodic table, we've completed bonding, structure and properties of matter, and we now are on quantitative chemistry. So hopefully we'll be able to finish quantitative chemistry and then we'll move on to the beginning of chemical changes. So what I want to try and cover today, but we'll have time tomorrow as well, is the acid and alkali part of chemical changes. So thank you for your questions. We've had some really good questions. Concept puzzle, someone from our team will contact you. That's got less to do with myself, it's more to do with the technical team. But thank you for your questions. So, conservation of mass. So conservation of mass, hydrogen plus oxygen becomes water. So what we're saying here is 2H2, we have got, in fact, before we move on, let's just clarify a couple of things. If I write down here H2, then what do I mean? I mean hydrogen with a covalent bond with another hydrogen. If we say O2, we mean oxygen. Now oxygen is in group 6, and because oxygen is in group 6, it needs 2 more electrons, so it shares 2 electrons. So both oxygens share 2 electrons, that's 4 electrons shared, that's 2 covalent bonds, and then that makes H2O, where we've got oxygen molecule. Sorry, I've done this. We've got H2O. Now H2 means we've got 2 hydrogens and 1 oxygen. So we've got oxygen and we've got 2 covalent bonds coming from the oxygen to our hydrogen. Now the second we say 2H2, what's the difference? The difference is, it means we've got 2 of them. We've got 2 molecules that are exactly the same. And here we've got 2H2O. What does that mean? It means we've got another one of these. So that's the first thing that needs to be clarified. Now, if we look on the left-hand side here, we have got 4 hydrogens. Let's just do a quick count. I'm sure a lot of people so we've got 1, 2, 3 and 4 hydrogens. Now let's look on the other side. We've got 1, 2, 3 and 4. What that means is the hydrogen has been conserved. And here we've got 1 oxygen, 2nd oxygen. And on the right hand side, on our products, we have 1 and 2 oxygens as well. So that's what we mean by conservation of mass. That whatever we have in our reactants, we have to have the same amount of atoms of each thing in our products. So it has to be conserved. So symbol equations should be balanced in terms of the numbers of atoms of each element involved on both sides of the equation. So we should end up with the same amount of atoms on both sides. Okay, now I've already explained the difference between the large number at the front, which is a multiplier, and the subscript, which tells you about the individual atom. So this 2 here, the big 2, is the multiplier, and the small 2 is specific to that individual individual atom, the individual element. So that small 2 is individual to that one element. So that means we've got 2 hydrogens. But the big 2 means we've got 2 of that full molecule H2O. Okay, relative formula mass. So what relative formula mass means is, if you look at the periodic table, let's quickly look at H2O. On the periodic table, hydrogen's mass number is 1. Oxygen on the periodic table's mass number is 16. H2O is made up of 2 hydrogens and 1 oxygen. So 1 has a mass number of 1, oxygen has a mass number of 16. All relative formula mass means is just adding up all of the mass numbers. So in this case it's 1 plus 1 plus 16. So the relative formula mass of H2O is 18. Now if it says MR, then that's the relative formula mass of a molecule, for example H2O. If it says AR, then that's talking about an individual atom. That's talking about an individual atom. So for example, just H2, or relative atomic mass of just O2, oxygen. Akshat, can you please go through electric field questions and content again, please? I don't fully... Yep, I can do. Tomorrow we're going through topic 3, biology. But I'll make a note, and if there's time, but it does depend on time, because there's a really good question that was asked as well, which I need to answer from yesterday. That was asked by Karuba. So after I've gone through topic 3, I've answered Karuba's question. If there's time, I will go through electric field again. And if I can't go through it tomorrow, I'll try to go through it on Thursday. So that's not a problem. Let's make a quick note of that. Yeah, that's absolutely fine. I can do that. Now, let's quickly look at this now. If you look at carbon dioxide is carbon, oxygen, and oxygen. So carbon has a mass number of 12, oxygen is 16, and 16, so 12. So that looks like I've written cod instead of coup. 12 plus 16 equals 44. So the relative formula mass is 44. We've done H2 already. Now let's look at MgOH2. So now if you look at MgOH2, what does that actually mean? It means Mg, and it's attached to one hydroxide, and it's attached to a second hydroxide. So what we're actually adding up here is magnesium has a mass number of 24. We know oxygen and hydrogen are 16 and 1. So what we're doing here is 24 plus, now OH altogether is 16 plus 1, 17. And we've got 2 of them, so another 17. And if we add that up, we end up with 58. Now, the way they've added up here is they've added up magnesium, they've added up 2 oxygens, and they've added up 2 hydrogens. So that's why you've got 32 and 2 separately. Well, we've added OH together, so 17 plus 17. So mass changes when gas is made. Now, here, because it's an open system, it means the gas will diffuse away. So in this open system, this might be a solid reacting with an acid, so the hydrogen gas has diffused away, and then the mass has decreased. What this actually does is, it says, from the product, there's 16.82 grams left, and when you do 17.32, take away 16.82, that tells us that there's 0.5 grams of hydrogen gas that's been lost. So it shows us so it shows how much gas has been dissipated. So some reactions may appear to change in mass, but this can be explained. A reactant or product is often a gas, and its mass is not always measured. So if a gas is produced and escapes into the air, the total mass seems to decrease. This does not mean mass is lost, it's just contained within the system. So whenever measurement is made, there's always some uncertainty about the result obtained. Now, by uncertainty, it means identify the highest and lowest values in your set of results and calculate the range. And divide the range by 2. So that gives you an uncertainty. So identify the highest and lowest values in your set of results, work out the range, and then divide that by 2. And that gives you your uncertainty. Okay, moles. A measure of the amount of substance. Now, when we say measure amount of substance, let's ignore the relative formula mass bit for a second. Moles are a measure of the amount of substance. Now, what scientists calculate is that in 1 mole of substance, actually the best way to explain this is different. Sorry, if you give me just 1 second, let me get rid of this. Now let's look at carbon 12. What they found is if you have 12 grams of carbon, in 12 grams of carbon, you have got 6.02 times 10 to the power of 23 atoms of carbon in 12 grams. Now, remember, actually it's not showing it here, but when you calculate moles equals mass divided by the MR. Now, in this case, what's our mass? 12. What's our MR? It's also 12. So that means our moles our number of moles is 1. So what that means is in 1 mole, how many atoms of carbon do we have? 6.02 times 10 to the power 23. So let me just repeat that. The MR of carbon is 12. In 12 grams, we have 6.02 times 10 to the power 23. When you do mass, which is 12, divided by the MR, which is 12, we get 1 mole. So 1 mole has 6.02 times 10 to the power 23 atoms or molecules of something. So if I said I've got 1 mole of carbon dioxide, it means I've got 6.02 times 10 to the power 23 carbon dioxide molecules. If I say I've got 2 moles of carbon dioxide, it means I've got 2 times this number. If I say I've got 0.04 moles of something, then I've got 0.04 times 6.02 times 10 to the power 23 of that particular molecule. If I say I've got 1 mole of pens, I've got 6.02 times 10 to the power 23 pens. If I say I've got 3 moles of pens, I have got 3 times that number of pens. So that's the thing that needs to be kept in mind, because sometimes what you get is questions that ask you to calculate the number of moles. Then after that they say, well, how many atoms of that substance is there? Or they might not ask you to calculate moles, but they'll give you the information to calculate moles and say, work out the number of atoms or molecules. So, amounts of substances. Using balanced equations, magnesium plus hydrochloric acid becomes magnesium chloride plus hydrogen. So magnesium plus hydrochloric acid becomes magnesium chloride plus hydrogen. So what we're saying here is that 1 mole of magnesium reacts with 2 moles of hydrochloric acid, and that produces equations of moles. But one thing to keep in mind here, particularly for those doing higher and for those doing triple, is that if I said, let's just look at magnesium and hydrochloric acid really quickly. I've got magnesium and I've got 2 HCl. If I said I've got 3 moles of magnesium, then how many moles of HCl do I need to react with it? I need twice as many, because 1 mole of magnesium reacts with 2 moles of HCl. 1 reacts with 2. So if I've got 3, then I need 6. If I've got 8 moles of HCl, then how many moles of magnesium do I need? 4 moles. So these numbers that come before it help us to understand. If we can work out the moles of 1, we can, with the ratios, we can work out the moles of everything else. So if I'm using 3 moles of magnesium, I'm going to make 3 moles of magnesium chloride and 3 moles of hydrogen, because they're all one. They all have a ratio of 1 to 1 to 1. But in terms of with HCl, it's a ratio of 1 to 2. So I always need twice as many moles of HCl. Sulfur dioxide pollution is reduced by reacting calcium oxide with sulfur dioxide to produce calcium sulfate. So this is the kind of question that would put a lot of people off. So this should say sulfite, apologies, not sulfate, because it's SO3. So here we've got, the question is, we've got 7 grams of calcium oxide and it reacts with an excess of sulfur dioxide. Now there's different ways that you might have been shown how to do this in school, so you just need to use whatever works for you. So the relative atomic masses of oxygen, sulfur and calcium are here. Now the first thing you've got to do is calculate the mass of calcium. What we're doing is we need to calculate the mass of calcium sulfate produced. So that's the question. We need to work out how much from, if we've got 7 grams of calcium oxide, then how much calcium sulfate will be produced. So we know our MR, 56 calcium oxide and 120 calcium sulfite. So because we know the information of calcium oxide, we look at calcium oxide first. So moles equal the mass divided by the MR. So that's what we're doing here. We know the mass is 7 and we're dividing by 56 the MR. And then we multiply by the MR of the substance we're trying to find the mass of. So that's why we're multiplying by 120. And that gives us 15. Now, if that works for you, then stick to this. If anyone says to me that they've learned, if you've done it a different way in school, that's absolutely fine. What I always personally do is slightly different. So I'm just going to show you how I would do it. But this way is shorter and easier. So if this works for you, stick with this way. But just personally, what I do with any of these kinds of questions is I draw a table. We've got calcium oxide, we've got calcium sulfite, and I put all my information in. So mass, MR, number of moles. So we know the mass of calcium oxide is 7. We're trying to find out the mass of calcium sulfite. The MR of calcium oxide is 56. And we know the other one is 120. So in the end, I end up doing the same calculations, but it just makes things clear. So I do 7 divided by 56, find out the number of moles. Now, because this is a 1-to-1 ratio, one of these reacts to make one of these. Whatever the number of moles are initially, that's going to be the number of moles here as well. So that's 1/8, 0.125. And then to work out mass equals Mr. Mole, so MR times the number of moles. So 0.125 times 120, and then that gives us 15. So whatever method works for you, use the method that works. So how do we calculate moles from a chemical reaction? So here we've got propane plus oxygen. So you can actually use moles to balance an equation. So what you would do is you work out the number of moles of each one. So remember the number of moles equals mass divided by MR. So we know right now, propane, we've got mass of 88. And propane has a relative formula mass, has an MR of 44. So with propane, what's 88 divided by 44? It's 2. So that means we've got 2 moles of propane. Then with oxygen, the MR of oxygen is 32. So again, mass divided by MR. So oxygen will be 320 divided by 32. So we'll have 10 moles of oxygen. Let's look at carbon dioxide. It's 44. 264 divided by 44 is, I think, 6. So we'll have 6 moles of carbon dioxide. And H2O is 18. So 144 divided by 18, which I think is 8. So we'll have 8 moles of water. So now we can work out the moles. So this is what is showing on this slide, what I just went through on the previous slide. 88 divided by 44 is 2 moles. 320 divided by 32 is 10 moles. 264 divided by 44 is 6 moles. And 144 divided by 18 is 8 moles. Now all we've got to is put this into the simplest ratio. So we can divide all those numbers by 2. So we've got 1 mole of C3H8. So we don't need to actually write a 1 before there because there's already 1. We've got 5 moles of oxygen, so we'd add a 5 here. We've got 3 moles of carbon dioxide, so we'd put a 3 here. And we've got 4 moles of water, so then we'd put a 4 here. It's very rare to get a question like this. It's more likely that you just be asked to balance it. And you would not have time to do this level of balancing in a question. But the main thing here is that you know how to work out the number of moles. Okay, limiting reactants. In a chemical reaction with 2 reactants, we often add extra of one reactant. This ensures the other reactant is completely used up. The reactant that is used up first is called the limiting reactant because it controls how much product is made. So in a sense, for example, we get a spatula and we have an acid, we add our reactant. So we add our solid, we add a metal, powdered metal oxide, for example, and it will dissolve. Then we add another spatula of it and it dissolves, it disappears. Then we add another spatula, it dissolves, it disappears until we get to a point where all the acid has been used up and we see a build-up of the powder, the solid that we've been adding. So let's have a go at a question that's linked to this. Now, if anyone is unsure about the specification, what I would advise is if you go to the AQA website, you can access all the specifications there, and that shows you what's combined. It shows you what is separate science as well. It could be that some topics are covered in less detail or more detail at school, so there's no harm in having a look at it. That way you can get a good understanding yourself as well. Now, a mixture contains 1 kilogram of aluminium and 3 kilograms of iron oxide. So what we're going to do now, that's the equation for the reaction. We're going to show that aluminium is the limiting reactant. So we know the relative atomic masses, that's given to us in the question as well. So this is the main part of the question. Step 1, we're going to find out the MR of Fe2O3. So it's got 2 ions, so that's 56 times 2, plus 3 oxygens, which is 16 times 3, which is 160. So now we can work out the number of moles of Fe2O3. Now we've got 3 kilograms, so we're going to multiply that by 1,000, so that we have 3,000 grams. And like we've already said, moles equals mass divided by MR. So 3,000 divided by 160 equals 18.75 moles. Now, if you look here, 2 aluminiums react to make 1 Fe2O3. So it's a 2-to-1 ratio. So what that means is if we've got 18.75 moles of Fe2O3, we need twice as many moles of aluminium. So we need 37.5. Now, if we work out the number of moles of aluminium, again, we've got 1 kilogram. So that's 1,000 grams. So we're going to do 1,000 divided by the MR, which is 27. That's 37.4. Now, if we look at Fe2O3, based on Fe2O3's number of moles, we need 37.5 moles of aluminium. So 18.75 moles of Fe2O3 needs 37.5 moles of aluminium. In this case, we don't have 37.5, so that means aluminium is the limiting reactant. So again, I would advise to try as many of these kind of questions as possible. Now, concentration is the amount of mass within a certain volume. So it's mass divided by volume. You can get questions which are the number of moles divided by volume as well, but that usually comes in separate science. So many chemical reactions happen in solutions. The concentration of a solution tells us how much of a substance is dissolved in a certain volume of liquid. So it is measured in grams per cubic decimeter. The formula to calculate concentration is concentration equals mass divided by volume. Now, some questions that you might get on this, for example, is let's say you have 100 you've got this concentration, 200 grams per decimeter cubed, but you're only using 100 centimeters cubed of it. So the volume you're using from this concentration is just 100 centimeters cubed. So what will be the mass? So what will be the mass that is used? So what you do here is, to work out the mass, you do concentration times the volume. Now volume has to be in decimeters, so we divide that by 1000 and it equals 0.1. So our concentration is 200. We times that by 0.1, and that means the mass is 20 grams. That means whatever the substance was, we've got 20 grams of it in 100 centimeters cubed. And the remainder of this is triple. So what we covered this morning. So for those that attended the triple session at 9 a.m, thank you for attending this morning. That's all. This bit's already been covered. So now I'm just going to get up topic 4. And then we'll continue. Okay, so this does put us a little bit ahead of schedule from a chemistry perspective, and also just want to say thank you for everyone that has been asking questions. Thank you, Akshat, for your questions. I will go through them tomorrow, wherever I'm able to, and I will clarify for you. As far as I'm aware, everything I'm covering is on the specification. It is content that I cover, so I would advise you have a look at the specification. The main thing you need to understand from the electric field questions is that within the actual dome where the electric field is created, you don't end up with a charge because you've got air particles. And the main kind of question that come up linked to that is drawing the electric fields, where if it's positive, the electric fields go lines going outwards, and when it's negative, then the lines are coming inwards. Beyond that, I've never really seen too many questions, so I would advise having a look at some past papers. That is if you're doing triple award, so that is specifically a triple award topic. I'm assuming you are because you were here for the triple award section. But overall, it's not a topic that's you're going to get too many questions on. Okay, metal oxides. So we're going to carry on now till 11:55, take a 5-minute break, and then we will start physics. So what is oxidation and reduction in terms of metal, of a metal that's been oxidized? So metal plus oxygen makes metal oxide, copper plus oxygen makes copper oxide. So 2 copper plus oxygen makes 2 copper plus, so 2 copper oxides. That's the balance. So oxidation is gain of oxygen. So when we're saying 4.1.1, 4.1.1 is not referring to redox initially. It is talking about redox from its oxidation reduction perspective, but it's not talking from an electron perspective. The initial understanding that you have to have of redox is gain and loss of electrons. So oxidation is gain of electrons. Reduction is loss of electrons. Loss of oxygen, sorry. Gain of oxygen, loss of oxygen. So here, the copper has gained oxygen, so it's been oxidized. Now this might be a good opportunity before we continue, because we do have a little bit extra time, that I really quickly go through redox as well from an electron perspective. So even though it's a gain of oxygen, oxidation is, and I'm assuming everyone's come across this term before, oil rig. Oxidation is loss of electrons. So oxidation is loss of electrons, and reduction is gain of electrons. So if we have a quick look at this reaction here between copper oxide and oxygen, let's work out what has been oxidized and what has been reduced. And we'll have a quick practice on writing half equations, because that's one of the topics that some students struggle with. So let's look at each one individually. Copper is an element, and because copper is an element, it has an overall charge of 0. It hasn't gained or lost electrons. Oxygen, on the other hand, has an overall charge of 0. And then if we look at the other side, copper oxide, oxygen's from group 6, so when it becomes an ionic compound like this, it has a charge of 2-, and copper has a charge of, therefore has a charge of 2+. If oxygen is 2-, then copper automatically becomes 2+. So let's look at each one. What's happened to copper? Copper has gone from just being copper to becoming copper 2+. So what has copper done to become copper 2+? It has lost 2 electrons. So we can, on the left hand side, write -2 electrons. But if you look at it from an algebra perspective, if we move that to the other side, it becomes +2 electrons. So usually we put +2 electrons on this side. In other words, it has lost 2 electrons, so it has been oxidized. Now if we look at the oxygen, it has an overall charge of 0, and then it becomes, and I'm going to write there's 2 of them, it's from O2-. So what's happened? It has gained electrons. Now because there's 2 of them, it's actually gained 4 electrons. So that means it has been reduced because it has gained electrons. Okay, now when this comes up as a topic, I'll go through it in more detail again, but I just want to have a quick look at it now. So that means copper has lost electrons, so that's been oxidized, and the oxygen has gained electrons, so it has been reduced. So we call it redox. Okay, reactivity series. So when metals react, they lose electrons to form positive ions. How easily a metal forms positive ions determines how reactive it is. Metals can be ranked by how reactive they are in what's called a reactivity series. Carbon and hydrogen though non-metals, are often shown in the series for comparison. So all this is like a league table. The most reactive ones at the top, the least reactive ones at the bottom. And now a common question I get is, how do you know? How do you know, in terms of reactivity, what's at the top and what's at the bottom? So the best way to remember this is, look at what group they're in. So potassium is in group 1, sodium's in group 1, lithium's in group 1, calcium's in group 2, magnesium's in group 2, aluminium's in group 3, then we've got carbon. Then we've got zinc, iron, tin and lead, which are all transition metals. And then we've got hydrogen. Then we've got copper, silver, gold. Now, silver and gold and platinum are the kind of metals that are found in the ground unreacted, as in they're found pure. Everything else has to be purified with reaction with carbon. So if anything is below carbon, then we reduce with carbon. We react it with carbon, and then carbon, because it's more reactive, takes away the oxygen. If something is more reactive than carbon, then we have to use electrolysis. So what is oxygen? So metal to 50 centimeters cubed of dilute acid, then you stir the mixture gently. You record the highest temperature reached. Repeat the experiment using water instead of acid, and then you try the experiment with different metals, and then you compare the temperature changes. So it's a really simple experiment to show which one is most reactive. Now, this is not the only observation that you have to take down. Temperature is probably the most accurate one, because you will get temperature changes. So a more reactive metal will have a bigger temperature change. A less reactive metal will have a lower energy change. However, if you can also look at your observations, how many bubbles, how much effervescence there is, how quickly the solid disappears. There's lots of different things you can look at to see if it's more reactive or less reactive. Now, usually when questions come up like this, it's where you have some information and then where it already says potassium reacts very fast. It's all about the descriptive words. That potassium is explosive, sodium is fizzes and heats. You can feel the heat. Lithium is fast. Calcium, you can see bubbles, but it's less vigorous. So it might say, okay, magnesium less reactive than calcium. What would its reaction be like? Now, no one's expecting you to have memorized everything. It's just using the adjective that shows that it's not as vigorous as the one above. So you say bubbles, but not as vigorous as calcium, or steady reaction. Zinc, slow bubbles, even slower, no reaction. So all you're showing with this is that as you go down the group, the reaction becomes less volatile. It becomes less explosive. There's less effervescence. So, what is a reactive metal? Why can zinc take iron's place in iron sulfate? So a more reactive metal can push out or displace a less reactive metal from its compound. For example, zinc and iron sulfate will become zinc sulfate and iron. So we have kind of covered this already, but let's go through it in more detail now. So this happens because zinc is more reactive than iron. So it takes iron's place in the compound. So what's happening here is the zinc is more reactive than iron, so it pushes the iron out and replaces it. So let's just remove this side for a second, and now iron has been displaced. Now again, and I'm doing this because we've got a little bit of time, and I think it's important that we practice this. Let's look at this from a half equation perspective. So we've got iron and zinc sulfate. So we've got Fe and we've got zinc sulfate, and this becomes iron sulfate plus zinc. So I've written this the wrong way around. So I've written this down in a way where no reaction was going to occur. So we've got zinc plus iron sulfate becomes, so I keep writing this down the wrong way, that displaces the iron, so it becomes zinc sulfate plus iron. Now let's look at this from a half equation perspective. Let's look from a redox perspective. I know redox hasn't come up yet, but it's, like I said, it's one of those topics that's not always well understood. So zinc has an overall charge of 0. Iron, now it's a transition metal, so in theory we don't know. But we know sulfate is 2 minus. That means iron must be 2 plus. And that gives us zinc 2 plus, SO4 2 minus, and iron is an element, so it has a neutral charge. Now, the first thing you do is you get rid of spectator ions. Spectator ions are the ones that haven't changed. So if you look here, that sulfate was SO4 2 minus on that side, and it's SO4 2 minus on this side, so it hasn't changed, so we can ignore that. Now let's look at each one individually. Let's first look at zinc. We've gone from zinc on this side as Zn, and the other side has become Zn2 plus. So what has happened to zinc for it to become 2 plus? It's lost its negativity, so it's lost its electrons. So it's lost 2 electrons. And so we know that zinc has lost electrons. So oil rig, oxidation is loss of electrons, so we know this is oxidation. And let's look at iron. We started with Fe2 plus, and on the product side it's Fe with no charge, so that means it's gained 2 electrons. So that has been reduced. So again, that shows the redox reaction. So now let's have a quick look at this actual question that's here. A student is given 3 metals, X, Y, and Z, to identify. And this is a very common type of question that comes up. And they've been asked to identify the metals are magnesium, iron, and copper. Plan an investigation to identify the 3 metals. By comparing their reactions with dilute hydrochloric acid, your plan should give valid results. So we add the metal to dilute hydrochloric acid, and you measure the temperature change during the reaction. Now that can be done more than once, so you can make sure that there's no invalid results. You can get rid of anomalous data. And from it, plan an investigation, identify by comparing the reactions, and your plan should give valid results as well. So now we've got our plan. Now in the plan, if we're going to make it better, we should be talking about control variables. So we should talk about the fact that we can use the same concentration of acid, the same mass of each metal, even the starting temperature would be a control. The thing that we're changing, our independent variable, is the metal, and what we're measuring, the dependent variable, is the temperature. So in our conclusion, we should know magnesium's from group 2, iron is from the transition metals, and copper is from those metals that aren't very reactive. So we should know that magnesium will give the largest temperature change, and second is iron, that will give a small amount, and copper will show very little temperature change. Okay, we're going to stop there, and we will continue from 4.1.3 tomorrow. Okay, thank you everyone. We're going to have a 5-minute break, and I will see you all at 12 o'clock. Okay, welcome back everyone. Now there was a couple of questions just linked to the specification that I want to clarify before we move on. So coronary heart disease is in the biology AQA spec. It's 4.2.2.4 and electric fields is 4.25.5.2, but this is a separate science topic only. So for electric fields, anyone that's doing separate science physics, you need to be able to draw the electric field pattern for an isolated charge sphere. That means if it's a positive charge, you draw the lines going away, but what you don't do is draw the lines within the sphere. You draw them going from the surface of the sphere outwards, and you make sure that the uniforms have the same gap between each one, the way it was shown in the diagram for those that came up on this morning. And if it's negative, you show the line going inwards. And the second thing, you just have to explain the concept of an electric field. So essentially, with the electric field, if something comes within the electric field, it will, if it's the same charge, it attracts it. If it's the opposite charge, it repels it. In a nutshell, that's predominantly what you need to know. And you need to explain how the concept of an electric field helps to explain the non-contact force between charged objects. So it's talking about the fact that you can, through electrostatic, well, as well as other electrostatic phenomena such as sparking. So you need to, in a sense, understand why lightning occurs or why sparks occur. And we went through that also. Beyond that, I did go into a little bit more detail, but if you didn't understand the extra detail, that was only there to enhance the understanding. So it's not too much of an issue if it didn't make sense. What I've just said now, if that's made sense, that's what's needed. So like I said, I really appreciate the questions that we get. I hope that's clarified it. The slides that we made are linked to the AQA specification purely. So I just wanted to clarify that because there was some questions just kind of along the lines of, we've not really covered it in school, so is it or isn't it? It is. So that would be more of a conversation that you need to have with your teacher. And by that I mean you need to question why your teacher hasn't taught you it. Okay, we're now in our third and final part of our AMALathon day 4. So after this, we've just got 2 days left, and we're going to be doing our best to finish everything off. So like I said, we'll be starting at 9 AM tomorrow with topic 3 biology, and that will be combined and triple. So this, for those that can't make it, it's not a problem. As you know, it's being recorded, and please keep liking, sharing and encouraging people to subscribe so we can get to a point where we're able to do a lot more. I've said this to you guys before, we have a lot of plans in place, including an app which will hopefully come out at some point next year. We'll have the weekly AMAL from next year. Now with the YouTube side of things, we are looking to make things affordable. The app, again, we're looking at affordability, and that's and actually a big part of our goal is to make things affordable, particularly in countries that can't afford the same quality of education. So we want to provide the same quality of education but at a cheaper price. So our first thing that we've done is the AMALathon, and we've made it completely free for that reason. And also we made it free so people can see what we're doing, give us a chance to kind of introduce ourselves. Also, it's a chance for us to have a go and improve as well. This is the first time I've done anything like this. I've done lots and lots of Zoom calls and lots of Zoom type tuition. I teach in a school. I've taught for the last 15 years, but it is the first time I've done something on YouTube, and it is a very different experience. And I'm not someone who can claim to have that special YouTube style voice. But hopefully if I keep practicing, I'll get better. But the main thing is, I'm not here to entertain, I'm here to help you understand. So please keep asking questions. And like I said, I really appreciate those that keep asking questions. They do help. It shows that people are listening on the other side. So if something doesn't make sense, just say it doesn't make sense, and I will try my best to make sense of it. So this topic we are going to finish by the end of the lesson, and that is density of materials. So how do we calculate density? Density is mass divided by volume. Mass is the amount of matter in an object, and it's measured in kilograms. And volume is the amount of space an object takes up in a three-dimensional space, so it's measured in cubic meters. And density is the measure of how much mass is packed into a certain volume. So if we increase the volume, it means we're spreading out the mass, so we have decreased the density. So density is measured in kilograms per meters cubed, mass is measured in kilograms, and volume is measured in meters cubed. Now there's a core practical link to this topic, and it's a core practical that comes up quite often. So again, when you're going through past paper questions, you're going to start to see certain things come up again and again and again. So this is just a quick question. The width of a cube was 18.45 millimeters. The density of the cube was 8 times 10 to the power of 3 kilograms per meters cubed. Calculate the mass of the cube. I'm actually interested to see what people get in this answer. So I am going to, density equals mass divided by volume. I am going to wait just a small amount of time before I start talking through the answer, because I want to see your answers. In fact, I'm going to wait just 1 minute. So the faster typers amongst you can start answering. There is a bit of a time delay between what I'm doing and what you're doing anyway. So I will start talking in about 30 seconds, 45 seconds. Actually, the time delay is only about 10 seconds. No problem. If you don't have a calculator, it's not a problem. But if you're able to answer, have a go. Okay, let's start going through the answer then. If you manage to get it and you're still calculating, that's fine. Just put the answer in as soon as you get it. But I'll start going through the answer because I don't want it to be that we don't end up with enough time. That's correct. First convert millimeters to meters. That's right. Absolutely right. Well done. So the first thing we've got to do is divide by 1,000. So we've got 0.01845 meters. Now it's the cube and we're trying to find the volume. So how do you work out the volume of a cube? We do length times width times height. So that's why we have to cube this number here. 0.01845. We've got to cube it. So 0.01845 times the same number times the same number. So you end up with 6.28 times 10 to the minus 6. Now we're trying to calculate the mass. So mass equals, if we rearrange that formula, the rearrangement's already here, the density times the volume. So now we just multiply our density by the volume, and we've got 0.0502 kilograms. Now, in this question, you would still get the answer correct if you wrote 0.05, because that's 3 significant figures. As long as you've done 1 or 2 significant figures, that's sufficient. 3 is okay too, but generally speaking, 1 or 2 is all that's asked for. Now, where a lot of people go wrong with this question is either they don't convert this to meters. That's one thing. The second is if they don't convert to meters, they forget to cube it. So they forget to cube. So it's one or the other, and then people lose quite a few marks. So this will be a 4-mark question, and if they don't cube it, they'll end up with 1 mark. If they don't convert it, they might still get conversion. They'll most likely still get 3 marks because they're still going to cube it. They're still going to go through the whole process. but that conversion and that cubing part is very, very important. Okay, determine the density of a regularly shaped cube. So density of material, determining the density of a regularly shaped cube. So this is nice and easy. We find out its mass using a mass pan balance, and we work out its volume using a ruler. So if it's a regular shaped cube or a cuboid, you just use a ruler to work out how big the shape is. You measure its, if it's a cube, you're just measuring one side and then cubing it. If it's a cuboid, then you're doing length times width times height or breadth, and length, width and height, and you're calculating it, and done. You've got the mass, you've got the volume, and you've got the density. So when it's a regular shape, it's nice and easy. You just need a ruler, a calculator, and a mass pan balance. Now if you've got something that's got an irregular shape, then that's a little bit different. You can still work out the mass using a mass pan balance, but that shape's going to is impossible to work out the volume of. So what you do instead is you put it into something like this beaker here, which is something we call a eureka can. A eureka can is just a can with a little spout at the side, and you pour water into it so it's just on level with the beginning of the spout, as it is in the diagram that's already there. Then when you pour, so you pour the water level just below the spout, position the empty beaker beneath the spout, and then put inside your irregular shape. And what that does is it causes the water to increase. The same way when we sit in a bath, or when you put your hand in water, you feel the water go up. The amount the water's gone up is your volume. So in this case, the amount of water that's displaced is the volume. So now we have the mass, we have the volume, and we can calculate. So how do we find the volume? We used our measure. We can either use it on the other way, is a measuring cylinder. So if you have a measuring cylinder, we've got water, put in the irregular shape. Again, what's going to happen is the water level is going to increase. The amount it increases by is its volume. So that's another way of doing it. But now we've got the volume, we've got the mass because we use the mass pan balance, and then we just do density divided equals mass divided by volume, and done. We have the density. Now, what are the possible sources of error? Now, sometimes in school, things like uncertainty aren't taught as part of this curriculum, but some teachers will still teach it because they'll have an experience of past paper practice. And in past paper, if you look at past paper exams, when you're answering questions linked to core practicals or required practicals, what you find a lot of the time is questions that are linked to evaluative type questions. What could be done to improve the experiment, or where could the possible errors have come from? Those kind of things. So the how science works type questions. And in AQA, there's a section in each paper on that linked to core practicals. So this kind of stuff is not directly in the curriculum where it says you must learn this. It automatically comes as part of the core practicals. So random error happens when a person makes mistakes while taking measurements. So for example, reading the ruler from the wrong angle. So that's a parallax error that's about to come up. Zero error happens when equipment doesn't start at zero. For example, a balance already shows a number before anything's placed on it, and people don't realize the number's already there. So how do you correct a zero error? If you've got a mass pan balance that just isn't working right, and it's just at 0.12 grams before you start, whatever mass you get, you just take away that error. Now, parallax error happens when you read the scale from the wrong angle. So if you're looking at it from above, you're going to see the line as here. If you're looking at it from below, you're going to see it here. You have to bend down so you're on level with where the water actually is, and then you get an accurate reading. When observing the volume from a lower perspective, the measurement taken will be less than the true volume. When you look at it from above, it will appear greater. Okay, so here's a quick exam practice question. I'm just going to give you 20-30 seconds to have a quick read. Again, if someone's able to answer, I would love to see your answers. So the resolution of the micrometer is 0.01 millimeters. The student could have used a meter ruler to measure the width of the cube. Explain how using a meter ruler would have affected the accuracy of the student's measurement of width. So the meter ruler has a lower resolution, so it's less accurate. So remember, when you're looking at the resolution of something, so let's say the meter ruler is in centimeters. So the distance between one of the lines to the next line is 1 centimeter. So you would half that, meaning the resolution would be half a centimeter. As in, it's give or take half a centimeter whenever you give an answer. And that's its level of accuracy. So this has a 0.01 millimeter resolution, so that is much more accurate. So you wouldn't use a ruler over a micrometer. So what happens to the mass when a substance changes state? When a substance undergoes a change of state, the mass remains constant. The changes of state are classified as physical changes. Now we know it's physical when it can reverse. So if a solid becomes a liquid, or a liquid becomes a gas, it can now go in reverse. The gas can go back to being a liquid, the liquid can go back to being a solid. If it's irreversible, then a chemical change has occurred. They are distinct from chemical changes since the material regains its original properties. So when it goes from solid to liquid, it is a reversible change, and once it goes back to being a solid, it goes back to having the properties of when it was a solid. When it goes to being a liquid, it gains the properties of being a liquid. When it becomes a gas, it has the properties of being a gas, and it's all reversible. With a chemical reaction, it's not reversible, and something new has been made. Internal energy. We did cover this slightly in physics. It refers to combined kinetic and potential energy of all, in the previous topic of all particles within the system. So the energy contained within the system attributed to particles that comprise it. So the energy contained within the system is attributed to the particles that comprise it. So meaning it's based on the particles. So the more kinetic and potential energy the particle has, the more internal energy that the system has. Now, what would happen if this solid were heated? The temperature would rise. The particles would possess greater kinetic energy. Internal energy would increase. It could change state. What would it need to do to change state? It would need to break the bonds between the particles. And when enough bonds are broken, it'll turn to a liquid. what could happen if this solid were heated? So the heating raises the energy levels. Remember what we said? If you increase the energy, thermal energy, you're increasing the internal energy of this. And internal energy is either kinetic or potential. Now, that thermal energy gets mainly converted to kinetic energy. Kinetic energy is half times the mass times the velocity squared. Now, the mass of the particles is not going to change. That's going to remain constant. So if the kinetic energy increases, what's the only thing that can increase? The velocity. And at that, it's exponential in that, not exponential, sorry, it is squared. So if the kinetic energy increases by 1 joule, whatever the velocity increases by, it would be squared. So the velocity increases is bigger, relatively speaking. So when we say when we say proportionality, if one thing doubles and the other thing doubles, here, if one thing doubles, the other thing is not doubles, but it's to the power of 2, so it increases by a power of 4. If one thing triples, the other thing goes up by a power of 9. So if our kinetic energy increases by a power of 4, our velocity will increase by a power of 16 because it's being squared. Now, this increases the system's temperature or results in a change of state. So initially, we get an increase in temperature because the particles start to move faster and faster. But in at a certain point, the temperature increase stops because all the energy is being absorbed by the bonds, so that the bonds can start breaking and that the state can start changing. Now, we've got to understand there's two things here. One is an increase in temperature, and one is where let me rephrase that. There's two things that can occur here. We can add heat energy, which causes an increase in temperature, or we can add energy and it causes a change in state. Both need to be looked at, and both need to be understood. So you can have a question that might say, the temperature is minus 15 degrees. We're talking about a piece of ice. Then energy is added until that solid melts. So now there's two things that's happened with this energy. Initially, that ice cube, because ice melts at 0 degrees, initially what's all the energy done? All the energy has been used to increase the temperature of minus 15 to 0. Once it's got to 0 degrees, what has the energy been used for then? It's been used to melt it. It's been used to turn the solid to a liquid. Both need to be understood. I'm going to repeat that a few times so we can really understand. So when we talk about specific heat capacity, this refers to the amount of energy needed to make the temperature increase. When we talk about latent energy, we're talking about the energy needed to make something melt or change state. So both things go hand in hand. Now, what does the temperature increase in a system depend on? What is specific heat capacity? The amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So if you've got a piece of metal that weighs 1 kilogram, so it weighs 1 kilogram, is the amount of energy that needs to go inside it to make the thermometer show that the temperature has gone up by 1 degree. And this is the apparatus that we can use to do that. So here we've got a copper block. The copper block weighs 1 kilogram. We've got a thermometer to measure temperature change, and we've got an immersion heater. So there's usually you've probably seen it looking like this when you've done it at school. You've got like a copper block like this, and it's got hole for the thermometer to go inside, and it had a hole for the immersion heater to go inside. Then the immersion heater is attached to a jouleometer, and it's attached to a power pack. The power pack turns on, this heating element turns on, and it starts to heat up the copper block. Then you measure how much the temperature increases by and how much energy has been used. And because you've got energy, you've got mass, and you've got change in temperature, you can work out specific capacity. Specific capacity is C. Now, change in energy, now that's usually written as a Q, but I'm just going to write as E for the, and it's interchangeable. Q equals mass times specific heat capacity times the change in temperature. And that's usually written as theta, the Greek letter theta. So if you rearrange that, you can work out specific heat capacity. But if you look at this equipment here, what does this equipment show us? It gives us, if you have a mass pan balance, that is, you can use the mass pan balance to work out the mass of the copper block. Usually it's a kilogram though, just to make life easy. The thermometer gives us, oops, I've used the wrong thing and rubbed it out instead. I've gone way too far here. Apologies, just give me a second. Apologies, I've ended up clicking the wrong button, I've gone way too far. Okay, so if you look at this apparatus here, it is energy equals mass times specific heat capacity. So we've got the mass because we can weigh the copper block. We've got the Q, the change in energy, because we have a jouleometer measuring the energy. And we've got change in theta, the temperature, because we have a thermometer, so we can work out specific heat capacity. Now, what specific heat capacity, what we're working out here, when you work out Q, the energy, you are working out the amount of energy needed to increase the temperature. So in that kind of example I gave you before, if you've got an ice cube at minus 15 degrees, then if you want to work out the amount of energy needed to get that to 0 degrees, then we are using this formula. Okay, temperature changes. So we know specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So it's the energy required to raise the temperature of 1 kilogram of a substance by 1 degree. And you may need to convert units. So change in E, now that can be written as Q as well. It doesn't really make a difference. I prefer to write E, but it comes as Q as well, so they're interchangeable in this respect. That's not referring to charge here, it's referring to energy. But in this particular scenario, but let's just stick to E. So that's change in thermal energy. M is mass. C is specific heat capacity, and del change in theta, that's the Greek letter for T, that's temperature change. So make sure you know the units. So here we've got a question, calculate the energy needed to increase the temperature. Calculate the energy needed to increase the temperature of a 500 gram aluminium block by 15 degrees. So like I said, this equation is when we're increasing the temperature. Then we have another equation that we're about to go through in a bit. That is for when we're causing a change in state. And then we're going to do a question that kind of brings both of them together. So let's go through this question really quickly. Let's convert the units first. 500 grams, we divide by 1,000. That's half a kilogram. We know our formula here. We've got mass, 0.5. We've got specific heat capacity, 900. The change in temperature that we need is 15. Multiply them all together and we've got 6,750 joules. Okay, another example here where we've got energy needed for a 350 gram block by 8 degrees this time, and we've got the specific heat capacity of copper there. So metals usually have a lower specific heat capacity because it doesn't require as much energy to increase their temperature. Why? Because they have delocalized electrons, and the delocalized electrons carry electricity and thermal energy as well. They increase how quickly they transport it. So again, 350 grams we convert to 0.35 kilograms. We substitute all the numbers in. So 0.35 times 385, that's specific heat capacity, and we've got 8 for temperature change. Multiply it all together and it's 1078 joules. Okay, the energy transferred to the water in 100 seconds was 155,000 joules. Specific heat capacity of water is 4,200 joules per kilogram. Determine the mass of water in the kettle. Now, this is the information you also get in this question. So we're just going to zoom in just a little bit so we can see it. The temperature initially was 22 and it's finished at 100 and it was on for 100 seconds. So let's zoom back out. So that's why we have a change in temperature of 78 degrees. So in this kind of question, because it says determine the mass, first thing you should do is write down everything you know. So what do we know right now? We know that mass equals question mark, because we don't know mass yet. We want to know. We know that C equals 4,200. We know the temperature change. So that's delta theta. We know the energy transferred was 155,000 joules. So do we have enough to work out mass? Because the thing here is, some people look at time and think, whoa, what do I do with time? But actually for this part of the question, do we need to know time? Because we've got everything else from the equation. So we don't. That's why sometimes it's good to write everything down and bring that clarity for yourself. A lot of people will also have missed the fact that there's a temperature change from the graph. Otherwise, we have all the information here. The reason why the 100 seconds is there, because the second part of this question asks you to calculate power. And what does power equal? Energy divided by time. So we know the energy is 155,000, so we substitute that in. We know our specific heat capacity. We know change temperature of 78. Rearrange it all. So it's 155,000 divided by 4,200 times 7.78, sorry. But that's in brackets, so we don't have any bid mass errors. Do the calculation and we end up with the mass of water being 0.47 kilograms. So I'm hoping that makes sense. That's a really good question. Okay, specific latent heat. Now, when we just spoke about specific heat capacity, we're talking about the energy needed to increase the temperature. Now what we're looking at is the energy needed to make something melt. Because like I said before, if you've got something at minus 15 degrees and it says how much energy is needed to make that ice cube melt, you first got to calculate the energy needed to get it to 0 degrees, and then you've got to calculate the latent heat energy. In other words, the amount of energy needed to make it melt. So both things have to be understood. And what I've seen time and time again is that what students sometimes don't understand fully is the difference between the two. When this topic comes up, they kind of skip past, they memorize the actual formulas, but not the theory and the understanding behind it. Okay, so the energy required to change the state of a substance. I have slowed down a little bit, so I'm going to speed up. So if there's something that you need more explanation on, just ask. I'm hoping now the main point I'm trying to clarify has been clarified. So this is the energy required to change the state of a substance, like melting or boiling, without changing its temperature. So this is where we get a flat line on a graph. When something's melting or boiling, the temperature stops increasing because all the energy is going in to the solid to break bonds. And specific latent heat is the energy needed to change the state of 1 kilogram of a substance without any temperature changes. So what is latent heat? We've got specific latent heat of fusion and vaporization. So when we say heat of fusion, we're talking about the energy needed to turn 1 kilogram of a solid into 1 kilogram of a liquid without changing temperature. That's melting. So when you have a graph like this, I'm sure you've all seen it before, and that's temperature. Sorry, this is temperature here, and this is time. And at a certain point, for a certain amount of time, the temperature stops increasing, even though the solid is being heated. And that's this here, specific latent heat. All the energy now is going into the solid to break the bonds, but the energy is still going in, there's still energy being used up. So to work out the amount of energy there, that's where we calculate we use the formula for specific latent heat of fusion. And specific latent heat of vaporization is when energy needed to change 1 kilogram of substance from liquid to a gas with no temperature change. So how can we calculate latent heat? It is the energy for the change of state equals mass times specific latent heat, which is in joules per kilogram. So this is a nice straightforward question. I'm hoping there's a nice complex question that's about to come. I definitely added one in. I think it is a really nice question. And if you understand it, excellent. Now, this one's a nice straightforward one though. So we've got 500 grams of water and has a latent heat of fusion of 334,000 joules per kilogram. So first thing we're going to do is convert to kilograms. There's our formula. Substitute the numbers in, 0.5 and 334,000. Multiply them and done. 167,000 joules of energy were needed. Now, calculate the mass of water when it takes 125 kilojoules to change it from solid to liquid. And the latent heat of fusion for water is 334,000 joules. These are constants, so they've been calculated and you'll get them in the exam. You don't need to memorize that the specific heat capacity of water is 4,200 or the latent heat of fusion is 334,000. So again, first we convert our kilojoules, so that means we times by 1,000, so we've got 125,000 joules. So energy equals mass times the latent heat of fusion. So we're going to rearrange that. So it's going to be energy divided by latent heat of fusion. So it's going to be 125,000 divided by 334,000, which gives us, and we only need to do this to two significant figures. So the answer is sufficient to write 0.37 kilograms. Now, what does this graph show? The slope sections, this is what we've already explained, but let's go through it again. The slope sections show temperature increases. The substance is heating up as a solid, liquid or a gas. There's no change of state here. The flat sections show temperature stays the same. The substance is changing state, melting, boiling. That means all the energy is being used to break bonds, not raise the temperature. Now, how do we work out the energy change here? It is mass times specific heat capacity times the change in temperature. How do we work out the energy change here? Mass times latent energy. So this is a clear distinction between the two. Because what people are used to answering is this type of question where you just plug in a few numbers, substitute the numbers into it and answer. But there has to be the understanding for, especially those that are doing higher paper, because this is very much, the kind of question I'm about to go through is very much a higher Yes, Abu Bakr, Musab, Islam, this is all AQA. The AQA session starts at 9 a.m. Well, it started at 9 a.m. today and it will start at 9 a.m. tomorrow and it will run till 1 o'clock with breaks. So specific latent heat. What's the difference between specific latent heat and specific heat capacity and specific latent heat? So like I said, specific heat capacity is the energy needed to raise the temperature, and latent heat is the energy needed to change the state. And here's the question I've been building you guys up for. Now, when this kind of question came up originally in tests, when it was a new specification, a lot of students would have got this question wrong because there wasn't enough of an understanding between specific heat capacity and specific latent heat. And that's why I've said this over and over again, just to get that understanding there. So look, I'm going to go through this one line at a time, and I would advise watching the video again afterwards when it's uploaded to YouTube. I mean, we upload it straight away, but when it's uploaded to YouTube, I would watch this bit again so it's properly understood. Now, the total thermal energy needs to raise the temperature of an ice cube to 0 degrees. That's what the question is asking. An ice cube currently has minus 15 degrees. It's at minus 15. And what this question is asking is increase the temperature to 0 and then melt it, and how much energy is needed. Now, the total thermal energy needed to raise the temperature of an ice cube, now it's actually giving you the answer here. Raise the temperature of this ice cube to 0 and completely melt the ice cube is 5,848. The specific heat capacity is 2,100. The latent heat of fusion of ice is 334,000. Calculate the mass of the ice cube. That is what I would call a beautiful question. Because what it's saying is, you know, when we say energy equals MC change in temperature and energy equals ML, it's in fact what it's saying is when you add them two together and it equals 5,848. So let me just write it here. So if you've got MC change in temperature plus the mass times the latent heat, that equals 5,848. So if you look at all the information that we've got there, there's two ways of doing this question. I'm initially going to, actually, if you're good at maths, there's a really nice way of doing it. So initially I'm just going to explain it. I might not, if I've got time, I'll explain it both ways. So let's use the explanation that's been given already in the notes. So we've got change in energy equals mass times specific heat capacity times the change in temperature. So let's substitute what we know. We've got change in energy equals mass times 2,100 times 15. So our initial change in energy, therefore, this is fine. Let's do it this way. This is actually the way I was going to do it, but I was just going to factorize it as well. But there's no point factorizing it. So we now know from our first equation that change in energy equals 31,500 times M. Okay, because we don't know M, the mass, we don't know that yet. Now if you use a second formula, so this is our first energy. Remember what we said? Both energies, energy 1 and energy 2, equals 5,848. So energy 2 equals mass times the latent heat of fusion of ice. So that's going to be 334,000 M. Now we've just said 1 plus 2, the both energies equal 5,848. So what we're going to do is we're going to add both of them up. So what is, in fact it does it here. So the 5,848 equals both of these added up, as we can see from there. So 31,500 M plus 334,000 M, which equals 365,500 M. And we rearrange that, so M equals 5848 divided by 365,500. So the mass is 0.016 kilograms. In other words, 16 grams. That is the kind of question you're going to get at the end of a paper or in separate science. It does come under both, but it can come in both papers. That's what I think is a fantastic question. Now, the triple award content, just for anyone that's unsure, because that might seem for a lot of people like it's a difficult topic. It is difficult. The comprehension side of that is difficult, but that's still as part of combined. But it's the kind of thing that would come, if that kind of question comes up, it comes towards the end of the paper, and that's a 5-mark question, potentially 6-mark question. Now, this topic 3 does have triple award content, but that starts on 3.3.2. So remember, all of this is linked to your specification, AQA. So if you go through the specification, you'll be able to see this all correlates. So again, that's just for anyone that wants clarity that this is an AQA topic. So, particle motion in gases. Now, I did, with the triple award students, I did already go through 3.3.2 till the end this morning. So we have already covered that as a topic. Thank you, Dean. If it made sense, that's excellent. If that makes sense, you're already on a way to getting a grade 9. That is as hard as any maths gets in science. That's as difficult as it gets. So if anyone's understood what I've just gone through, that is amazing. That's fantastic. Really, really pleased. I'm really pleased for you. So if you now do the right thing in your revision, which is what I mentioned to you guys, the AMAL method, activate your brain, understand everything. And that's the whole point of the AMALathon. Then memorize key parts and practice, lots of application, lots of past paper practice. Now my advice is, we've got 4 weeks. How do we get a grade 9 in 4 weeks? How do we get a grade 9 in 4 weeks? Number 1, understand everything. So if you recap these videos, what's going to happen with all the videos is we're going to take all the physics and make one recording out of it. Take all the chemistry, make one recording out of it, and one recording for the biology. So there'll be 6 to 7 hour videos that will cover all of biology, all of chemistry, all of physics. So if you need to recap any of the activate phase, it will only take you 6 hours. Now I know there's loads of videos out there that say learn it all in 20 minutes, learn it all in 30 minutes, but all those videos, what they're doing, they're excellent. They're really good for a last minute revision just before you enter an exam, but it is not for the activate phase. They are good for last minute revision only because they don't cover everything. What we're doing here is we're covering everything. So number 1, activate your brain. We are going to provide, we've all these recordings are up, so it takes you 6 hours to activate yourself for one topic. And that's about the right amount of time. 20 minutes, 30 minute videos, those are last minute videos, last minute revision, where you've just got key topics. And that's for someone who's now desperate and they just want to get themselves to a grade 5. That 20-30 minute video is not going to take you to a grade 9. It takes 6 hours to get to a grade 9. Then, as you're going through that video and you're looking at past papers, you start to understand what needs to be memorized. And then through the past paper practice, you will start to understand what you need to memorize, what the examiner is asking for. You'll get yourself to that grade 9. And we've got 4 weeks. So right now, as soon as the AMALathon's finished, like I advised you in our last session, I advise that you try and do 2 papers per day. No, sorry, one paper per day. So it could be a third of biology, a third of chemistry, a third of physics, or it could just be a whole biology paper one day, then a chemistry paper, then a physics paper, and then just keep repeating. If you do that, you'll have gone through 7 biology papers. So as in what by that, I mean if you're doing 2 a week, you'll have gone through 7 biology papers, 7 chemistry papers, and 7 physics papers in 3.5 weeks. And that is more than doable. So you spend 2 days doing Activate. You've got 6-hour video and you can get through it in 2 days, 3 hours per day. Then you've learned that topic, and then you need 3.5 weeks. You need 3.5 weeks to actually go through all the past papers. For that, I'm only talking about paper 1 here. Okay, particle motion in gases. So I'm really hoping every single person that's been joining us live and any person that's watching the recording gets the grades that they deserve, which is a grade 9. So when the results come out, we will send a post out. So I'm hoping some of you guys can come back and let us know how well you did. Gas particles move randomly and rapidly in all directions because they're full of energy. So consider if you've got a solid, how does a solid turn to a liquid? We add energy. How does that liquid then turn into a gas? You add more energy. So that means the gaseous state is the most energetic. So they move randomly and rapidly in all directions. They are widely spaced and have no fixed positions because there's no bonds between them. They move randomly. So whatever they collide into, that's going to dictate what direction they move into. As temperature increases, particles gain even more kinetic energy and they move faster. And that's the case when you go from solid to liquid to gas. Which is why if you put your hand in boiling water, which please don't do this. By that I mean if you put your hand in really hot water that's less than 100 degrees, it'll burn, it'll hurt. But what will hurt even more is if when your hand, and this may have happened to people when they're making a cup of tea, if you put your hand at the side, it will burn your hand, you feel the pain. But if your hand ends up in the steam, it hurts a lot more because that gas has got even more energy. So it's transferring even more energy to your skin. When gas particles collide with the walls of a container, they create pressure. So higher temperature leads to faster motion. Remember, kinetic energy increases the speed, and that means greater pressure. That's if the volume stays the same. Why is it greater pressure? Because pressure is when a particle collides with the side of the container. If it's going faster, it's going to hit the container more often. So why does pressure of a gas increase when its temperature is increased? When temperature increases, gas particles gain kinetic energy. They move faster and collide more often with the walls of the container. Each collision also happens with more force. This results in a higher pressure inside the container. So like what we were saying before, like what I've just said, when a particle hits the side of a container, that's pressure. A balloon is a really good example. When you put air into a balloon, the balloon gets bigger. You put more air in, it gets even bigger. Why? Because there's even more particles in there. Every time the particles hit the side of the balloon, it gets bigger. If I put more air particles in, now the particles are exerting even more pressure. They're hitting the side of the balloon even more, so the balloon gets even bigger. Now, if I get that balloon, and this is something you can try, if you get a balloon, it might be average sized or whatever it is. If you get an average sized balloon, you put it under a hot tap, then what will happen? It will increase in size. So if you put a balloon in warm water or hot water, it will increase in size till it bursts. That's because now what you've done is, you've increased the temperature, the gas particles have got more kinetic energy. Kinetic energy equals half times mass times velocity squared. Mass times velocity squared. So you've increased the kinetic energy, you have increased the velocity. The particles move around faster, hit the side of the container more often, which means the pressure increases. Or in our case, the balloon gets bigger. Okay, and this is the triple award content that we've covered in the morning. Okay, thank you very much everyone. We started an hour early and we finished 5 minutes early. Really appreciate everyone's time again today. Please keep sharing. Please like the videos. We've got some really good animations for biology up at the moment. They are based on the Edexcel spec, but they cover the topics that you're covering as well. Particularly when you get to things like protein synthesis, there's some really good videos for those kind of topics. Okay, thank you everyone. Have a wonderful evening. I hope you've enjoyed the session. You're more than welcome to add some feedback or give me a rating at 5 out of 5. Not 5 out of 5, sorry. I'm telling you what to do there. Whatever you want to give me out of 5. And that just gives us as a team an indication of how things are going. Okay, thank you very much everyone. Have a wonderful evening. I'll see you all tomorrow morning. So remember, tomorrow morning, 9 a.m. Dean, there has been an issue with the slides, so it's we're just seeing if we can. Oh, thank you, Asha. We're just seeing if we can rectify it before the end of the sessions. So we are really sorry that they've not been made available. The first session ones were made available, but we've had some issues since. When we have the AMALathon 2, the issues that we've had will be sorted by then. So you'll definitely get all the resources for AMALathon 2. And hopefully for the pre-exam workshop as well. Okay, thank you everyone. Thank you, Dean. Really appreciate it. Good afternoon, everyone. Welcome to AMALathon Day 4. We're just about to now go through biology. What we're hoping to do today is go through biology topic 3 and hopefully as much of biology topic 4 as possible as well. If anyone has any questions, you can ask in the live chat. I'll do my best to answer straight away. And if it's not possible for me to answer while I'm teaching, then I will go through it during the question and answer session at the end of the day. Okay, so we've already gone through all these topics. We did get up to 3.4, so we're going to continue from DNA. Thank you for those people that have been sharing the videos. We really appreciate it because each video has had up to 1,000 views. The first AMALathon Day 1 has had 1,100-1,200 views, and so we really appreciate those people that have been sharing it. We would have been happy with 10-20 students because it's just at the moment what we want to do is just help. We just want to increase I suppose our exposure so people know what we're about, what we're aiming for. And one of the main aims is to make education affordable. So it doesn't matter where anyone is in the world, everyone should have access to quality education regardless of what they can afford. So we want to keep our costs low and keep the quality high. Okay, so we're on 3.4 now and we're looking at DNA. What is the structure? So I just need to check something. What is the structure of DNA? So DNA is the molecule that carries genetic instructions for life, and it's, as I showed you in topic 2, if you look within a cell, if you get to the nucleus part of the cell, so here we have our cell, and then in the middle of that cell we have our nucleus, and then within the nucleus you have lots of chromosomes, and the chromosomes, if you were to unravel them, would reveal the DNA, and small segments of that DNA are genes. Different versions of the genes are alleles. Now the DNA is a double helix. Now when you get questions on anything linked to the structure of DNA, you're either going to get a question just on DNA, or you might get a question linked to DNA and the experiment linked to DNA. That's 3.6. So we're going to go through that in around 5-10 minutes when we get to it. Now, there's certain things you need to memorize. And when you start working through past paper practice, which is really important, the AMALathon is just to activate your brain. It's just to help you understand everything. After that, you need to start memorizing. You need to start doing lots of past paper practice. If you want a grade 9, there's still plenty of time. When I say there's plenty of time, there is plenty of time. 4 weeks is enough to get to a grade 4 if you do the right things. So right now, let's look at biology separately. We're doing 6 hours of learning. So in 6 hours, you'll have understood content enough to get to a grade 9. Now, if you've seen a video that says, learn everything, pass your GCSEs in 20 minutes, half an hour, those videos don't cover everything. That's enough to get yourself to a grade 5. To get to a grade 9, you need to watch a 6-hour video. That's what we're making for you. So afterwards, when we bring all the biology into one video, or the chemistry into one video, or the physics into one video, that 6-hour video will be every single specification point. Then if you want to watch that again just to help you with your understanding, that's phase 1. Then during the video, you'll see bits that I've said, oh, this is important to memorize, that's important to memorize. So you memorize as you're going through. And then you start doing past paper practice. And with the past paper practice, the more you do, the more you're going to understand what's required in a question and what is required for you to help you to succeed, what the examiner is actually looking for. So I've seen lots and lots of past papers. I've been looking at them since 2018. So I have a good understanding. So I'm going to keep telling you what needs to be memorized. Now, if you spent 6 hours going through our video, now my advice is to do 1 past paper a day. So for combined, that's only 60 minutes. But as you're doing it, have your mark scheme open. So you're looking at the exam question, you're looking at the mark scheme, look at the exam question, look at the mark scheme. And if something comes up that you don't know off by heart, then you memorize it. You give that around 2 hours. So if the exam's a 1 hour exam, the second, whilst you're actually going through one question at a time, you're also marking it live. So you have the question, you have the answer, you spend a bit of time memorizing. You have the question, you have the answer, you spend a bit of time memorizing. It could be that you make notes on it. It could be that you make flashcards on it. You do whatever's necessary, whatever helps you to learn it. And that's just 2 hours a day. And if you're doing 6 exam papers a week, as in 1 paper per day, by the time you get to 3.5 weeks, you will have covered 7 years worth of exam papers. And we're talking about topic 1 here. If you now do the same thing, you add a couple of extra hours, you could also get through all the paper 2 content. So I'm only talking about paper 1 content here. In 3.5 weeks, you can get all your paper 1 content to a grade 9. So it is still possible. Everyone on here should be aiming for a grade 9. Anyone watching this video afterwards should be aiming for a grade 9. Anyone that's currently doing foundation should be aiming for a grade 5. It is possible. Now, what is the structure of DNA? So we've just said, now I'm going to highlight the key things that need to be learned. DNA is a double helix, 1 mark. It's 2 strands, 1 mark. It's got a sugar phosphate backbone, 1 mark. It's got base pairs, AT and CNG. Now notice they're complementary. So it's 1 mark for saying AT, CNG. It's another mark for saying that they're complementary. As in A always joins to T and C always joins to G. And the DNA is a polymer that can sometimes get your mark as well. So look, all those marks just from this. You don't need to memorize these off by heart. As you don't need to know that T stands for thymine, A for adenine, G for guanine, C for cytosine. What you do need to know is that that bit there is a repeating unit. That bit there is a repeating unit. They're monomers that join together to make polymers. So DNA contains 4 bases, A, C, G, and T. 1 mark. Adenine always pairs with thymine, and cytosine always pairs with guanine. Now, if you just say A pairs with T and C pairs with G, that's another mark, which we already covered on that first slide. Now, when you have a sequence of 3 bases, we call it a triplet code or a codon, and that codes for a specific amino acid. Now, you don't need to know too much more than that. That's more triple award. So those that were with me yesterday from 4:30 till I think it was about 5:15, we went through this in a lot more detail. The order of bases controls the order in which the amino acids assemble to produce a particular protein. So what that means is, there's the DNA. Each one of, if you look at the DNA, you've got all these bases. Each three triplet codes, each 3 bases code for a particular amino acid. So these 3 will code for 1 amino acid. The next 3 will code for another amino acid. Another next 3 will code for another amino acid. You combine, if you join all those amino acids together, you make a protein with a specific shape. Okay, so this is a question. Describe the structure of DNA. And usually it comes up as a 4-mark question. So number 1, DNA is a polymer made up of 2 strands that twist to form a double helix. It's a polymer made up of monomers called nucleotides. DNA contains 4 bases, A, C, G, and T. Cytosine C always pairs with G. A always pairs with T. DNA is a polymer made from long chain of repeating units. Now if you look at the mark scheme, polymer, 1 mark. 4 bases, 1 mark. Complementary, 1 mark. AT and CNG, 1 mark. We didn't mention this, but between the bases, there's weak hydrogen bonds that join the bases. Another mark. 2 strands, another mark. Double helix, another mark. And nucleotides. Now, nucleotides, you know how the bit I circled before? This bit, each monomer is called a nucleotide. So when you've got this phosphate group, the sugar group, the base, all of that equate, what we call the whole thing is a nucleotide. So it's lots of nucleotides attached to each other. So you know all of 3.4, you can learn all of 3.4 and answer every question linked to 3.4 with that one mark scheme. Let's get back to this mark scheme. So if you want to learn 3.4 and answer every single question linked to this, just memorize this. Okay, 3.5. Describe the genome as the entire DNA of an organism and a gene as a section of DNA molecule that codes for a specific protein. So again, this seems really complicated, but actually, so excuse me 1 second. So we've got cells. Inside the cells, we've got nucleus. Inside the nucleus, we've got chromosomes. So we're just going through the same thing as we did before. You don't need to worry about this word centromere or telomere. The chromosome is made up of a raveling up of DNA. So if you unravel it, you've got this long section of DNA. And then one small section of DNA is called a gene. And that codes for proteins. But we've all got different versions of that same gene, which is an allele. We've got 23 pairs of chromosomes, and a gene is a section of DNA that codes for a specific protein. So for example, my eyes are dark brown. So I've got the allele, I've got the gene that makes the protein for dark brown eyes. Each protein helps determine a characteristic such as eye color, height, or the risk of diseases. So what is the genome? And this is the bit that you've got to memorize. The genome of an organism is the entire genetic material of that organism. So it's the entire genetic material of the organism. It's every single gene code that scientists have spent ages writing down the coding for. So for humans, the genome has been completely mapped through the Human Genome Project. So now what we can do with the Human Genome Project, because all these scientists have gone through this effort and they've got all this information of every single gene within the human being, it can help us, and this is the part that is memorized, it can help us identify diseases. It can help us understand genetic disorders, and it can help us trace human migration. That's a little bit more difficult, tracing human migration, but understanding genetic disorders and identifying genetic diseases have become much easier because of this. And why is it important? If we know about genetic illnesses or genetic disorders, it means we can make specific medicine for a person. It can be a personalized medicine that treats only them or treats those that have got the same genes as them. Because some medication doesn't work as well on people from different countries. So because based on genetics. So based on their genetics, based on our heritage, not the country that we come from, but our heritage and our genes from that heritage, some medications work better on people from some parts of the world, but not as well on people from other parts of the world. And that's because we make certain enzymes. We all produce different types of chemicals in our body that interact positively or negatively with that medication. So if we understand the genome, the genes of a person, we can make personalized medication. So that's number one. It helps scientists develop gene therapies where faulty genes are replaced or repaired. And so it helps with gene therapy. Yep, that's a good thing. Faulty genes can be replaced, and faulty genes can be repaired. So this is good stuff. Now, why is it important? Why is understanding the genome important? So like we've said, medicine and health might be a risk. So some people might be at more risk of getting cancer, diabetes, heart problems before the symptoms even appear. It helps us understand genetic disorders. So this is all repetition, so we can really understand it, and it helps us to profile from a DNA perspective, from, for example, a crime scene. But these are the main ones. The crime scene bit, we don't need to worry about as much. That's additional information. And we don't need to worry about tools like CRISPR. We need to worry about developing of gene therapy. So what can we use the genome project for? Help us develop medicine that cures illnesses that people don't even know about until they kick in. So here's a really good question. State the benefits of discovering the sequence of bases for all plants and animals. So number one, it helps search for genes linked to diseases. So this question summarizes the whole of 3.5. So if you're going to memorize something, memorize this mark scheme. It's the reason why I've added it in. It's the reason why I did this question, because I know these are the kind of questions that come up. Understand inherited disorders and diseases. And trace the migration patterns of organisms from the past, therefore helping understand an organism from a potentially helping us understand an organism from an evolutionary perspective. It enables personalized medicine. So look, it searches for genes linked to diseases. It helps us understand inherited disorders and diseases. It helps us trace migration patterns. It enables personalized medicine by identifying how genetic differences influence response to treatments. And it helps scientists develop gene therapies where faulty genes can be replaced or repaired. So memorize this slide. Get full marks if this question comes up. This is a topic that's not well answered. So there's your mark scheme. I would just memorize the mark scheme. Identify useful genes. Track evolution. Or better than that is identify new species. Understand diseases. Discover new medicines. Identify the sequence that allows some plants and animals to cope with environmental changes. And it's always going to be around a 2-mark question. 3.6. Explain how DNA can be extracted from fruit. Okay, I'm definitely gonna have to speed up now. How can DNA be extracted from fruit? So fruits such as kiwi or strawberry, and this is what you need. You need salt, heat source, chilled ethanol, washing up liquid, a filter. So the whole filtering process, you need filter funnel, filter paper, a conical flask. You need protease, potentially, and a small clay container. So how do we do this? Step 1, peel the skin off the fruit and mash it up. You don't have to peel the skin off. You can, but if you're using something like kiwi, then it's probably easier to take the skin off so that you're not having to, it makes filtration as part of things easier. But with something like a strawberry, I suppose you could take the stem off, because although the stem will still have a bit of DNA, but it's easy to mash up. It's easier to mash up the fruit part. So this breaks up, then we mash it up, that breaks open the fruit's cells. So main thing here, don't worry about peeling the skin off. The main thing is we mash up the fruit. So kiwi or strawberry is the best. That breaks open the fruit cells. Then you mix the fruit pulp with salt and washing up liquid. Salt helps separate the DNA from the proteins. That's what we want. We want to separate the protein from everything else. The washing up liquid breaks down the cell membranes from releasing the DNA. So that means because the DNA is stuck behind the cell membrane, the nuclear membrane, so even the nucleus has a membrane around it, and the washing up liquid breaks that down, so the DNA is free to come out. And what the salt does then, it takes the DNA and it starts joining it to it, attaching it, starts clumping it up. Now, how can DNA be extracted from fruit? Let's continue. Now we heat the mixture gently at 60 degrees for about 5 minutes. That denatures the enzymes that could break down the DNA and aids in further lysis, as in it helps the cell break down further. You don't have to do that process, that part of it. It still works without warming up at 60 degrees. Filter the mixture to remove solid fragments. So now what you're doing is getting rid of all the cell walls and getting rid of all these big chunky bits, solid fragments. And now what you're left with is a nice clear solution at the bottom. Now you cool the filtrate in an ice bath, or you just pour into the sides chilled ethanol, so cold ethanol. Now that cold ethanol, what you do is you make it run down the sides. So as soon as it touches this filtrate at the bottom, all of the DNA precipitates out. That's why we add the ethanol. It helps it precipitate. It helps it to precipitate, and then we can see this visible stringy white substance. Okay, here is a question. A student wants to extract DNA from strawberries. The student crushed the strawberries and added washing up liquid, salt and water. The enzyme protease was then added to the mixture as well. The mixture was heated and filtered. Finally, the student poured the filtrate into a test tube and ice cold ethanol was poured down the side of the test tube. The question is, why did they add washing up liquid? Why did they add salt? Why did they add protease? Why did they add ice cold ethanol? So not only do you need to know the process, even more than the process, more important than the process is knowing why, and why we add these different chemicals. So let's look at each one. Why do we add washing up liquid? Because it breaks down the cell membranes, releasing the DNA. Why do we add salt? Because it helps clump up the DNA. It helps separate the DNA from the proteins, and it also helps join it together. It attaches it in like a clump. Why is protease added? Protease is added because it breaks down the proteins in the cell. So it actually does something similar to the washing up liquid, which although the washing up liquid specifically targets cell membranes, the protease breaks down a lot of the other proteins that could stop the release of the DNA. No need for the word pure there, but it still makes sense. State why ice cold ethanol is poured in. It is to make DNA. DNA is insoluble in ethanol, so it doesn't dissolve in ethanol. So it doesn't. The DNA is insoluble in ethanol, so it doesn't dissolve in that. So it precipitates it out as a visible, stringy white substance. So in the Edexcel specification, if you say salt increases friction, you won't get the mark. You won't get a mark for that. Possibly in other specifications, but definitely not in Edexcel. Now, why are washing up liquid, salt, protease and ethanol added? So same kind of question, just another summary. So if, again, memorize this. This is the kind of thing that comes up over and over again. Now this is all triple, so let's quickly zoom past the triple stuff that we covered yesterday. So those that were with us from 4:30 onwards would have gone through this. Still happy to answer questions linked to it if anyone has any questions. Okay, alleles and what their role is in inheritance. So how inherited characteristics result from alleles and how variation occurs within the population needs to be understood. Variation is differences in characteristics among individuals in a population. So this may be due to genes or alleles an individual inherits. So what we inherit from what a baby inherits from their mother and father are their genes, and then the genes have an impact on what proteins are made in that child. So if they've got the protein that makes a certain eye color, the protein that makes a certain shape of a nose, a protein that is linked to skin color, any of these things. Or it can be due to environmental factors as well. So our difference in our variations can be linked to environmental factors. For example, someone gets a cut or a scar. What we're covering right now is biology, topic 3. So it can be linked to a scar, or it can be something, can be a combination of genes and the environment. So for example, our height is actually a combination of both. Genetically speaking, let's say if someone's going to be really tall and their genes mean that they're going to be 6 foot plus, then genetically speaking they're going to be 6 foot plus, but the environment and their diet can have an impact on that. So if someone gets an illness when they're young, or they live in unfortunately they live in a way that's they don't have much food, or they're malnourished, then that can lead to not reaching that particular height. What is variation? So variation just means the difference between individuals of the same species. And types of variation, you've got genetic variation, so it's just a quick recap of the page before, and environmental variation. And you can have a combination of the two as well. So alleles are just different versions of the same gene. And offspring inherit two alleles from their parent, one from one parent and one from the other parent. So offspring inherit, so that means we can either get two genes. So we get two alleles, one from each parent. Now, if the alleles are the same, we call it homozygous. And if the alleles are different, we call it heterozygous. And when it's heterozygous, whichever gene is stronger is the one that gets expressed. Now, the alleles that we inherit, we call genotype. All of this will be covered properly in 3.13. 3.13, as a specification point, is all about knowing what each term means from a genetic perspective. And then that means when we go through genetics, everything makes a lot more sense. So inheritance is the process by which genetic information is passed on from parents to offspring. So we're now going to go through the key terms. So what is inheritance? This happens through genes, which are sections of DNA. So the genes, we've got our DNA, and each small section of that DNA, not necessarily just that section there, it could be a bigger section, it's called a gene, and it codes for a specific trait like eye color, hair type, or even blood group. Now, when living things reproduce, they pass on a combination of genes from both parents to their offspring. This is why you might have a nose that's similar to your mum or your dad. You might have curly hair like one of your parents. That's because everything you've inherited is from your genes, from your parents. Now, chromosomes, genes, alleles. Chromosomes are structures found in the nucleus, so we know what chromosomes are. We've said it lots of times now. Chromosomes, when you unravel it, we end up with DNA. When you get one part of the DNA, we call it a gene, and the gene codes for a specific protein. And what do we call different versions of a gene? We call it an allele. And what are alleles? Different versions of the same gene. So for example, if you have a plant that could be red and it could be white, that means you've got one allele for red flower and you've got one allele for white flower. So that's two versions of the same gene. Dominant and recessive alleles. Now, a gene codes for a specific type of protein. Allele is a different version of that same gene, but some of these genes, some are dominant and some are recessive. What that means is when we take our genes from our parents, some are stronger and some are weaker. The dominant one is the one that is where we get our characteristics from. So dominant alleles are the ones that are expressed. So let's say we get two genes from our parents and we've got one capital B, and B is for black eyes, and we've got small lowercase b for blue eyes. Now I've done capital B because that's dominant, and lowercase shows recessive. What that means is, even though you've got the gene for brown eye, let's say brown eyes instead, brown eyes, and you've got blue eyes, the one that the child will actually be, the offspring will have brown eyes, because the brown eyes is the dominant allele. So dominant alleles are always expressed if present and are represented by a capital letter. For example, capital B is used to represent an allele for brown eyes. Now if you look at recessive, recessive alleles are only expressed when two copies are present. So now if parent number one gives a lowercase b for blue eyes, and parent number two also gives the gene for blue eyes, then the child that comes from that will also have blue eyes. So the only way a recessive allele can be expressed and that protein can be made is if there's two of them. Otherwise, it's the dominant one that always expresses itself. So recessive alleles are not expressed when in the presence of dominant alleles. Okay, so that we need to understand too. What does homozygous and heterozygous mean? So if we've got two of the same gene, for example, capital B, lowercase b, so we've just said that's for brown eyes and this one is for blue eyes. Heterozygous is when you've got one of each. Simple as that. So homozygous is when both alleles are the same, and heterozygous is when you've got one of each. Now when you've got heterozygous, it's the dominant allele that will be expressed. Now, what do we mean by genotype and phenotype? The genotype is the genetic makeup of an organism. It tells you which alleles an organism actually have. So, genotype, for example, based on the examples we're already using, the genotype of someone with brown eyes will be capital B, or it will be, so that's the homozygous for brown eyes, or it will be capital B, small b. So, or dominant and recessive. But for blue eyes, it'll be lowercase b. And that's a genotype. So that's a genetic makeup for that organism. But phenotype will be the actual characteristic expressed. So here, brown is the phenotype. Here, the phenotype is blue. Blue eyes, brown eyes. So for this particular individual, the eye color would be capital B, small b, so that's a genotype, but the phenotype is brown eyes. Now, what is the genotype of this individual's eye? So it's lowercase b. In other words, the genotype is that, and the phenotype is blue. What are gametes? So it's something we've already covered. A gamete is a reproductive cell, so that could be a sperm cell or an egg cell. They're formed by meiosis, and it makes haploid cells. So a lot of what we've just said in 3.13 is what we've already covered. So meiosis is used to make gametes. So you end up with half the number of chromosomes or haploid cells. Okay, now the allele for purple flowers is dominant to the allele for white flowers. Which term describes the allele for white flowers? So the allele that describes white flowers is recessive. Question 2. Potatoes have different physical characteristics such as color. Which genetic key term describes the physical characteristics of a potato? It's phenotype. Right, we're going to move past these questions now. Which key term means the genetic makeup of an organism? And that would be genotype. What's the definition of the key term allele? Different version of the same gene. Okay, 3.14 now. Explaining monohybrid inheritance using genetic diagrams, Punnett squares, and family pedigrees. So monohybrid inheritance focuses on single characteristics controlled by one gene. What that means is some things are controlled by multiple genes and some things are only controlled by one gene, such as flower, the color of a flower in pea plants, the color of something's fur in cats or other animals, or color blindness. So how can we, so this is the process to this now. If you memorize this process, or at least understand the process, it's really easy to answer monohybrid inheritance questions. So the first thing you do is you draw a Punnett square. There we go, Punnett square. A bit like a noughts and crosses, what you would draw for noughts and crosses. Then we add in our genotype. Now in this case, we're saying the mother is dominant, has dominant alleles, and the father has dominant alleles. Now we compare the alleles in each box. So if we've got, so what that means is B and B is capital B, then we're joining these two here. We've joined these two here and joined these two here. So we've ended up with everything capital B. So their child will also have the dominant genotype, and they would have the phenotype that corresponds to. So in this case, what we were saying was the parents have got brown eyes. So for some reason the questions come at the end, unfortunately. So we said the mother had brown eyes, capital B, and in this case the father had brown eyes, capital B. We made our Punnett square, we've completed the cross, and now we know 100% chance that their children will also have brown eyes. Now let's look at another one. Now here we're saying a gene controlling fur color has two alleles. Capital B represents the dominant allele for black fur, and lowercase b represents the recessive allele for white fur. So lowercase b, and we've got capital B there. So these are our two parents now. Actually, no, sorry. So we've got one mouse with black fur, but it's heterozygous. And we've got one mouse with homozygous fur. Now what we could say is the black fur is the male, so that would be a sperm cell. Now 50% of the sperm cells will contain capital B, as in black fur gene, and 50% will have the gene for lowercase b, which is for white fur. And here we've got our egg cells, and both egg cells have got lowercase b. So now if we do the Punnett square, that's going to be capital B, so lowercase b, that'll be capital B, lowercase b. Now if we combine this square, it's going to be lowercase b, and here we've also got lowercase b. So what that means is, out of the offspring, 50% have got black fur, and 50% will have white fur. So it's a 1-to-1 ratio. Okay, this is now looking at a couple that are heterozygous carriers of sickle cell disease. Now, sickle cell disease is a recessive disorder. Recessive disorder means if we use the letter D, the child has to have two lowercase d's to have the illness. But what we're saying here is that the parents are heterozygous, so they've got capital D, which is your normal gene, and they've got lowercase d, which is the allele that would cause the illness. So the first thing we've got to do is draw the Punnett square. We now added the parents' alleles. So again, that's the egg cell, that would be a sperm cell, and that would be a sperm cell. So now if we make our combinations, we've got one child that is capital D, capital B. So in that respect, we would call that child normal. Not a nice way to name it, not a nice thing to write, but that's what we say, normal. As in, it's not even a carrier. Now this child here is normal, as in other words, doesn't have the disease, or doesn't have sickle cell disease, but they are carriers. Just like the parents, they're carriers of the recessive gene, the recessive allele. And this child, unfortunately, would be the one that ends up having sickle cell disease. So that means there's a 1 in 4 chance that their children will have sickle cell disease, or you could put it as 1/4, or you could put it as there's a 25% chance their child will be born with sickle cell disease. Okay, so we've covered all this. So another question, predict using the Punnett square the percentage probability that the genetic cross will have offspring that produce green colored peas. So this is based on each parent being heterozygous. So they've got capital A and lowercase a. Now, capital A represents green, lowercase a represents yellow. So there, we've done our Punnett square, we've completed the cross. So we've got green, but it's a carrier of the yellow allele. We've got green, but it's a carrier of the allele. And we've got two A's, so we've got one of the pea plants that will be yellow. So there's a 1 in 4 chance. That should have said yellow. Apologies. Okay, so I hope this all makes sense. Okay, 3.15. Now, everything we're going to go through now for the next few specification points is exactly the same. If you understand how to use Punnett squares, then you've understood this whole section, or a big chunk of this section. Even the triple word content, which comes as, I think it's 3.17 and 3.18. If you get what I've just shown you, it makes it a lot easier. So let's have a look at how sex is determined. So we've got 23 pairs of chromosomes. 22 pairs control the traits, 1 pair determines sex. And there are 2 types of chromosomes that determine sex. We've got the X and the Y chromosome. If you get an X and Y, if you get XX, you have a female. If you get XY, you have a male. And you will not get any questions linked to XXY or anything like that. So if any questions like that do come up, because usually when I do things like this, there's loads of questions that come up on extra bits. We are just going to focus on male and female. What is the role of the sex chromosome in fertilization? So, as you can see, the egg cell, all the egg cells only carry 1 chromosome. They all carry X. But the sperm cells, either 50% carry X, 50% carry Y. Now, if the X egg cell is fertilized by the X carrying sperm cell, then we have a baby girl. If our egg cell, which only carries X, is fertilized by our Y chromosome carrying sperm cell, then we have a baby boy, or we have a male. Of course, this could happen in other animals as well, so I can't say female and male, but no, I can't say baby boy and girl, but female and male would be more accurate. So let's do it using a Punnett square. Now, same process. How can we model the inheritance of sex? We draw a Punnett square, we add the mother's chromosomes, X and X, add the father's chromosomes, X and Y, and now we combine the alleles in each box. So we've got XX, XX at the top, XY, XY, and what does that show us? 50% are female, and 50% are male. So when I had, so for a year, I lived abroad. And when I went to the hospital because my wife was expecting, and I spoke to the midwife, and she did a scan to see if it was a boy or a girl, and she said it is a male. And I said to her, how likely is it? As in, my point was is it 100% it's going to be a male? And she said to me 50%, which wasn't the answer I was looking for, but at least it was an accurate answer. I mean, in the end, it was a boy. So she could have said, yes, I'm experienced and I know it's definitely a boy. But she chose to give me the scientifically accurate answer instead. So, complete the Punnett square to show how sex is determined. Sex is determined in birds. Now, this question is a little bit of a confusing one. And actually, when this question has been transferred to these PowerPoints, the question's actually been deleted slightly. Now, in this question, it explains that males of this particular bird have the chromosomes capital A, and the female of this particular bird species has capital A, the alleles of capital A and capital B. Now, what do you think most people do when they see this question? They look at it and they get confused because they've always known XX to be female. So they can't get their head around the fact that AA is now a male. But you just have to accept the information you've been given and answer the question. So here we complete the cross, capital A. So what this means is we've got 50% chance of getting a male, 50% chance of getting a female. So AB in this case represents female. But when you get a question like that, don't get put off. You're just doing the same thing. Draw the Punnett square, add the male and female alleles, complete the cross, identify the phenotype, as in is it a male or female. So these two are males and these two are females, and then write down the probability. So this is a 1-to-1 ratio, 50% chance, or a 1 out of 2 chance. Now in this question, as part of the extension of this question, you would have been told to write down which ones were males and which ones were females. So these two would have been male and these two would have been female. But this is where people wrote the wrong answer. Students actually wrote the other way around because they couldn't get past the fact that for human beings, XX means female and XY means male. So don't worry about the question. It's the same process. Okay, calculate and analyze outcomes using probabilities, ratios, and percentages for monohybrid crosses and pedigree analysis for dominant and recessive traits. So this is similar to what we've already covered. We know what a monohybrid cross is and a genetic analysis. Well, we don't know genetic analysis, but we know what a monohybrid cross is. A genetic cross looking at one characteristic controlled by one gene with 2 alleles. So when we do our when we look at things using our genetic crosses, that's part of our genetic analysis. So monohybrid crosses and genetic analysis help us with probabilities, ratios, or percentages of how likely a particular inheritance is going to be. How likely a child will have a certain protein, a certain allele being expressed. So how likely a child's going to have curly hair or straight hair, or more importantly, if they're going to have a genetic disorder or not. So question 1. A father has a genotype of capital D, small d, for polydactyly, while a mother has a genotype for polydactyly of small lowercase d. Now, polydactyly is a dominant. So if someone has capital D, or if they have capital D, small lowercase d, they will have polydactyly. So polydactyly is actually carried on the capital D. So what we've got here is the male has heterozygous alleles, and the female, the mother, has homozygous recessive. That means she doesn't have polydactyly. So what's the chance of their child having polydactyly? So let's have a look. So it's just explaining here what it is. So what polydactyly does is it causes a child to be born with an extra finger. So it could be two capital D's, or it could be capital D, lowercase d. So step 1, let's draw a Punnett square. Step 2, let's add our alleles. Step 3, let's identify the phenotypes. So what we've got here is a child with polydactyly, and we've got another child with polydactyly. So that means there's a 50% chance, and then we've got the lowercase d's, just like the mother, they will have no polydactyly. Now we calculate the probability, the ratios, or the percentages. So there's a 50% chance of getting polydactyly, 50% chance of not getting polydactyly. Question 2. Both parents have polydactyly, but they are heterozygous. So let's go through the same process. There's a Punnett square. Add the alleles for both parents. Complete the cross by combining the alleles to show the potential genotypes. And looking at that, what percentage will have polydactyly? Well, that child's definitely got polydactyly. This one's polydactyly, but it's a carrier of the normal gene. The recessive one, that child's same is a carrier, and that child won't have polydactyly. So let's look at the percentages. 75% chance of polydactyly, or 3 out of 4 chance. So now we're looking at cystic fibrosis. Cystic fibrosis is an illness which causes too much mucus to be made, and that causes a buildup of mucus in, for example, in the lungs, in the pancreas, in different parts of the body, even in the reproductive organs. It can block the release of sperm cells and egg cells, so it can cause infertility, it can cause digestive issues, but mainly it blocks the lungs, because that's where a lot of the mucus is made, within our trachea, and it is really difficult illness to deal with. Now, it's a recessive illness, so you have to have small f, lowercase f to be ill. Now, what we've got here is a mother who's homozygous dominant, and we've got a father who is heterozygous. So let's draw the Punnett square, add the alleles. So firstly, thank you for all the positive comments, and Mariam, this is higher content, yes. It's also foundation content. The content, if it's specifically higher, I will say this is just higher. Or I will say this is triple award. Otherwise it's for foundation, higher and triple, if I don't say anything at all. What happens is you get, in a foundation question, it is, the question is just asked in a different way. That just makes it a little bit easier. And in higher, it's asked in a slightly more difficult way. So this is, okay, thank you everyone. And what it is with this is, it is combined. This is higher, and it's foundation and higher as well, this particular topic. But it's not specifically triple, it's for everything. So now let's complete the cross. So we can see from here, this child is normal. This child is normal, but is a carrier of cystic fibrosis. And this child is normal and a carrier of cystic fibrosis, meaning none of their children will have cystic fibrosis. Okay, this is incorrect. It's a 0% chance of having cystic fibrosis. Okay, now this is triple award content. I will be teaching this at 4:30. I'll be going through it at that time. So what I'm going to go through today at 4:30 is 3.17 and 3.18. I'll be going through topic 4, triple award content. So I'm going through 4.1, 4.6, 4.9, 4.12, 4.13. And then if there's time, I'll be going through topic 5, triple award content as well, which is 5.7, 9, 10, 11, 17, 18, 19, 21, and 22. Hopefully, should be able to cover that in half an hour, 45 minutes. Having said that, sex-linked genetic disorders does take a little bit of time to get your head around. But if you've seen what I've just zoomed through, it's the same process. You draw your Punnett square, you complete your Punnett square, and you're done. Okay, now, state that most phenotypic features are a result of, now 3.19 to 3.23 are actually quite small topics, so hopefully we'll be able to get through it in about 5-10 minutes. So 19 and 20 come into one category. What is a phenotype? So we already know what a phenotype is, but this just focuses in on the topic a little bit more. phenotype refers to the observable characteristics of an organism, such as height, eye color, or skin tone. Now, we say polygenic inheritance. That occurs when multiple genes influence one trait. So, for example, height. Height is not just one gene. Lots of different genes have an impact on it. Skin color, in some cases eye color, result from many genes working together rather than just one single gene. So that's when we say monohybrid in inheritance, we're talking about one gene. When we're talking about lots of genes impacting on the phenotype, then we call it polygenic inheritance. So a person's mass is partially influenced by the alleles they inherit from their mother and father. Give two other factors that can influence a person's mass other than genetic inheritance. So this is an actual past paper question. So let's have a quick look. So heights in humans is determined by many genes, each influencing growth in small ways. Environmental factors like nutrition and exercise also play a significant role. So this is the actual mark scheme answer. So environmental factors, a person's diet, exercise, if the person is affected by disease. And to be honest, if you memorize this mark scheme, you've got a good understanding of 3.20. That's essentially a big part of it. So our phenotype is based on what we inherit from our parents, but also it's based on environment as well, and they're the environmental factors that have the biggest effect. Okay, so this is what I've already explained, so I'm just going to go past. Okay, 3.21. Discuss the outcomes of the Human Genome Project and its potential applications with medicine. Now, when I covered the Human Genome Project before, I actually covered this one automatically within it as well, but I'll just quickly go through it again anyway. So the genome of an organism is everything that is contained within the organism's DNA. So the Human Genome Project, its main goal was to identify and map every gene found in the human DNA, helping scientists understand the full human genetic code. So it started in 1990 and it finished in 2003. So 13 years they spent mapping the genes within a human being. So it helped us map the genome. So now we know what genes and where the locations are within the organism's DNA. The entire DNA was around 20 to 25,000 genes. Helped us understand what part of the genes are non-coding and what parts of the genes are coding. So from a triple perspective, you need to know about this. Non-coding genes have the information on how much protein should be made. Whereas the coding part of the gene, which is the middle bit, that tells the ribosome which protein to make. So the information in the middle is the information about which protein is being made, whereas this green bit here, the non-coding part, gives information on how much of that gene should be made and when it should be made. So outcomes as well, applications in medicines. So it's helped find genes connected to diseases like cystic fibrosis, cancer, and Alzheimer's. The third thing is helped us to understand adaptation and migration patterns. And fourthly, it's helped increase and improve our research on inherited disorders. So that means diagnosis has improved. So we can find out what's wrong with people earlier, and also the treatment has improved. So in the future, it means we could use it to personalize medicine. We could use it for drug development. We could use it, and of course it does have some ethical and social implications, because if people start to understand what genes a child's going to have from beforehand, it could lead to some people wanting designer babies. It could lead to people terminating pregnancies because they don't want the child to have a certain illness. So that is covered. So this is a question, and this is a really good question. State 2 benefits that the Human Genome Project could have for medicine. This is a mark scheme that I would memorize. So locate genes associated with diseases. It helps to treat genetic disorders, and it helps to personalize medicine. Okay, thank you, Cedra. Whatever your comment means, I still appreciate it. Now, state that there is usually extensive genetic variation within a population of a species, and that these arise through mutations. And finally, 3.23. So these are going to come together, and this is linked to genetic mutations as well. So what is genetic variation? It's differences in an organism's phenotype. And what are the sources of genetic variation? So sexual reproduction, and that's because we have 46 chromosomes, but when they split due to meiosis to make either the egg cells, or they split to make the sperm cells, then we don't know which 23 from the pairs has gone into the egg cell or that sperm cell. So what you get is something completely new. Mutations cause changes in the DNA sequence. Fertilization increases variation by combining alleles from two parents. And meiosis, processes like crossing over and independent assortment during formation of gametes. So when the egg cell and sperm cell is actually made, it's a random process. We don't know which 23 chromosomes are passed on. So that means every brother and sister, or brothers and sisters, will look different to each other, but still have some similarities. So variation can be due to mutations. So what can happen? You've got your original sequence at the top there, and look what's happened. That T has been replaced with C. So now we have a different sequence. So before, remember what I said? These three code for one amino acid. This triplet here codes for another amino acid. Them three code for another amino acid. That makes a protein. But what's going to happen here is that will be the same amino acid as above, but now we've got a different sequence of amino acids, bases here. So this means this will be an amino acid, but different to this one. And that could cause a change in the protein shape. So a mutation is a change in the genetic material of an organism. Mutations occur during DNA replication or due to radiation or chemicals. So what effects do mutations have on phenotypes? So firstly, mutations happen all the time, and generally speaking, they're called neutral mutations where they don't have an effect. Because like I said, if you have a chain of amino acids, let's say one of those amino acids is different, it's not going to make a massive difference to the overall protein. Some mutations can have a small effect on phenotype, and then you have some mutations that are harmful. So that's where you have so many changes in the amino acids that a completely different protein is made. So for example, cystic fibrosis is caused by a deletion mutation. That means so I'll just quickly show you. Let's say you've got some bases here, and it's A, C, T, and G. Now let's say A gets deleted. That means everything is going to move one across. So C will go there, T will go there, G will go there. Now, if we were coding for these three to make an amino acid, now we're coding for T, G, and whatever the next one is. So now every three bases that make an amino acid, the whole gene has been disrupted. Now, if the deletion happens at the beginning of the gene, then everything gets disrupted. If it happens at the end of the gene, it doesn't disrupt it as much. So cancer is caused by mutations in genes regulating cell division. So this is the coding and the non-coding parts. So you can imagine in the non-coding part, that's the part that gives the information for how many genes should be made, how fast they should be made. So if you had a mutation there, that could either reduce the amount of protein made, but it could also increase the amount of protein made. Okay, brilliant. Thank you very much, everyone. We're going to take a break now. I really did want to finish that, and thankfully we have. So we're going to take a break and we're going to restart at 2:40. Okay, see you all in 3-4 minutes. Thank you. Okay, welcome back, everyone. We're now going to start working through chemistry topic 2. Our aim is to finish this. I know it's 61 slides, but chemistry topic 2 is probably the easiest part of chemistry paper 1. So in Edexcel Chemistry paper 1, topic 2 is probably the easiest bit. So hopefully by the end of 50 minutes, we will have this finished and we'll move on to physics for the final hour. Well, not the final hour, the penultimate hour. Then we'll have the triple award hour at 4:30 to 5:30, where we'll be covering the rest of triple award biology. So hopefully tomorrow what we'll be doing is looking at either topic 7 physics, which is purely triple award, that'll be at 4:30, or we'll be looking at topic 5 Chemistry, which is purely triple award as well. Okay, so how do we model the arrangement of particles in solids, liquids and gases? Solids are packed closely together. Let's explain better on the next slide. So we'll go straight to the next slide. People get this wrong all the time. Why do they get it wrong? Because they don't bother memorizing it. A lot of people look at it and think, oh, this is really easy. So what's the point memorizing it? Particles, and you actually just need to memorize word for word. And if it comes up in an exam, it's easy marks. So particles are tightly packed. And not only tightly packed, they are in a regular pattern and there's no gaps. Ignore the gaps bit. We don't need to worry about that too much. And liquids, particles are close together and they're randomly arranged. And in gas, the particles are far apart and they have random arrangement. Well, they have no arrangement. Now, what's the limitations of modeling particles in this way? Firstly, particles are shown as solids. Particles aren't solids because we know atoms. We know from Rutherford's experiments that particles aren't solids. Majority of an atom, because we're using particle atom here interchangeably here, by the way. Particles and atoms are the same thing. So atom here would be a better word. Atoms are predominantly empty space. We know that from Rutherford's experiments when he fired alpha particles at a thin piece of gold leaf. The particles don't show how fast the diagram don't show how fast the particles are moving, because here you'd have some slow movement. They vibrate on the spot. Here the liquid particles are moving around but within one space, so they're flowing. And here the gases will have, the particles have lots and lots of energy. Now, it doesn't show the force between the particles, because in a solid you would have covalent bonds, or ionic bonds, metallic bonds. It doesn't show the movement of the particles, and it kind of shows the particles as spheres or circles, and it only shows two-dimensional. So there's a lot of things that limit the way we present our solid, liquid and gas. Okay, so this is a big thing that needs to be memorized. In solids, particles are packed closely together. The particles in solids vibrate in their place, and solids are dense because the particles are close to each other. So they've got fixed volume because the particles are tightly packed. They cannot be compressed because the particles are already close together. You can't squeeze them any further, and they don't flow because the particles only vibrate in the place. They are part of that solid. They're in a regular arrangement. They're attached to each other with strong bonds, so they can't start flowing, moving around. They can't break free from those bonds. Now in a liquid, the particles are close together, but they can slide past each other, and that allows liquids to flow. The particles vibrate, but they also move around. Now they've said jostle here. The better, you can just say they move around, meaning they have more movement, but they're not as free as gases. And liquids tend to be dense as their particles are still relatively close together, but they're just not as dense as a solid. So they take the shape of the container. Why? Because the particles can move past each other, liquids can flow, so they take the shape of the container. It has a fixed volume because the particles are still close together, so the volume remains constant regardless of the shape, meaning it can't suddenly take up a new amount of space. If you've got a litre of water and you pour it into a bucket, what you've got in the bucket is still 1 litre of water. It can't take extra space unless you heat it up. Then it'll expand slightly and then you will have a slightly bigger volume. But this is all based at fixed temperature. And it's not easily compressed because the particles are already closely packed. So you can't really bring them any closer. What are the typical properties of solids, liquids and gases? So in a gas, the particles are widely spaced and move independently. Gas particles travel randomly in various directions at different velocities. So they move around randomly, and gases have low density because they're far apart. So why are they so widely? Why is there so much space? Why is it so widely spaced? Because the gas particles are much farther apart compared to solids, liquids, and gases. They move randomly and rapidly. That's actually because they've got lots and lots of energy. So gas particles travel in all directions. It depends on how much energy they have. But if you think about a solid, what do we have to do to turn that solid into a liquid? We have to heat it up. So we increase the energy that's inside it. Once it's become a liquid, we heat it up further, we boil it, meaning we're adding even more energy into it. So by the time it becomes a gas, it's got lots and lots of energy. And energy, so for example, kinetic energy is half times the mass times the velocity squared. So if you increase the kinetic energy, you've automatically increased the velocity. Now that's physics, but it still helps you understand this. And they can be easily compressed because you've got such a big space between the particles, you can push them closer to each other. So you push from here and you push from here, those particles are going to get closer to each other. So what are the different state symbols? So we've got solid, which is an S, liquid is an L, gas is G, aqueous is AQ. So what do we mean by aqueous? Aqueous means, for example, sodium chloride. When it's in your salt shaker, so sodium chloride is salt. When it's in your salt shaker, or whatever container you have for your salt, it is a solid. As soon as you put it into water or a liquid, it dissolves into the liquid and the sodium plus and the Cl minus separate from it, they dissociate. And we'll cover this more in topic 3 when we cover acids and alkalis and bases. So now that they're dissociated, we would now call this aqueous. So this would be, when it's in your salt shaker, it would be NaCl solid. When it dissolves, then we would write it as NaCl aqueous. So physical changes. Melting point is when the substance turns from a solid into a liquid, and boiling point is when it turns from a liquid into a gas. Now, to change state, what do we have to do? We have to break bonds. So in a solid, we've got to break bonds. And if we want to go from a liquid to a gas, we're going to break all the bonds. And that requires energy. And that's why gas has the most energy. So what happens to the mass when a substance changes state? It's a physical process. If it's a physical process, what we mean by that is if if an ice cube melts and turns to water, or if water boils and turns to a gas, we can reverse that process. So gas will become water again, water will become ice again. But if we measure the ice and it weighs 5 grams, afterwards, when we turn it to a liquid, it will still be 5 grams. When we boil that water, how much gas will we have? 5 grams. So the mass doesn't change because it's a physical change. We know it's physical because it can be reversed. If it cannot be reversed and something new is made, then we would say it's chemical. But the whole point here is when it's ice cube, it's H2O. When it's a liquid, it's still H2O. When it's a gas, it's also H2O. What's the only difference? We put a little S there for solid, we put a little L there for liquid, and we put a little G there for gas. So, internal energy. Internal energy is the total kinetic and potential energy within the particles in a system. So this is overlapping with our physics content. What would happen if a solid was heated? So when you start heating up a solid, so there's our solid, we've got our particles. If the temperature is increased, the particles move faster as they gain kinetic energy. So what I said to you guys before, kinetic energy equals half times the mass times the speed squared. So if you increase the energy, kinetic energy, you're not changing the mass. Mass stays the same. So what's the only thing that can increase? The velocity. And that means the internal energy increases because we've now increased kinetic energy. And if it gains enough energy and those particles vibrate enough, the bonds holding them together start to break. And if enough bonds are broken, it'll go from solid to liquid. If it's a liquid and if enough bonds are broken, it'll become a gas. So what will happen if this solid were heated? So this is just what we've just said. So I'm going to move on. Okay, this is something that's really important that we understand. It always comes up in Edexcel papers. It can come up as a 1 mark, 2 mark, 3 mark question, but it's poorly done. Now at room temperature, now this says room temperature is 25 degrees. Usually room temperature is 20 degrees, but let's just use the number that's there, 25 degrees. Now, we're now assuming we've got some fluorine in a test tube and it's 25 degrees. Meaning, if it's 25 degrees, have we gone past its melting point? Yes, we have. Let me highlight this instead. Yes, we've gone past minus 220 degrees. Have we gone past minus 188? Yes, we have. That means it's melted and it has boiled. So we have a gas. Chlorine, 25 degrees, it's definitely gone past minus 101. It's gone past minus 35, so it's melted and it has boiled. So yep, we've got a gas. Bromine, minus 7 degrees, it has melted. So 25 degrees is past that point. But at 59 degrees, have we reached 59 degrees yet? No, we haven't. It's only 25 degrees. So that means we've melted the bromine, but we have not boiled it at 25 degrees. It's going to be a liquid. Water, at 0 degrees, it melts, but we're at 25 degrees, so we've gone past 0, so it has melted. But it has not boiled because we've not reached 100 degrees yet, so it's a liquid. Mercury, minus 39 degrees, means that the melting point, we've gone past that. But have we reached the boiling point? No, we haven't, so it is still a liquid. And sodium, which is a group 1 metal, 98 degrees. Have we reached 98 degrees yet? No, we haven't, because it's only 25 degrees. So we haven't melted, we definitely haven't boiled, that's 883 degrees. So it's going to remain a solid if it's not melted yet. So I hope that makes sense. Try some past paper questions on this, make sure that you understand. Okay, what do we mean by pure? When we say something's pure, we actually mean that there's only one thing there. So if we said pure water in this beaker, I'm just going to draw some circles. These circles represent water molecules. There's nothing there except water molecules. In other words, there's nothing there except H2O. If I said this bar of gold, right, I was just trying to draw gold, never mind. After 4 days, you probably realize that I'm not very good at drawing. So, this is a gold bar. What's the only thing inside that gold bar? It is gold. It only has gold atoms, so it's pure. Now, so either we can have the same compound over and over again, or we can have the same element over and over again. Now, when you've got something that's pure, it has a fixed melting and boiling point. So on a graph, it shows itself as a pure substance will, sorry, I'll come back to it. A pure substance will look like this on a graph. Straight line. That straight horizontal line represents when it's melting or boiling, and it only melts or boils at one temperature because there's nothing else there. When you've got a mixture, then it'll look like this because you've got a range of melting and boiling points because you've got a mixture there. So let me rub this out and talk through this. We can use melting and boiling points to tell if something is pure or a mixture. So if it's got one distinct melting and boiling point, what does that tell us? It tells us that it is pure. If it's got a range, then that tells us that it is impure. It has some impurities inside it. So in everyday life, a pure substance means something that has nothing extra added to it. It is in its natural form and not changed. So pure substances have fixed melting and boiling points. Example, milk. So look at this graph. And this is now on a separate topic. This is what we need to understand. So let's understand this graph in its entirety. So that initial line, let me highlight it so you know what I'm talking about. This initial line here, temperature increases with time. Now this line here is where the temperature stays the same. Now that doesn't mean that we've stopped heating the thing. It just means all the heat energy. So let's say we've got an ice cube. What's happening in that second line, that flat line, is that all the heat energy, so the Bunsen burner is still on. Okay, that's a terrible Bunsen burner, sorry. The Bunsen burner is still on, but all the heat energy is going inside the ice cube, inside the solid, to break the bonds. So what's actually happening here is melting or boiling. So the substance is changing state, and then once it's changed state, the temperature keeps increasing as it was over here. So when you see that flat line, what does it mean? What does the horizontal line mean? It means that all the heat energy is going inside the solid. It's going inside so to break the bonds so it can melt or boil and change state. So now this is what it's going to look like if it's a pure substance. It is horizontal line, just one temperature. Whereas here, you've got a range of temperatures. So it melts at one exact temperature when it's pure. When it's impure, it melts over a range of temperatures. So that shows us it's a mixture. That's why in the winter we put salt on the ground, because that salt turns the ice into a mixture and it lowers its melting point. So it melts at a lower temperature. Otherwise it would stay icy. Okay, separation techniques. Now, if you do end up with a mixture, you need to know all the different ways to separate it. So if you've got an insoluble substance, if you have some, for example, you've got a beaker, and inside here you've got water and you've got sand. Now this is where the highlighter will look good. We've got a bit of sand inside the water. The rest of this is water. How can we separate it? We've got an insoluble substance, which is the sand, because it doesn't dissolve in water. I think 1 grain of sand will dissolve in 1 liter of water. So you still class that as insoluble. So the insoluble substances are trapped by the filter paper. So as we go here, all the sand will get trapped here. But the water will go through. So you can use filtration. So filtration separates an insoluble solid from a liquid using filter paper. For example, removing sand from water. Here is our next one. Crystallization. So the solution, so this is, for example, you've got some salty water. Let's say seawater. So seawater is salty. Here's our seawater inside our evaporating dish. So the solution is heated to evaporate some of the liquid, making it more concentrated. It is then left to cool. So what happens is you've got your water in here and you evaporate off most of the water until you get to a point where you've only got a small amount of water left and it's full of salt, and you can start to see the color change. It's become a little bit thicker. You can tell because what you do is you get a splint or some sort of stick, put it inside, and if you can see crystals forming on top of the splint, you know you reach crystallization point. At that point, you just go to a windowsill and leave it there, and then the water evaporates. And when you let it cool and evaporate slowly, you get much larger crystals. But what you've done there is you separated the water and you've separated the salt. Okay, now here's our next technique, which is simple distillation. And in simple distillation, we have to do 2 processes. We have to evaporate or boil the water. So what we've got here is 2 liquids. Now the thing with those two liquids is one has a lower boiling point and one has a higher boiling point. The one with the lower boiling point, once you start heating it, starts to evaporate, and then it makes its way down this tube in the middle. Now when it's in this middle part here, we've got water flowing. This thing's called a condenser. Now the tube's in the middle of that condenser, so this water flows around the outside. So this cold water flows through the condenser and it comes out from this side. As the cold water flows through, it absorbs the heat energy from the gas, the vapor, the gas particles, and it condenses it. So now what we've got coming out from this side is a liquid, and it fills up the tube on the other side. So now we've got our liquid that had a higher boiling point over here, and over here we've got the one with a lower boiling point. So we've separated the liquid. So it can be used to purify water from salty water, but if you had, for example, water with ink inside it, you can separate the water and the ink also. Next one. So many separation techniques. Okay, next one. This one we will cover in a lot more detail in paper 2 when we cover organic chemistry. And we talk about how to separate crude oil. So right now, it can come up in paper 1, but it won't come up in as much detail as it is likely to come in paper 2. And although this is a foundation and a higher topic, it usually comes in foundation papers. Well, this element of it does. That does not mean though that it won't come in a higher paper. So fraction distillation, this method separates liquids in a mixture based on their boiling points. So you take a mixture, so that means you could have 4, 5, 6 different things in there. You turn it into a gas. The gas starts diffusing upwards. As it does, hot air rises. Now, each one has a different length. The mixtures are different sizes. So you might have, they're all made of carbon. So you might have one that's got 60 carbons. You might have a slightly smaller one with 40 carbons, another with 20 carbons. So the one with 60 carbons is going to become a liquid and condense at a higher temperature. So when it becomes a liquid at a higher temperature, it's siphoned off. Then the one with 40 carbons is going to become a liquid at a slightly lower temperature. So that becomes a liquid here. The one with 20 carbons might become a liquid here. So now we've separated them. Now, the carbons I put there are not accurate. When we cover it in paper 2, I will go over it in more detail. And when are we going to cover paper 2? We will be covering in AMALathon 2. So in May, we'll be doing 3 pre-exam workshops. That means the weekend before every single of your exams. So biology paper 1, chemistry paper 1, and physics paper 1. I will be going through lots and lots of past paper practice to get you prepared for the exam. And the past paper practice will be linked to my analysis of the exam papers. And then in the May half-term holidays, I will do another AMALathon like I've just done now. I'll do a marathon of learning. I'll do a full 18 hours where I'll cover biology paper 2, chemistry paper 2, and physics paper 2, just like I'm doing right now. And then in June, the weekend before your biology paper, your chemistry paper, and your physics paper, I will go through past paper questions, again based on my analysis. And usually I'm around 80% correct. It would have been nice if I could have got some of my ex-students to come on so they could explain to you the process, the AMAL process, why it works, and how they got really good grades. In the future, we will have a few students that have already come forward, particularly the ones that I tutor. So hopefully there will be some kind of testimonials made at some point. Okay, so I think actually a few are already on the website. If anyone needs credentials or needs evidence, you can check what's on the website. Now, chromatography uses a moving liquid, the solvent, and the stationary solid, as in that's the stationary phase, the paper, to separate substances. So let's go through this one step at a time. Chromatography will come up in a lot more detail, so I'll come back to that. So what is chromatography? You need to remember both phases. The mobile phase is the water, and as it is soaked up by the stationary phase, the paper the water makes its way up to the top. The same way if you have a spill in the kitchen, if you get a piece of tissue, what happens? The water moves into the tissue. So it's a capillary effect, is known as. Chromatography is used to separate different substances in a mixture, like dyes in ink. Chromatography separates mixtures because different substances are attracted to the stationary phase, the paper, and mobile phase in different amounts. This makes them move at different speeds, allowing us to identify them. Okay, so let's just go through this one step at a time. We've got our mobile phase and we've got our stationary phase. As the water, firstly, see that line there is drawn with pencil so that it doesn't dissolve. Then you get your different colors, or get your whatever liquid it is that you're trying to identify, and you put dots of them on, a few dots of each on that pencil line. Now, as the water rises, depending on how much those liquids are attracted to water in this case, because you can use water, alcohol as your mobile phase, you can use different liquids. They dissolve into the liquid, and the liquid carries them up. So the liquid, the water in this case, will go all the way to the top, so possibly up to here. However, as those dots that you put in dissolve into that liquid, they'll get carried up to a different point. Now so for example, that first dot might only go up to here. The second dot might go up to here, but it might be made of multiple colors, so it might split up into those multiple colors. And then we can use that to calculate and find out something called an RF value. And using the RF value, we can work out what substance it might be. So chromatography is a method used to separate different substances in a liquid, in a mixture, often dissolved in a liquid. And stationary phase is the part that does not move, and the mobile phase is the part that does move, usually a liquid. So here we go. What do these results show? Chromatograms help us identify substances in mixtures. Now, until students don't understand this, this is one of those topics, for some reason, in my 15 years of teaching, in mock exams, students do really poorly. But I always make sure I go through it in a lot of detail just before the exam, because as soon as it clicks and people understand how to do it, it's a really straightforward topic. Okay, so and we're going to do that now. This is the part I was trying to show you, and it's a core practical. But I've kind of gone through this, but let's just go through this one step at a time so that we can really truly understand it. And then the RF value comes in 2.12. So first thing you do is you draw your pencil line towards the bottom and you add small spots on it. Now you place the chromatography paper into a beaker. Now you make sure the bottom edge is in the solvent, but you make sure that this line with the dots on is not inside the solvent. Now, whoops, I've not explained the mistakes as well. Now, because it's a core practical, what can happen is when you get asked questions on this, you might be asked, how can you improve it, or what mistakes were made? And I've seen questions where they've asked about mistakes. So if the ink spots are below the solvent level, they'll dissolve into the liquid. So you have to make sure the ink spots are above the solvent. If the ink spots are too close together, the colors might mix. So you've got to make sure that doesn't happen. And then you place the chromatography paper in the water. And notice the water line, the water level is below the pencil line and the inks. Now if the spots touch the solvent, these inks will dissolve into the liquid instead of going up the paper. And that ruins the separation process. Now, you let the chromatography paper absorb the solvent until the liquid reaches near the top. Measure how far the solvent has travelled from the starting line, and measure how far the middle of the sample spot has moved from the starting line. So what you're doing is, the solvent you measure the solvent from that line to where the solvent goes up to, which is here, and you measure the ink spot from that line up to the middle part of the dot there. So you've got two measurements, this measurement and this measurement, which has already been shown, so I'm just going to delete that. So now what we do is RF value is the ratio of how far the dye moves compared to how far the solvent moves. So it's a ratio, and it's the distance the dye moves divided by the distance the solvent moves. So in this case, the solvent has moved 8.4 and the dye has moved 8.4 and the solvent has moved 12.2. So we divide them and we've got 0.69. Now in literature, as in scientific literature linked to chromatography, you can look it up and find out in water what has an RF value of 0.69, and then you've got an idea of what substance it might be. Okay, what is potable water? So potable just means water that we can drink, or water that's safe to drink, so it's clean. It doesn't mean it has to be pure, because pure means it would only have H2O in it. It means it's clean, so it can have minerals inside, which are absolutely fine. So the water that we drink is full of minerals, and that is absolutely fine. We can drink that because it's full of minerals. It's not pure, but it's clean. So what is potable water? Potable water has small amounts of dissolved salts and only a few microbes. So meaning we're not going to get ill when we drink it. It's not pure water because it's got dissolved minerals inside it. So pure water is only H2O. So how do we obtain potable water? We obtain potable water from salty water and fresh water. So we can get it from the sea, but the problem with that is it's got loads of salts inside it. Or we can get fresh water from rivers, lakes, or rain, which has little or no salt. Little bit of salt is not a problem, but the seawater is a problem. But it just depends what resources a country has. So for example, if you're looking at United Kingdom, or you're looking at England, Scotland, or Wales, or Ireland, they've got lots of natural rivers, natural lakes, and plenty of rain. Particularly if you're from where I am from, which is Manchester, lots of rain at certain times in the year. Which means they've got fresh water supplies. So all they've got to do is clean out, filter out. So they've got to, and this is the process, they've got to filter. Oh, I'm using the wrong pen. They filter out all the twigs and leaves and all that kind of stuff. Then they put in a big container. Now this is more of a foundation question, and it's called sedimentation. I don't think I'm going to fit it in there. Sedimentation. That says sedimentation. So at that point, all the sediment starts to drop to the bottom. If you leave it long enough, that means all the little bits of dust and dirt and little stones, they drop to the bottom. And after a few hours, when you come back, all the sediment is at the bottom and all the water's at the top. Then finally, you blast it with, well, you adding a little bit of chlorine, and the chlorine kills off the germs. And now it is clean and ready to drink. Now you can either use chlorine, and we call that chlorination, or we can blast it with a bit of UV rays, ultraviolet radiation, and that also causes the germs to die. However, that's more expensive. Now with salty water, that's usually in countries where there's no rivers. So an example would be Saudi Arabia. There's no naturally occurring rivers. They do have the well of Zamzam, but in terms of parts of Saudi Arabia, because it's quite an expansive area and it's quite a lot of desert, they don't have access to that Zamzam everywhere. So what some coastal cities do there is they use filtration. distillations. Either use distillation, where they boil the water and then condense it, leaving the salt behind, or they use something called reverse osmosis. So all this stuff should be coming up. So how can we obtain potable water? So from fresh water, you pass the water through a filter to take out the dirt and bits. Then, after that, we do sedimentation. Then we kill the germs using ozone, UV light, or chlorine. Usually in this country it's chlorine. That's the stuff that you can smell when you go to the swimming pool. And how do we get from salty water? We can remove salt from water by heating it up and collecting the steam. In other words, simple distillation. Or we can use something called reverse osmosis. Now, but both ways need lots of energy. Now, reverse osmosis, we'll come to in a second. What happens during distillation to obtain pure water? So it's what we covered before. This is water and salt. So you boil it. I have a Bunsen burner here. That looks more like a candle, but I suppose you could use a candle. The water evaporates. Over here it's condensed. So it's boiled, then it's condensed, and then pure water is collected on this side. Over here you're left with salt. So you can use simple distillation, that's one way. That costs a lot of money because you need energy to heat something up. Or now we can explain how we obtain water from groundwater and salty water. So we've already explained all of these now, but I'm just going to very quickly explain to you how reverse osmosis works. So with reverse osmosis, remember, if you think back to osmosis is the movement of water from a region of high water concentration to a region of low water concentration. Now, I'm actually going to draw this again. No, I won't draw it again. Now I'm going to add some red dots. And what these red dots represent is the red dots represent salt, and these blue dots represent water. So I've already drawn some water circles, but I'm replacing that with these blue dots now. Now if you look at this, where is there more water? On the left hand side or the right hand side? There's more water on the left hand side. Now osmotically speaking, or speaking from an osmosis perspective, which way is the water going to go? It's going to go from a high water concentration. In other words, it's going to go from dilute to concentrated. But that's not really going to benefit anyone. Why won't it benefit anyone? Because now what have you got? You've got salty water still. So what actually happens now, one thing I've not shown in this diagram is that the salt is much bigger. The salt crystals are bigger than the water molecules. So what happens is, like this kind of, the pressure is increased, so almost like a plunger. And that plunger forces the water through these gaps. So all these little blue dots are forced through the gaps, and what's left is the red dots on the other side. So the water gets forced to the other side. So it's a little bit like you're actively transporting the water. You're forcing the water through those gaps, leaving the red dot salts. Obviously they're not red in real life. I'm just showing that as salt, leaving the salt behind. So what's in wastewater? So cities and factories make a lot of dirty water that must be cleaned before it goes back into nature. So dirty water from toilets and farms need to have germs and waste removed. And factory waste water may also need harmful chemicals removing as well. So how's this water treated? The dirty water is first filtered to remove big bits like grit. Then the water settles, so the heavy stuff sinks. So similar to what I was saying before, first you filter it, then you put it in a large container and you allow the sludge to go to the bottom. That sludge then can be anaerobically digested. And when it's anaerobically digested, it turns into fertilizer. So to sell that fertilizer, that's Essentially, that's everyone's feces and solid bits that come through the toilet. And the light stuff stays at the top, so that's more urine and water and the lighter stuff. The sludge is broken down without air anaerobically and then sold. The effluent is cleaned using the air. So actually what's happening there, if you look at it, the sludge is broken down anaerobically by bacteria. So all the feces are being broken down into nitrates. And the effluent is being broken down by bacteria, again, which cleans it up. So describe what different parts of the sewage are and how they're processed. The sludge, the solid material that sinks to the bottom during sedimentation. That's what it is. How is it processed? Is anaerobically digested. So this is exactly what was on the previous slide. It's just a summary slide. And effluent is the liquid that remains at the top. And that's biologically broken down by bacteria using oxygen. So sludge is anaerobically digested and effluent is aerobically digested, both by bacteria. So how can we determine if water is pure? So what we've already said before, but this just comes up again in this topic. Pure water boils at 100 degrees. But if the water is not pure, we can do this experiment. And we can do this experiment to find out if it is pure. So you weigh the empty evaporating basin, add water to the basin, we heat the water until it evaporates. Now look, it weighed 58.32 grams. If the water is not pure, if the water is pure, it'll still weigh 58.32 grams once the water evaporates. If it's not pure, then it'll leave the salt crystals behind and it'll weigh just that little bit more. After the water's gone, you'll see solids like salt left in the basin. This shows the water was not pure. And look, the mass has gone up as well. Now, what are the possible sources of error when analyzing water samples? Now, these kind of questions, these kind of slides are important because it helps us to understand thinking out of the box type questions, which is a common occurrence, common type of question. Each tool you use measures something. Each tool you use to measure something can cause errors. So you can either have a random error or a zero error. So a random error is when measurements change slightly each time, even though you do the same thing. So that's usually a human error. A zero error is an error with your actual equipment. So for example, it could be that your weighing scales are 0.03 grams off or 0.2 grams off. So in that situation, all you do is whatever your answer is, you just take off that error. Now, when your equipment doesn't show 0 at the start and it's giving a wrong reading, that's a zero error. So for example, it's saying 0.12 grams before you even started. So all you do is you just take off 0.12 grams from your final answer. And what is parallax error? Now, this is something that I've added. It's not something that specifically is needed to be known in the Edexcel specification, but it can still come up as part of an answer. Now, you won't have to say the word parallax. So the word parallax doesn't come in Edexcel, but the understanding does. And the understanding here is that if you look at something from above, then, so when you're trying to find out, for example, how much liquid is in that cylinder, you have to get at eye level. So that means you might have to get on, like, kind of bend your knees a little bit, bend down, so you're in eye level, and you can see that that's the reading. But now if you look from above, you're going to take the reading as there. If you look from below, you're going to take the reading as there. So it's important to take the reading at eye level. Okay, excellent. Right, so that is the end of topic 2. So tomorrow we're going to start chemistry topic 3. Now, chemistry topic 3 and chemistry and parts of chemistry topic 4, I would say are possibly some of the more difficult topics. Not difficult, they're topics that just need to properly understood. And if they're properly understood, it becomes a lot easier to answer questions. With chemistry, the reason why students don't do as well as they should sometimes is because of understanding. If you understand it, it opens up the questions so much more. So tomorrow we'll start topic 3. Hopefully we'll finish topic 3 tomorrow. We're going to do our best to. So we're going to have a break now and we'll be back in 4 minutes. So we'll be back at 3:30. Thank you, everyone. Okay, welcome back, everyone. Welcome back, everyone. Let's start the final session now. So this is the final session for those that are doing combined, and let's start working on, let's finish topic 4, physics, which is the topic of waves. And it's not the biggest topic, but it does need to be understood. So hopefully we'll have this completed and understood by the end of the hour. So what are waves? Waves are repeating disturbances or vibrations that transfer energy from one place to another without the net movement of matter. So the main thing here is what waves transfer is energy, and they transfer information, but they do not transfer particles or matter. And how can we prove that a wave is traveling itself and not, for example, and not water? So we can prove that the wave is traveling and not the water itself through a simple floating object experiment. So if you take a small object like a leaf, a cork, or a paper boat, or a rubber duck, and place it on the surface of still water. Now, if you create ripples by tapping or dropping a pebble into the water, then look at the actual movement. So what we're saying is, you get a nice big bowl. It's got water inside. Put your whatever it is in the middle and just cause the water to move a little bit. Now, as the ripples go through, what you'll notice is the object will move up and the same object will move down. So depending on where it is on the wave, but it won't move position. It's not going to move left to right. It's just going to move up and down depending on where it is. So you create ripples by tapping or dropping a pebble in the water and observe the object's movement. The object will move up and down. They'll oscillate, but not travel with the wave. And yeah, so there's just a question. Yeah, chemistry is finished. We've now moved on to physics. So observe the object's movement. The object will move up and down, but that means the energy is moving through, but the particles themselves, they oscillate, they vibrate up and down, they move up and down, but they're not actually moving across themselves. They're not moving from place to place. So the conclusion from that is the wave moves across the water, the energy, but the water particles themselves do not travel forward. Instead, the water particles oscillate, they move up and down in their place, transferring energy without actual displacement. If you think back to what displacement is, it's how far something has moved from its original place. That proves that it is the wave energy traveling and not the water itself. So now key terms when we're talking about waves are the crest. So this is the crest. This is the crest, just there. The trough, which is the lowest point. The wavelength is the distance between two consecutive crests or troughs. So I'm just going to change the color so I can show you. So for example, if I go from here to here, that's the wavelength. Or I could go from here to here, that's the wavelength. For myself, and another easy way to do it is from here to here. So that kind of upside down S shape. That's a wavelength. And then we've got amplitude. The amplitude is the maximum displacement, as in how far it moves from its rest position. So the amplitude is from, this is the rest position to the top, or the rest position right to the bottom. So as in from the rest position up to the crest, or the rest position down to the trough. And the last one is frequency. So that word there is not needed. Frequency, the number of waves passing a point per second. That's measured in hertz. And wave speed. When we calculate the speed of the wave, we do the frequency times the wavelength. Now wavelength, the symbol for wavelength, although it's measured in meters, we put this, the symbol used is lambda. So what are the different parts of a longitudinal wave? You've got compression. which is a region where the particles are close together. So there's your compression area there. And that creates a high pressure area, and a rarefaction, that's the bit in between. So you've got, I'm putting the compression as the blue bits, and the bits in between are rarefactions. That's where particles are spread apart, creating a low pressure area. The wavelength is the distance between two consecutive compressions or rarefactions. So this would be the wavelength from here to here. From here to here. Amplitude, you don't need to actually identify wavelength, amplitude or frequency of sound waves or longitudinal waves, so we're gonna move past this. It's the extra information for those that want it, but that's not the part that you need to know. Okay, we've covered this already. Frequency is the number of waves per second. So if we count them here, if we start from here, 1 wave, 2 waves, 3 waves. So this is 3 hertz. Assuming that at this point here, that took 1 second. Now, assuming this point here is 1 second, because remember, it's the number of waves in a second. So now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 waves, 1.5. So we can call that 11 hertz or 11.5 hertz, because that's the number of waves we have per second. Now, period is the time taken for one complete wave to pass a point. So if your frequency is 11 hertz, period, which is t, will equal 1 divided by the frequency. So if it's 11 hertz, it will be 1 divided by 11. If it's 3 hertz, it'll be 1 divided by 3. That's the time taken for 1. Now, definition of transverse and longitudinal waves. A transverse wave are they're waves in which particles of the medium move perpendicular to the direction of the wave's propagation. So what that means is, if the wave is traveling this way, so that's the wave's propagation, that's the direction the wave is moving, then as it goes through particles, and they gain some energy, the particles vibrate up and down. And if you look at that as an angle, that's 90 degrees, which means it's perpendicular. These waves consist of crests and troughs, so it looks like this. So examples are light waves, and light waves and radio waves are both electromagnetic waves. All electromagnetic waves are transverse. Water waves are transverse waves. Seismic S waves. So these are your secondary waves that are caused during earthquakes. All of these are transverse examples. Now, here's your key differences between a transverse wave and a longitudinal wave. So this is something I would advise that you learn. Particles move. So in a transverse wave, particles move perpendicular to the wave's direction. In longitudinal waves, so if the wave is moving this way, when it goes through particles, the particles vibrate back and forth. In other words, parallel. The wave structure, it consists of crests and troughs because it's like this. So you have crests at the top and troughs at the bottom. Whereas in longitudinal, you've got regions of compression. So when you're talking, if you pass on energy from your mouth to the particles next to your mouth, then those particles pass on that energy to the next particles, the next particles, next particles, until it reaches someone's ear so they can hear. The bits in between are called rarefactions. Rarefactions are the points when we're not really talking. So we're not passing energy on to the particles. Medium is the medium required. Now, transverse waves can travel through solids and on surfaces, but they can also travel through a vacuum. So the main thing here is vacuum. They can travel through space. So if you think about light, it travels all the way from the sun travels all the way from the sun, but it travels through that empty space. It travels through the vacuum, so it doesn't need particles to transfer it. Whereas longitudinal particles have to travel through solids, liquids and gases. The more particles, the better, so it travels best in solids. And here we've got some examples: light waves, water waves, EM waves. And longitudinal waves, we've got sound waves, seismic P waves and ultrasound waves. So I'll give you an example. If for example, let's see, I'm talking, or this individual here is talking. Oh, that's really badly drawn. Let's put hair there instead. Okay, let's lower the nose. No, it doesn't matter. It doesn't need to be worked about. That's the person. Right, so they're talking. The energy that comes from their mouth, it causes the particles to start vibrating. Now they collide into the particle next to them, and because they've collided with the particle next to them, what happens? They start vibrating. They cause the next set of particles to vibrate, and the next set of particles to vibrate, and the next set of particles to vibrate. Now, let's say, oops, I've removed the person. Keeps changing slides. Now let's say the person's talking. The particle energy is going to keep moving across. But the second the person stops speaking, then the energy is no longer being passed on to particles. The energy doesn't pass on to particles. So at that point, your normal air is moving around. So you end up with gaps in between the points where you've spoken. So now when I'm speaking, I'm passing on energy to the particles, which are passing on to more particles, onto more particles. But when I stop talking, that moment of silence, I'm no longer passing energy on, so you have an area of rarefaction. So how do we calculate wave speed? V equals F lambda. Wave speed, V equals frequency, F times wavelength, which is lambda, the Greek letter lambda. And here's our units: wave speed in meters per second, frequency hertz, which is the number of oscillations or number of waves per second, and wavelength is in meters, and that's measured from trough to trough, as in sort of peak to peak, or trough to trough, so the bottom bit to the bottom bit. Now, the speed of a wave depends on the medium it's traveling through. Sound waves travel faster in solids than in liquids and gases, and light waves travel fastest in a vacuum and slowest in denser materials like denser materials such as glass or water. So light waves travel fastest in a vacuum but slowest in denser materials like glass or water. And that's where refraction occurs. So refraction is something that will come up as a topic, and we will go through it. Another way of measuring speed, wave speed, is distance divided by time. Okay, exam style question. Actually asked for some more exam questions, and we've got more exam questions. So, calculate the frequency of a wave when the wave speed is 12 meters per second and the wavelength is 12 millimeters. So what's the first thing we've got to do? We need to convert the units. So convert the 12 millimeters into meters. So when we go from millimeters to meters, we're going from small unit to big unit. So we're going to divide by 1,000. Now, if anyone's still struggling with converting units, if you watch the AMALearning animation, I think it is specification, it's specification 1.4/1.5. If you watch the animation, I think it's possibly a 3-4-5 minute animation, and it will help you understand how to convert one unit to another unit. So I would really advise that you watch that one. It will definitely help. Then we write the formula. V equals F lambda. V equals velocity. Wave speed equals frequency times wavelength. Now let's rearrange this because we're trying to work out the frequency. So if you're using a triangle, V goes at the top, frequency and wavelength go at the bottom. So frequency is going to equal V divided by lambda. So frequency will equal wave speed divided by the wavelength. So let's do the maths. 12 divided by 0.012. So the frequency is 1000 hertz. We've already rounded it. We've already added the units. So here's another one. If you're able to answer quicker than I'm going through it, you are more than welcome to have a go. So a wave travels at speed of 340 meters per second and has a frequency of 1700 hertz, 1700 hertz. So this time we've got wave speed and we've got frequency. So here's our triangle. Velocity at the top, frequency and wavelength. And this time we're trying to work out a wavelength. So it's going to be velocity divided by frequency. So no conversion needed. Write the formula. There we go. Substitute the values. Well done. Thank you, Akshat. 340 divided by 1700 and do the maths. It's 0.2 meters. We've already rounded it, or we've already written down the units. So wave speed. Now, how can we measure the wave speed of sound waves in the air? We can use the echo method, which is not something we need to worry about. The method that we need to know about is the starter pistol method. So there's a few different things written here. If I shouldn't have really scribbled over the top. And the way it can be done is to measure the speed of sound in air. One person fires a gun, like a starter pistol, not a real gun. That looks more like a water gun. I'm not sure what I've drawn there. That's fine. It's supposed to be a starter pistol. And as soon as they fire the starter pistol, they put their hand in the air. And the second their hand goes in the air, there's a person 500 meters away. As soon as they see their hand go in the air, they start a timer. And the second they hear it, the second they hear the sound, they turn off, they press the timer again. And that means you've got a distance and you've got a time. Now this is highly inaccurate because of reaction time. You can use a loudspeaker and a microphone, but still the problem is with this whole experiment is that reaction time is about 0.3 seconds. So you react when you click it initially, you react when you click it after. So instead, and all that ends up happening is you end up clicking it twice. Like consecutively, it's like click, click, and you got the time in between. So it is a difficult thing to do. So waves behave in specific ways. So one is they transmit. Now when transmission happens, that means they go straight through. We have absorption, so that means they're absorbed, and that stops the energy. We have reflection, so for example, it bounces off a mirror. And we have refraction. So refraction is when the light changes direction because the speed has changed. And when it slows down, it bends towards the normal. And when it speeds up, it bends away from the normal. Okay, refraction. Yeah, and as it's mentioned in the live chat, the best way to do that experiment is to use an automatic timer. So to use similar, you can use computers which have microphones attached to them, and they record the time. So that can be done, and that's a much better way. Now, by the way, we're going to cover this topic up to 4.16. 4.17 is a required practical. The best way to cover 4.17, as I've said to you guys before, that's the kind of required practical where to understand the theory, to understand the actual practical, you need to visually see the practical. So if you go on YouTube and you write Edexcel and waves practical, you will find a video. I think it's around 10 minutes. It's 2 different required practicals. So after this finishes, I would advise you spend 5-10 minutes watching that video, and it's been made by the exam board, so they've covered it in a way that suits the way they're going to ask questions. They're not going to spend money and resources making something that they're not going to end up asking questions about, or they're going to make it in a way that helps you answer the questions. So please watch that. So I'm going to go up to 4.16 and 4.17. Please watch that video. Now, refraction is the change in direction of a wave as it passes from one medium to another due to the change in its speed. Now, one thing I want to just explain to you before we continue here. If, let's say there's 3 people walking, and I'm just going to draw circles for their walking, and they're all holding hands. Okay, they're walking in this direction. Now, initially they're walking on the pavement, but when they reach this line here, it becomes muddy. Now, what happens to our speed? What happens to our speed when we're walking through the mud? We slow down. That's correct. Now, if we've slowed down, so imagine now we're walking. At this point here, we're still on the pavement. All 3 friends are still on the pavement, meaning they're all still moving at the same speed. Now, as soon as we get to this point here, one friend is now in the mud. So what's going to happen to that one person's speed? That one friend's going to move slower. Now, if you've ever held someone's hand and one person's walking slower, what happens to the other person? They start moving inwards. So now, because this person was walking slower, the other friends have moved inwards. So now when they're walking in the mud at the same speed, they're walking a completely different direction. And that's what happens in refraction. Your light comes at an angle like this, but the bit of the light that enters first slows down, so it drags it inwards in one sense. It causes it to change direction. So now it refracts and it goes inwards. So when it goes from less dense, which is the air, into more dense, which is the glass, it bends inwards because it's slowed down. Then on the way out, it speeds up again. So it bends outwards. Because the one on the outside, this one, speeds up first. So it starts pulling them this way. Now, one thing to note is the line that I've just drawn here, the first line, so let me highlight it. This one and this one, they're parallel. So they need to be drawn in a parallel. They have to be drawn in a parallel way. But can you see how they aren't in line with each other, but they are parallel? So I hope that helps understand refraction a bit better. It slows down, it moves inwards. So when it goes less dense to more dense, it slows down and it moves inwards. When it goes from high density, so the glass, to the air, it speeds up, so it goes outwards. It refracts, bends, the light changes direction outwards. So when it slows down, it bends towards the normal. For example, from the air to water. When it speeds up, it bends away from the normal. For example, when it goes from the water to the air. This happens with light, sound, and water waves. The bending depends on the refractive index of the material. So it depends on how much it's going to slow down. No, sorry, it depends on the material. So the denser it is, the bigger its refractive index. Refractive index just means how much it's going to refract it, how much it's going to cause it to bend. So what happens, I've already explained, but let's go through this. When light enters glass, it slows down and so changes direction. It bends towards the normal. So this is a very good slide to memorize. This shows how all the energy in a system is transferred at different stores. You don't need to worry about this too much, as in from a question perspective, you won't get a question on this. So when a wave crosses a boundary, now one thing I should point out, this line here, that's a boundary. A boundary means when it goes from one material to another material. So in this case, it's going from air to glass. So when a wave crosses a boundary at a non-zero angle to the boundary, each wavefront experiences a change in speed and direction. So you can see this part of the wave is slowing down, this part of the wave is slowing down, and hence it all changes direction. In the diagram, the wave has slowed down, and so the refracted waves are closer together, and that's another thing that happens. The waves become closer to each other because they've slowed down, and they're at a smaller angle to the boundary, so the angle changes than if we look at the initial wave. So this is what we have already covered, but it's the best way to explain this as well. When you change the wavelength of something, depending on its wavelength, it can either get absorbed, reflected, it can just transmit, or it can be refracted. So converting sound waves, how is it that we're able to hear? Now 4.12, right, apologies, just 1 second. No, I'm sorry, I'm looking at the wrong information. Yeah, 4.12, converting sound waves. Yeah, sorry, if you can excuse me just for 1 second, I just want to check something. Because I'm... Yeah, I thought so. Apologies. This is a triple only topic, as were this 4.8, 4.9, but it's still relevant. 4.10 was fine, 4.11 is fine. Okay, 4.12 is triple, 4.13 is triple, 4.14 is, 4.15 is, 4.16 is triple, and then 4.17, as I advised, it's best to go through using the actual video. Now at this point the combined section is finished, so if anyone's on combined, I just want to say a really big thank you for logging in today, watching us live. And what I would advise you, for those that are live and those that are watching afterwards, is the AMAL method. I can't reiterate enough. Activate it, activate your brain, memorize, and after you've memorized it, alongside memorizing, lots and lots of past paper practice. So apply. So it's lots and lots of activate your brain, understand everything, make sure you've understood, make sure you're memorizing alongside lots and lots of application. So anyone that's not triple, I will see you all tomorrow at 1:30. So Edexcel starts at 1:30 and finishes at 4:30. So see you all tomorrow. Have a lovely evening. For those that are doing triple, please stay logged on. And we're going to start the triple session now. So converting sound waves, how are we able to hear? So the sound wave travels through a medium such as air and reaches the outer ear. That causes a vibration of the eardrum. The waves cause the eardrum to vibrate, which transfers the vibrations to the middle ear bones, which are the ossicles. These are the middle ear bones here. Your eardrum is that beginning part there. Then after it, you've got your ossicles. That then goes to the cochlea. Now the cochlea, in fact, let me just do this so it's a bit more clear. The eardrum is here. These are the inner bones. And this snail shell type shape is the cochlea. Now the cochlea in the inner ear converts these vibrations into electrical signals. So there's tiny hairs inside the cochlea, and when they vibrate and they're moved, because the cochlea is full of water, the vibrations from the inner ear cause the water to move. The water then causes movement in the hair, which then sends electrical signals to the auditory nerve, which is a sensory neuron, to the brain, and then the brain interprets it as a sound. Now ultrasound, our ears can detect between 20 hertz and 20,000 hertz. Ultrasound is anything that's above 20,000 hertz, so we can't hear it. The thing, if it came to our ear though, hitting, because 20,000 hertz means it's vibrating 20,000 times, it would still, anything over 20,000 would cause damage to our ears. Well, even less than 20,000 would cause damage, but it would be painful if you had ultrasound being put into your ear. Now we use ultrasound as medical imaging, so ultrasound scans. So if, for example, when someone is expecting or is pregnant, the ultrasound, a lady can use an ultrasound scan, and when the sound bounces off the child, of the unborn baby, the fetus, it bounces back and it shows the shape. It can be used in sonar systems, so like fishing boats or things like that, and in industrial testing. So what industrial testing means is, if you've got a piece of metal but there's an internal fracture, you hit it with ultrasound and you can see where the fracture is. And by fracture I mean where the breakage is. Bats, dolphins and some other animals use ultrasound for echolocation to navigate and find food. What is the range of human hearing? So that's infrasound. That's anything that's below 20 hertz. So our ears cannot detect less than 20 hertz. It can be produced by natural sources, so earthquakes, volcanoes, ocean waves, and man-made sources, which are explosions and machinery. Some animals like elephants and whales use infrasound to communicate over long distances. So here the issue is our ears are only being vibrated 20 times a second, and if it's less than 20 times a second, our ears treat as background sound. So right now you've got air particles hitting your eardrum, but you don't hear it as you're not hearing a bouncing sound. You're not hearing a sound of those air particles hitting your ear. Why? Because our brain ignores it, because it's too slow. So our brain ignores it. Otherwise you'll be hearing the air particles all the time. Uses of ultrasound. So ultrasound waves are utilized for detection and exploration due to their ability to travel through materials and reflect off surfaces. So we can use it for, as we've already covered, medical imaging. We can use it on sonars and non-destructive testing. So engineers can find cracks in structures like pipelines and aircrafts without damaging them. So how can waves be used for detection and exploration? Well, the easiest way to show it is like this. Let's say we've got a boat and there's some fish underneath. Now these little blue dots, I'll change them to red dots. So there's this red fish underneath and there's a big shoal of red fish just there. Now what will happen is ultrasound will be released. Now when it's being released at this middle point, as soon as it hits the fish, that part will now start reflecting back. But the bits that are going here, they don't reflect till afterwards. They reflect back once they've hit the ground or they've hit a different surface. They reflect back afterwards. So in the image, what you get when you're seeing it as an image, you see that there's something here, but you've got empty space in the other bits. Or it shows that there could be, let me just rub that out and show it again. So on the screen, what it'll show is where the shoal of fish is, it'll show that there's something there. For the other bits, it'll show that it's something there, where it's been reflected from. So they know that could potentially be a shoal of fish. And if it's a really good device, it'll even come up as fish shaped, because all the sound will bounce off each individual fish. The ultrasound will. So that's called, I suppose, echo. That would be called echolocation. So echolocation in animals, bats and dolphins use ultrasound to detect objects and navigate. And it checks depth and distance measurement. So ultrasound maps the seabed and checks materials thickness or flaws in machines. And sound waves, this is something I've already explained, but I'm not sure what's happened to the screen there. So sound waves are longitudinal. They cause particles to vibrate parallel to the direction of wave travel. These vibrations can travel through solid, liquids and gases. The speed of the sound wave depends on the medium. So sound waves travel faster through solids, then liquids, then gases. But in air, which is a gas, it travels at 330 meters per second. Now sound will not travel through a vacuum because there's no particles. So if you ever, for example, some of your teachers may have shown you a bell jar experiment. What bell jar experiment means is that you have the bell jar and all the air gets sucked out. And you have a bell inside the jar. The bell is working, so you can hear the bell ringing away. And as soon as you suck all the air out, you can no longer hear it. That's because there's no longer any particles to transfer the sound. So sound will not travel through a vacuum. Sound travels faster through a solid because the solid particles are arranged closer together, so it's quicker for the particles to pass the energy on. Okay, excellent. So that's the end of topic 4. Tomorrow, we are going to do our best to finish off topic 5. Now we're going to take a short break just till 4:15, and then we're going to continue with triple award biology. So I see you all in 4 minutes. Okay, welcome back. So now we're up onto our last session of the day. And we are going to do our best to finish at least topic 3 and topic 4 triple biology, and possibly some triple biology from topic 5 as well. So we're now up to 3.17b, which is ABO blood groups and what is codominance. So both alleles are equally expressed in the phenotype. So neither allele is dominant or recessive. So you know, when in your blood groups, you've got A blood group, B blood group, O blood group, and AB. Now, what this actually means is that they're all codominant. Well, O is not codominant, but A and B are codominant. So you have this as an example as blood groups, but an example is also when you've got cows. Red fur and white fur are both dominant. So if an offspring has both red fur and white fur, we call it a roan. It becomes a mix of both. So there's our example. We've got a white cow that looks more like a brown one, but that's a red cow. So you end up with a roan, which shows codominance. So how are blood groups inherited? Now A, B, and O are 3 different blood groups. There's 3 different alleles. You've got an allele for A, you've got an allele for B, and an allele for O. So that's blood group A, blood group B, and blood group O. Now, the way that should be shown, and this is my mistake for not sorting it earlier, it should be I to the power of A like this. And that's how it's represented in this topic. So how are blood groups inherited? So 25% will be A and B, as in they'll have an allele for A and an allele for B, which is blood group AB. So no, sorry, that's the answer. But what we're saying here is if you've got, for example, a mother who has an allele for A and an allele for O, and a father who's got an allele for B and an allele for O, that means the mother has blood group A, but it's homozygous, and the father has blood group B, but it's homozygous. So if you look at the offspring now, so it's the same process as what we showed before. We draw a Punnett square, now we put in our alleles, now we fill the Punnett square. So 25% will be blood group AB, 25% will be just blood group A, because A is dominant over O. 25% will be blood group B, because again B is dominant over O, and 25% will be O, and that's the only way you can have blood group O if you've got 2 alleles linked to O. Now describe why a child can be born with blood group AB. So as long as the child's parents both have, one of them has blood group A and the other one has blood group B, then there's a chance that their child will have blood groups A and B as well. Now, because they're both codominant, it means both alleles will be expressed. So that child's blood group will be AB. So in addition to this, we know that both alleles can be inherited from our parents. So describe why a child can be born with blood group AB. It can be linked to environmental factors, but that's not something we're going to look at from when we're answering questions. We're looking more at that when we inherit B from one parent, and we inherit A from the other parent, so except inherit A from mother or father, inherit B from mother or father, and allele A and allele B are codominant. Explain why a child with blood group A blood group A mother, and a blood group B father has inherited blood group O. So how is that possible? And that's because the mother must have blood group A, but is a carrier of the blood group O gene, and same with the father, except the father is blood group B and is a carrier of the O gene. So let's put this into a Punnett square, and we know so we know that blood group A and B are codominant and O is recessive. So that means the mother has to be this, and it means the father must be this. So 25% chance the child will be born with blood group O. Now explain why a child, no, we've covered this already. That's just a mark scheme. So I'll just pause on the mark scheme so you can see it, but it's exactly the same as what we saw in the previous slide. Now we've got 3.18b. This is the final triple topic from biology. Explain how sex-linked genetic disorders are inherited. So how are sex-linked disorders, sex-linked genetic disorders, inherited? Remember, well, how is anything passed on? Is passed on through the genes. But sex-linked genetic disorders have to be inherited through the sex chromosomes. So they are conditions caused by mutations in genes located on the sex chromosomes, specifically the X chromosome. Which means if it's a recessive disorder and it gets passed on to the male child, they 100% have it because it's only expressed on X. Whereas with the female, they can be a carrier as well. But it means if it's only carried on the X chromosome, males either have it or they don't have it. Females either have it, they're carriers, or they don't have it. Now the Y chromosome is smaller, so it carries fewer genes. So that's why a lot of sex-linked genetic disorders are not on the Y chromosome. They're predominantly on the X chromosome. This means there is no backup allele for genes on the X chromosome in males. Meaning if they get one X chromosome, they've got it. So females have two X chromosomes, and males have one X and one Y. Now, this, just to point out, this image should have been bigger. It should have been two of the same thing. Only one image is smaller, this one, and that's to represent Y. All the X chromosomes should have been shown as big. So two X chromosomes, a healthy allele, and can compensate for a faulty one. But in males, there's only one X chromosome, so there's no backup if a gene on the X chromosome is faulty. So sex-linked genetic disorders. How are sex-linked genetic disorders inherited, and why are disorders more common in males? So because males only have one X chromosome, if a gene is on the X, if a gene on the X is faulty, there's no backup copy on the Y chromosome. But in females, they've got an additional one. They've got two X chromosomes, so if one is defective, the normal one can compensate. Now, what is color blindness? So this is an example of a sex-linked genetic disorder. Females can be carriers if they inherit one defective allele, but typically don't express the disorder unless they inherit two defective alleles. Males express the disorder if they inherit one defective allele. So here again, females can be carriers, but they inherit one defective allele and they won't express the disorder. But for a male, if they get one X chromosome, they become colorblind. So it's more common in males for that reason. So let's see how it's passed on. So here we've got a mother who, this first chromosome, X chromosome's got a lowercase b, that means that's a recessive allele. And we've got X capital B, that's a dominant allele. So the problem, the colour blindness, is being carried in this one, in the one that I've circled red. So I'm just going to delete that one. So what that means is we've got a female here who's a carrier, because the father's X chromosome is normal, and we've got a daughter here, a girl here, who has capital B, so that's not completely normal. Now, in terms of the boys that are born, the males, this particular male or this particular boy will have colour blindness. This boy will be normal. So daughters, there's a 50% chance of being carriers, but in the boys, there's a 50% chance of being affected, 50% chance of not being affected. So this is the benefit of having the extra X chromosome. So genetic testing helps families with history of sex-linked disorders to check the risk of passing them to their children. Okay, so this is the bit that we've already covered, so I'm just going to move on. I think we have covered this now. Haemophilia. Now, haemophilia, like colour blindness, is a sex-linked genetic disorder. It's a condition where blood doesn't clot properly. So if someone's got haemophilia, if they get a cut, they just keep bleeding. It's difficult for the cut to heal. It's a condition where, so they'll keep bleeding. It does heal, but it takes a lot longer than your average person. It's also recessive and X-linked. It works similar to colour blindness. So if you've got a mother who is a carrier of haemophilia, but she has a normal gene, that means that mother does not have any problem. She's heterozygous, meaning she's got one normal gene, one haemophilia gene, and the father is normal because he's carrying a normal gene. Now, unfortunately, now what that means is there's a 25% chance that a female will be born as a carrier. That's this child here. There's a 25% chance the child will be born normal, unaffected, completely unaffected, and not even carrying the gene. Then with the males, we've got one that's affected. So it's the capital H gene. This has been done the wrong way around. Sorry, it should be here. It should be X small h y. So it's this child here that's affected, and this one is unaffected. So there's a 25% chance from all the children, one child will have haemophilia, and specifically it's the boy. So the only way a girl will get it is if the father is also a carrier, or if the father has it, sorry. So let's have a look at this one. State and explain the phenotype of person Z. The diagram shows the inheritance of Duchenne muscular dystrophy in a family. Now, with these kind of questions, you don't actually need to know if it's recessive or if it's dominant. You've got to be able to work everything out by looking at the image. So before we even look at the answer, let's zoom in and let's work out what's what. So what we've got here at the beginning is a carrier female, and we've got unaffected male. Now, we then have an affected male just here. That means he got the X chromosome with the gene that causes the illness. This female here is a carrier. Person Z is a male. Now, if you look over here, we've got a white circle. That's an unaffected female. That unaffected female must have two X chromosomes without the defective gene. That means she's got an X chromosome from the male, from person Z, that is unaffected. So that means person Z's X chromosome must be X and Y, but it must be unaffected. So I'm going to just put it as a small h. Otherwise, that daughter would have two X chromosomes that have the recessive X-linked disorder, and she'd be a carrier. The fact that she's got two normal ones, two normal genes, means she's got the one normal gene from the dad and one from the mum. So it won't be small h, it'll be a capital H. So females can be carriers with one faulty X. So Duchenne muscular dystrophy is a recessive X-linked disorder. Females can be carriers with one faulty X, but only affected if both X's are faulty. So males are affected if they inherit one, because there's no backup X. So if the mother is a known parent, person Z must be a male, and an unaffected daughter inherited a healthy X from her father. So he has to be one healthy X and Y. Okay, that's the end of topic 3. So we're now going to move on to topic 4. Now, as I'm going through topic 4, I'm going to cover the topics which are standalone topics. But topics that are part of a sequence, I'll try to teach at the same time as I'm teaching combined, so you can see how they make sense from a sequence perspective. And I'm going to do the same with topic 5. So that's 17 and 18 done. Oh, sorry, I have put up the wrong slide. It'll just be 1 minute. So we're going to start from 4.1. So in terms of what we're covering right now, we're going to try our best to cover 4.1, 6, 4.9, 4.12 and 4.13, because these are the biology only topics. So 4.1b is linked to the work of Charles Darwin and Wallace, and the theory of evolution, and it's to explain why most scientists do not accept their research. And of course, there's people, scientists that still don't accept the research, and there's people with certain religious beliefs that don't follow or believe their research either. So there is not, it is a hypothesis that's become a theory because many scientists agree with it now. But from an evidence perspective, it is still something that doesn't have enough evidence to say it's definitive that this is the one and only way that's occurred. If anything, the original theory of evolution has changed. It's evolved, I suppose. So Charles Darwin, he proposed the theory of evolution by natural selection. So in 1859, he published a book called On the Origin of Species, detailing how species evolve over generations through natural selection. Now, what's really important with this whole topic is if you understand the process of natural selection, there's a few steps, and that's what we're going to go through tomorrow. The questions become really, really easy. So that's Charles Darwin. Now, why was the theory of evolution only gradually accepted? So it challenged the idea that God was the creator of the universe. So religious beliefs, which taught that all species were created exactly as they were. So that some religions have that belief. There was limited evidence at the time, as fossil records were incomplete, and even now they are incomplete because most fossils get destroyed within magma or under the ground. At some point they get destroyed, and scientists do not yet understand genetics, and they get distorted because of all the pressure. And it was a new and controversial idea. It was different from the belief that species were fixed and unchanging. So Darwin attempted to find the following evidence. So he tried to find fossils, he tried to find geographic distribution. Now, genetic inheritance was not understood until 50 years after the theory initially published. So the fact that he found a species, for example, an animal that in Africa that was similar to an animal in another continent, they didn't understand the genetic link till a long time after. So who was Alfred Wallace? So he was a scientist who independently developed a theory of evolution by natural selection. If anything, it was very similar to Darwin. He's especially known for his work on warning coloration and studying and on those kind of topics, but mainly warning coloration. So the fact that if an animal has certain bright colours, it's more likely to survive and therefore pass on its genes. And also speciation. So warning coloration is when animals have bright, bold colours to warn predators that they're poisonous. And there's some animals that they have warning coloration, as in it's the animals that have bright colours, but they're not actually poisonous. So that means due to a genetic mutation, one of them would have been born with brighter colours, and that particular animal survived better and passed its genes on over generations. That colour became the most common one. And speciation is where, because animals become isolated from each other, they start to develop differently based on their surroundings. So you end up with very similar animals, but you get to the point where you get animals that are very similar looking, like for example seagulls, but they've become almost like new species where they can't reproduce, like tigers and lions, for example. Now, which scientist wrote on the origin of species? It was Charles Darwin. And the reason he wrote it is because he found out how close Wallace was, and as in they shared notes and they discussed things, and they could see that they were both heading in the same direction. So he, for that reason, increased the speed at which he published his book. Wallace was also going to publish a book, but Charles Darwin ensured that he got his out first, which is why he gets credited more. Which statement is supported by the theory of evolution? New species evolve over many generations. So that is the definition of evolution. Okay, so we'll go through evolution tomorrow, and we'll go through the fossil record in more detail tomorrow. We'll look at evidence for evolution in more detail tomorrow. 4.6. So describe how the anatomy of the pentadactyl limb provides scientists with evidence for evolution. So this is a limb that has 5 digits. So the pentadactyl limb is a powerful example of how evolution has shaped. So it's a potential example of how evolution has shaped the anatomy of vertebrates. So this structure provides compelling evidence for common ancestry and adaptive evolution. So if you look at a lot of different animals, a lot of them have a pentadactyl limb, but in different forms. So even, for example, a whale has a pentadactyl limb, but it's just shaped more like a fin now. It's shaped differently. So here you've got a human, a horse, a cat, a bat, and a whale. If you look closely at all of them, the horse one is not very obvious, but it's just this area here. It has 5 digits. Well, it is small, and it's the main hoof that comes from it. Cats, 5 digits. Bats have those 5 digits, but now it's in the form of a wing. The whales have it as well, but now it's in the form of a fin. So the pentadactyl limb is a limb with 5 digits, fingers or toes, found in animals including humans, cats, bats and whales. The bones have the same basic structure, even though they're used for different functions like walking, flying or swimming. So this is potentially, could be seen as them having a common ancestor. It's not definitive, because again they would need to be a full fossil collection showing how they've come from a common ancestor, but it's potential evidence. So over time, species have adapted the pentadactyl limb for various functions, depending on their environment and lifestyle. So humans for writing, for using their hands, bats for flying, whales for swimming, cats for running, and also from a predator perspective. So how does it actually demonstrate evolution? So this is from a summary perspective. The pentadactyl limb is found in many vertebrates, all sharing the same basic bone structure, and they perform different functions with it, like walking, flying, swimming. And that shows that potentially species have evolved from a common ancestor, and through natural selection they've now adapted into different usage. So there's a diagram. Describe how the structure of these limbs provides scientists with evidence for evolution. So it shows that in the diagram it shows all the animals have pentadactyl limbs. Despite them having different functions, the pentadactyl limb has the same bone structure, indicating a common ancestor. And the species then have adapted due to natural selection and now have different functions. Humans have arms and hands for manipulation and tool use. Birds have wings for flight. Whales have got flippers for swimming. Cows and horses have legs for running. So let's look at the mark scheme answer. They have a pentadactyl limb. Yep, we covered that. They've got potentially a common ancestor that also had a pentadactyl limb. How the structure has been adapted to different functions is part of the answer. So how humans use it, how cows use it, how birds use the pentadactyl limb, how whales use it, is all part of the answer to get you 3 marks. Okay, so we'll go through this classification topic tomorrow. The key part of this topic is the 3-domain system. It's really important that you fully understand that. It is becoming a more and more common question. But we want to get to 4.9 now. Oops, it's paused, it's not changing slide. Must have pressed it too many times. I did press it too many times. So I just want to take it back to 4.9. And tomorrow we'll go through genetic engineering as well. Tissue cultures. So describe the process of tissue culture and its advantages in medical research and plant breeding programs. Now, what I would advise is if you, for all these videos up to, I think we're up to around 4.11, all the videos are available on AMALearning. So I would advise that you have a quick look through those videos as well. They're really, really good and they're straight to the point with some exam practice as well. So what is cloning? It's asexual reproduction, and that produces offspring that are genetically identical to both their parent and to each other. These identical offspring are known as clones. So, what is tissue culture? Tissue cultures are a technique used to grow new plants from a small group of cells taken from a parent plant. So, for example, if you've got a banana tree, and that banana tree has, well, this would be better if I drew this in green, but this banana tree has the perfect banana, not perfect, but the banana that everyone loves and enjoys to eat. Then what you would do is you would take a cutting from it, and then you can grow that cutting separately, and it would be then make a clone of that tree that sells with the banana that sells easily. So you take a small piece of plant tissue, like from a stem or a root, you cut from a healthy parent plant. The tissue sample is placed into a container with agar jelly, in other words nutrients. So it contains nutrients, water and plant hormones to help the cells grow. The cells divide and form a small clump of cells called a callus. Now the callus is encouraged to grow roots. So again, you add hormones like auxin, and what auxin does, it increases the root growth, and like gibberellins that increase the stems and the leaves to become new plants. And that then becomes a nice new tree, a nice new plant, but it's exactly identical to the one that you wanted. So advantages: it's faster than sexual reproduction. The clones keep the desired traits. So remember, if you think back to, I think it was 3.1, when we looked at the advantages of asexual compared to sexual, same things here, is faster. Clones keep the desired traits. You can grow plants all year round, and it help grow rare or endangered plants. Now disadvantages: everything is identical, so there's less adaptable to change. It's a reduced gene pool. So both these issues, reduced gene pool and less adaptable, mean there's an increase in vulnerability to disease changes, and there's a risk of contamination. And what are the advantages of producing plants in the way shown in the picture? So this is an exam practice question. Plants are grown much more quickly. So essentially the answer is the advantages there. They're grown much more quickly. All new plants are exact copies from the parent, so all the useful traits are passed onto the offspring. This method can be used to protect and grow rare or endangered plant species. So let's have a look at the mark scheme. Yep, many plants produced, quicker than sexual reproduction, genetically identical, so all the desired characteristics are still there, and you can save endangered species. Okay, let's move on to 4.12. Now 4.12 fits in with selective breeding, as does 4.13. So now what we're looking at is explain the advantages and disadvantages of genetic engineering to produce GM organisms, including the modification of crop plants, including the introduction of genes from insect resistance from Bacillus thuringiensis into crop plants for thuringiensis. So I'm just going to call that BT from this point onwards. So what we're essentially looking at here is the advantages and disadvantages of genetic engineering. So Bacillus, or BT, is introduced into DNA of crops. Now, genetic organisms are those whose DNA has been modified using genetic engineering to introduce characteristics such as insect resistance or drought tolerance. Now, genes from the bacterium Bacillus thuringiensis are introduced into crop plants like maize or cotton. So the way they're introduced is through genetic engineering, which we're going to cover tomorrow. And once they're introduced, the BT gene is isolated and inserted into the DNA of the target crop plant. The modified crop then produces the BT toxin. So it releases the toxin that bacteria releases. So remember, if you think back to what we covered, actually this is what we're going to cover in 2 days' time, when we cover how bacteria causes us harm, and bacteria releases a toxin. Now this crop releases that same toxin. So when an insect tries to eat this crop, it kills the insect. And in fact, the crop is able to release the BT toxin without it being eaten as well. But that helps destroy the insects around. So the benefits of that would be an increased crop yield. So possible harm to other species, but the risk is it causes harm to other species. So there could be beneficial insects around there as well, like for example bees, etc., that don't eat their crop, but they die from the toxin also. That means that less pesticides need to be used, but that means resistant crops will start spreading more and more, and cost effective for farmers, but we don't actually know the long-term effects from an ecosystem perspective. That's a real big problem. This is something that they've only recently started using. We don't know the long-term effects of it. Improved food quality. So golden rice is rice that's got vitamins inside it. So they've genetically modified the rice, so it has certain vitamins inside, which means you've got better food quality, or at least food with more vitamins. But there is ethical concerns. Some people don't like the thought of having genetically modified food, and it can be used for medical use. So genetic engineering can be used to make, for example, insulin, and that's the example I'll be going through tomorrow. But genetically modified crops can end up causing a reduction in biodiversity. So here's some, this is an actual past paper question. Explain the advantages and disadvantages of growing GM corn plants. And there's the answer. The advantage is pest resistance, higher crop yields, reduced pesticide use, and it's cost effective because it saves money. But it's possible that the genetically modified corn might kill beneficial insects. It can reduce biodiversity. There's a risk of gene transfer, so that actual gene that's in the corn plant could spread to a wild plant, creating a superweed that doesn't get eaten or killed off by insects. And expensive seeds. So genetically modified seeds, and a good example is grass. So if you're ever in B&Q, or if you're next time you're with a member of family that wants to buy some grass seeds, the best grass seeds, they have a lining on the outside of them. This is due to them being genetically modified, which means they don't actually plant themselves until it rains. When it rains, this outer lining dissolves, and then they start to grow. Some of that is due to just an artificial layer that's put on top, but they've genetically modified certain types of grass seeds so that they don't actually start growing to a certain point. But that makes those seeds more expensive. Okay, advantages and disadvantages of agricultural solutions to the demands of growing human population, including the use of fertilizer and biological control. So this is how farmers can grow more crops and the solutions for it. So there's use of fertilizers, but there's also biological control. Biological control just means the release of certain types of insects that will feed off pests. Now, how can agricultural solutions meet the demands for food? The following can be used to meet the demand for food. Genetic engineering, intensive farming, biological control, and selective breeding. So selective breeding and genetic engineering will go through as part of topic 4, but they can be used to meet the demands for food. So what are fertilizers? They're substances that we add to the soil to provide the plants with nutrients, things like nitrogen, which we need for growth, phosphorus, potassium, to ensure that the crops are grow healthy. So you've got natural fertilizers that come from animal waste, from plants that have been rotting plants, or bone meal, so that's bones that have been grinded down. So that's all natural material. Then you've got artificial fertilizers. They're made in factories and they're designed to provide the specific nutrients. So natural fertilizers take a bit longer to break down. They're not specific. But artificial fertilizers, you can get specific ones that have a certain amount of nitrogen, phosphorus and potassium. So if you look at the difference between organic and inorganic, organic is just capsules that, well, it is just a certain, well, I'm not sure what the material feels like, but you just spray it in and fold it into the soil. What are the advantages and disadvantages of using fertilizers? So one of the advantages is it gives more crops. That means you've got more food to feed people with. It's efficient land use. So now we've got more food from some land, but it reduces deforestation. So now we don't need to use as much land because we're making more food. And there's customized solutions as well. Different fertilizers fix specific nutrient problems. And the disadvantage is the environmental impact. So it can cause eutrophication, and that can cause harm to aquatic life. And what that means is some of the fertilizer can make its way into the water, and that can then ruin the ecosystem within the water because the plants grow really fast. Then you've got less light going in, so the plants on the ground level start to die. And it's the plants that provide the water with oxygen. That means the other organisms that need the oxygen for respiration, they start to die. Then you've got soil degradation, so it damages the soil structure and reduces biodiversity. And then there becomes a dependence on chemicals. So farmers rely too much on artificial input. So what is biological control? Biological control is a method of controlling pests by using natural predators, parasites, or pathogens, diseases, to reduce the pest population. Instead of using chemicals like pesticides, and biological control uses living organisms. So what farmers have done for many years is sprayed pesticides, and that kills off the insects. But biological control is just more insects that kill off those insects. So for example, aphids is like a green, so you might see them in summer, you might see leaves full of aphids, these little green little things. Ladybirds eat them. So that would be an example of, so there's an example, ladybirds used to control an aphid infestation. So what are the advantages and disadvantages of biological control? So it's environmentally friendly. We're not having to use chemical pesticides. So this is part of the reason why, I mean, when you eat fruit, you would clean it anyway, but a bigger reason to clean it, and I've seen videos on people that use certain, what's called like baking powder to make sure it reacts with all the chemicals on the outside, because you have chemical residue, particularly if you look at grapes. Then you've got sustainable, it's sustainable. Natural predators can maintain pests over time. They're eating, they've got loads of food, they're reproducing. Better crop quality, fewer chemicals, safer crops. Now there's unintended consequences. So predators may harm non-target species. So for example, the cane toad was released in Australia, but no one realized the actual cane toad. The problem with the cane toad is there was no predators there. So now the cane toads have just multiplied and they've caused harm to non-target species as well. Sometimes there's slow results because it takes time to reduce the pests, and limited scope. So if you release loads of ladybirds, it's only going to kill a few types of pests. It's not going to get rid of every type of pest. So using ladybirds to control insect pests is an example of biological control. Explain the advantages and disadvantages of growing corn, GM corn plants. So let's have a look at mark scheme for this one. If we use GM corn plants, it means we don't need to use as many pesticides or chemicals, because GM corn releases the Bt toxin. In the human DNA, forget that one. So pests do not become resistant to insecticides. I'm not sure where that line in the middle's come from. That makes no sense at all. So pests do not become resistant to insecticides, because that's what happens. If you keep using pesticides, then based on survival of the fittest, the ones that survive are the strong ones that will have some sort of resistance. So over time, all the insects become resistant. Now, all you can say is specific to the pest. So other beneficial, so other insects or animals are not affected. So you can have, in the GM corn, for example, you can have a toxin that only affects a certain type of pest. So it could be caterpillars, for example, but it doesn't affect birds and other animals. Okay, so that's the end of our topic 4. Okay, we're going to finish there for today. Thank you everyone that's been on since 1:30. Really appreciate it. Please keep sharing and liking our videos. Up to now we've had around 500 plus views of everything that we've gone through. Over 1,000 views of our first video. So we really appreciate all the support, all the love. Okay, have a wonderful evening. I'll see you all tomorrow for day 5.